Hi everyone, and welcome to this complete audiobook for ASNZS 3000-2007, made to support your EWRB regulation exam study. My name is Aria, and this full recording brings all 8 sections together in one place, so you can listen and learn without switching between videos. Alright, let's get started with the full book. Settle in, relax, and enjoy the lesson. Hi everyone, and welcome to this audiobook designed for the EWRB Electrician Regulation Exam. My name is Aria, and I work alongside Whit Roy as an electrical tutor. This audiobook explains the exam topics in simple spoken language, making it easier to understand and review anywhere, anytime. Welcome to this audiobook for Part 1 of ASNZS 3000-2007. Also known as the wiring rules. Before we begin, I want to be very clear, this audiobook does not replace the standard, and it must not be used instead of the official wording. When you do real electrical work, or when you sit an EWRB exam, you must use the exact text of the standard itself. My goal here is simple. To explain Part 1 in plain spoken language so you can listen, follow along easily, and understand the meaning behind each clause, even when you're driving or not reading the document. Everything you hear is based directly on the original 2007 standard. No rules are added, nothing changed, only rewritten so it's easier to understand. Alright, let's get started. Part 1 Scope, Application and Fundamental Principles. Section 1.1 Scope explains what Part 1 of ASNZS 3000 covers. Part 1 deals with the broad safety rules that apply to electrical installations. It lays out the high-level requirements, the essential things an installation must achieve so people, property, and livestock stay safe. These principles apply to every electrical installation covered by the standard. They apply no matter whether you are building a new installation, altering an old one, adding onto something, or repairing existing work. So think of Section 1.1 as the big picture rules. What the installation must achieve to be safe during normal use, during faults, and in any expected environmental conditions. Section 1.2 Application explains where Part 1 applies. Part 1 applies to all electrical installations covered by the standard unless a specific clause says otherwise. This includes new work, additions, alterations, and repairs. The key idea is that anyone designing, installing, testing, or verifying an installation must follow the safety principles set out in this part. Nothing in this section replaces any legal obligations under other regulations or laws. It simply tells you how Part 1 fits into the overall requirements for electrical safety. Section 1.3 Reference Documents tells you that the standard refers to other documents, such as equipment standards or installation standards, that support the rules in ASNZS 3000. These reference documents help explain how to select equipment, how circuits should be arranged, how testing is done, and how safety requirements are met. The important thing to remember is this. When the standard refers to another document, that reference document becomes part of the requirement, but only for the specific clause where it is mentioned. So you only need to use the reference documents where the standard tells you to. Section 1.4 Definitions. 1.4.1 Application of definitions. These definitions help us understand how certain words are used throughout the standard. Think of this section as the standard's own dictionary. Whenever the standard uses one of these terms, it is using the specific meaning listed here, not the everyday meaning. I will now explain each definition in simple spoken terms. 1.4.2 Accessible, readily. Something is considered readily accessible when it can be reached quickly without climbing over objects, removing obstructions, standing on a chair, or using a movable ladder. It must not be more than 2.0 meters above the ground, floor, or platform. 1.4.3 Accessory. An accessory is any device such as a switch, fuse, plug, socket outlet, lamp holder, fitting, adapter, or ceiling rose, used with wiring, luminaires, switchboards, or appliances. It does not include lamps, luminaires, appliances, or the switchboard itself. 1.4.4 Active or active conductor. An active conductor is any conductor that is kept at a potential difference from the neutral or earthed conductor. If the system does not have a neutral or an earthed conductor, then all conductors are considered active. 1.4.5 Aerial conductor. An aerial conductor is any stranded conductor, including aerial bundled conductors, that is supported by insulators or purpose-designed fittings above the ground and directly exposed to the weather. 1.4.6 Appliance. An appliance is any consuming device, other than a lamp, where electricity is converted into heat, motion, or another form of energy, or where the electrical characteristics of the electricity are substantially changed. 1.4.7 Appliance. Fixed. A fixed appliance is one that is fastened to a support or is otherwise secured in a specific location. 1.4.8 Appliance. Handheld. A handheld appliance is a portable appliance designed to be held in the hand during normal use, with any motor forming an integral part of the appliance. 1.4.9 Appliance. Portable. A portable appliance is one that is moved while operating, or one that can easily be moved from one place to another while still connected to the supply. Clause 1.4.10 Appliance. Stationary. A stationary appliance is either a fixed appliance, or an appliance that weighs more than 18 kilograms and does not have a carrying handle. Clause 1.4.11 Area. Hazardous. A hazardous area is a location where an explosive atmosphere is present, or may reasonably be expected to be present, in quantities that require special precautions for the construction, installation, and use of equipment. Clause 1.4.12 Arm's reach. Arm's reach is the zone extending from any point on a surface where a person normally stands or moves, to the furthest distance the person can reach with the hand in any direction, without using anything for assistance such as tools or a ladder. Clause 1.4.13 Authority. Regulatory. A regulatory authority is a government agency responsible for the relevant legislation and how that legislation is applied. Clause 1.4.14 Authorized person. An authorized person is either the person in charge of the premises, a licensed electrical contractor, an electrician, or another person appointed or selected by the person in charge to carry out duties on the premises. Clause 1.4.15 Available. Readily. Something is readily available when it can be reached for inspection, maintenance, or repairs without needing to dismantle cupboards, benches, structural parts, or similar. Clause 1.4.16 Barrier. A barrier is a part that provides basic protection from any usual direction a person might approach from. This definition also cross-refers to basic insulation in Clause 1.4.60 and basic protection in Clause 1.4.77. Clause 1.4.17 Cable. A cable may be a single cable core or two or more cable cores laid together, with or without fillers, reinforcements, or protective coverings. Clause 1.4.18 Cable. Armored. An armored cable is a cable wrapped with metal, usually tapes or wires, mainly to provide mechanical protection. Clause 1.4.19 Cable core. A cable core is a conductor along with its insulation, but does not include any mechanical protective covering. Clause 1.4.20 Cable. Flexible. A flexible cable is one whose conductors, insulation, and covering provide flexibility. Clause 1.4.21 Cable. Mineral insulated metal sheath, MIMS. This type of cable uses compressed powdered mineral insulation enclosed in solid drawn metal sheathing. It may be single core or multi-core. Clause 1.4.22 Cable. Neutral screened. A neutral screened cable consists of one or more cores laid together, with or without fillers, surrounded by a concentric wire outer conductor, and protected by an insulating sheath. Clause 1.4.23 Cable. Sheathed. A sheathed cable has one or more cores surrounded by a sheath. Clause 1.4.24 Ceiling. Suspended. A suspended ceiling, as described in ASNZS 2785, is a ceiling system hung below the floor or roof above. Clause 1.4.25 Circuit. A circuit includes live conductors, protective conductors if any, a protective device, and the associated switchgear, control gear, and accessories. Clause 1.4.26 Circuit breaker. A circuit breaker is a switch designed to open a circuit automatically when preset conditions occur, such as overcurrent or undervoltage, or when operated by external control. Clause 1.4.27 Class 1 equipment. Class 1 equipment does not rely on basic insulation alone for protection. Accessible conductive parts are connected to the protective earthing conductor so they cannot become live if basic insulation fails. Clause 1.4.28 Class 2 equipment. Class 2 equipment also does not rely only on basic insulation. It uses double insulation or reinforced insulation and has no provision for protective earthing. It may be A. Insulation encased, B. Metal encased with double or reinforced insulation, or C. A combination of both types. Clause 1.4.29 Class 3 equipment. Class 3 equipment relies on SELV for protection and does not generate voltages higher than SELV. Clause 1.4.30 Competent person. A competent person is someone who has the training, qualifications, experience, or a combination of these, to perform the required task correctly. Clause 1.4.31 Conductor. A conductor is any material capable of conducting electricity. Clause 1.4.32 Conductor, bare. A bare conductor is a conductor without insulation or covering. Clause 1.4.33 Consumers' mains. Consumers' mains are the conductors between the point of supply and the building or structure where they terminate. Clause 1.4.34 Contact, direct. Direct contact means contact of a person or an animal with live parts. Clause 1.4.35 Contact, indirect. Indirect contact means contact of a person or an animal with an exposed conductive part that has become live under fault conditions. Clause 1.4.36 Cord, flexible. A flexible cord is a flexible cable consisting of one or more flexible conductors. Clause 1.4.37 Current, fault. Fault current is the current that flows in a circuit during a fault. Clause 1.4.38 Current, overload. Overload current is a current that is higher than the rated current of equipment or conductors, but not caused by a fault. Clause 1.4.39 Current, short circuit. Short circuit current is a current resulting from a short circuit fault. Clause 1.4.40 Damp situation. A damp situation is a location where moisture is present in an amount that is enough to affect the safety of electrical equipment installed there. Clause 1.4.41 Distribution board. A distribution board is a switchboard that supplies one or more final subcircuits. Clause 1.4.42 Duct. A duct is a closed raceway of rectangular or circular shape for housing conductors. Clause 1.4.43 Earthed. Earthed means connected to the general mass of Earth. Clause 1.4.44 Earthed situation. An earthed situation is one in which exposed conductive parts are connected to the earthing system. Clause 1.4.45 Earth fault loop impedance. Earth fault loop impedance is the impedance of the earth fault current path, starting and ending at the point of the earth fault. This includes all active conductors, the protective earthing conductor, and the neutral conductor where relevant. Clause 1.4.46 Electrical equipment. Electrical equipment is any item used for purposes such as generation, conversion, transmission, distribution, or use of electrical energy. Clause 1.4.47 Electrical installation. An electrical installation includes any fixed appliances, wiring, switchgear, control gear, and accessories that use or distribute electricity in a building, structure, or premises. Clause 1.4.48 Electrical installation, domestic. A domestic electrical installation is one associated with a dwelling intended for residential purposes. Clause 1.4.49, Electrical installation, multiple. A multiple electrical installation is an installation where more than one consumer occupies parts of the same building. Clause 1.4.50, Electricity distributor. An electricity distributor is an organization responsible for the distribution of electricity through a distribution system. Clause 1.4.51, Enclosure. An enclosure is a part that provides protection of equipment against external influences, and provides protection against contact with live parts from any direction of access. Clause 1.4.52, Equipotential bonding. Equipotential bonding is the connection of conductive parts to keep them at substantially the same potential. Clause 1.4.52a, Explosive atmosphere. An explosive atmosphere is a mixture with air, under normal atmospheric conditions, of flammable substances in the form of gas, vapor, mist, or dust, where combustion spreads after ignition. Clause 1.4.53, Exposed conductive part. An exposed conductive part is a conductive part of equipment that can be touched and that is not normally live, but may become live under fault conditions. Clause 1.4.54, Extraneous conductive part. An extraneous conductive part is a conductive part that is not part of an electrical installation but is able to introduce a potential, usually earth potential. Clause 1.4.55, Fault current limiter. A fault current limiter is a device intended to limit the prospective fault current to a preset value. Clause 1.4.56, Functional earthing, FE. Functional earthing is earthing required for correct operation of equipment, not mainly for safety. Clause 1.4.57, Fuse. A fuse is a device that opens a circuit by melting a conductor when current exceeds a set value for a long enough time. Clause 1.4.58, Installation coupler. An installation coupler is a device used to connect fixed wiring to equipment without using tools. Clause 1.4.59, Insulated. Insulated means separated from other conducting surfaces by a dielectric that is capable of withstanding the required voltage. Clause 1.4.60, Insulation system. An insulation system refers to basic insulation and supplementary insulation, or reinforced insulation. Clause 1.4.61, International Ingress Protection Classification, IP classification. The IP classification identifies the degree of protection provided by enclosures against the entry of solid foreign objects and moisture. Clause 1.4.62, Isolation, isolating function. Isolation is the function of disconnecting a circuit or equipment from every source of electrical energy to ensure safety. Clause 1.4.63, Live part. A live part is a conductor or conductive part intended to be energized in normal operation, including the neutral in certain systems. Clause 1.4.64, Luminaire, lighting fitting. A luminaire is an appliance designed to produce light, and to distribute, filter, or transform the light from one or more lamps. It also includes all parts needed to support or protect the lamp and to connect it to the supply. Clause 1.4.65, Main earthing conductor. The main earthing conductor connects the main earthing terminal to the earthing electrode. Clause 1.4.66, Multiple earth neutral system, MEN system. An MEN system is one where the neutral is connected to earth at multiple points, including the installation's main earthing terminal. Clause 1.4.67, Neutral conductor or midwire. The neutral conductor is a conductor connected to the neutral point of a system and able to carry current under normal operating conditions. Clause 1.4.68, Obstacle. An obstacle is a part that reduces the likelihood of unintentional contact with live parts, but does not prevent deliberate access. Clause 1.4.69, Outbuilding. An outbuilding is any detached building that is associated with the main structure on a property. Clause 1.4.70, Overcurrent. Overcurrent is a current greater than the rated value of the equipment or conductor. It includes overload current and short-circuit current. Clause 1.4.71 Plug. A plug is a device attached to a flexible cord or cable, intended for insertion into a socket outlet. Clause 1.4.72 Point in wiring. A point is a termination of the fixed wiring for connection of current using equipment. Clause 1.4.73 Point of attachment. The point of attachment is the point where overhead consumers' mains are attached to a building or structure. Clause 1.4.74 Point of entry. The point of entry is the point where underground consumers' mains enter a building or structure. Clause 1.4.75 Point of supply. The point of supply is the point where electricity is supplied to the electrical installation by the electricity distributor. Clause 1.4.76 Protected extra low voltage, PELV. PELV is an extra low voltage system that is not electrically separated from earth, but provides protection by using low voltage and other measures. Clause 1.4.77 Protection, Basic. Basic protection is protection against electric shock under normal conditions, by preventing direct contact with live parts. Clause 1.4.78 Protection, Fault. Fault protection is protection against electric shock in the event of a fault, by preventing indirect contact with exposed conductive parts that become live. Clause 1.4.79 Protective earthing conductor. A protective earthing conductor connects exposed conductive parts to the earthing system to safely carry fault current. Clause 1.4.80 Residual current device, RCD. An RCD is a device intended to automatically disconnect the supply when the residual current reaches a given value under certain conditions. Clause 1.4.81 Ripple-free DC. Ripple-free DC is direct current with ripple content not exceeding 0.1%. Clause 1.4.82 Safety service. A safety service is equipment that provides essential safety functions in an emergency, such as lighting, alarms, or fire protection systems. Clause 1.4.83 Separated extra low voltage, SELV. SELV is an extra low voltage system that is electrically separated from earth and from other circuits, giving protection against electric shock. Clause 1.4.84 Service protective device. A service protective device is a protective device installed by the electricity distributor to protect the service conductors. Clause 1.4.84a Shall indicates a mandatory requirement of the standard. Clause 1.4.84b Should indicates a recommendation, not a mandatory requirement. Clause 1.4.85 Socket, cord extension. A cord extension socket is the socket outlet that is part of a cord extension set. Clause 1.4.86 Socket outlet. A socket outlet is a device fixed to the wiring of an electrical installation, intended to accept a plug. Clause 1.4.87 Source of supply. The source of supply is a transformer, generator, converter, or other supply equipment that provides electricity to an installation. Clause 1.4.88 Subcircuit. Final. A final subcircuit is the circuit that supplies directly to current using equipment. Clause 1.4.89 Submains. Submains are conductors between the main switchboard and a distribution board. Clause 1.4.90 Substation. A substation is an assembly of equipment where voltage is transformed, or where switching or protection equipment is installed. Clause 1.4.91 Switchboard. A switchboard is an assembly of switchgear, control gear, bus bars, and associated equipment used to control, protect, and distribute electrical power. Clause 1.4.92 Switchboard. Main. The main switchboard is the switchboard that contains the main switch or switches for the electrical installation. Clause 1.4.93 Switchgear. Switchgear includes switches, fuses, circuit breakers, and other equipment used for switching, controlling, and protecting electrical circuits. Clause 1.4.94 Touch current. Touch current is the electric current that flows through a human or animal body when touching parts that are not intended to be live. Clause 1.4.95 Touch voltage. Touch voltage is the voltage that appears between parts that can be touched at the same time by a person or an animal. Clause 1.4.96 Track system. A track system is a system with one or more conductors arranged for movable or repositionable luminaires or current-using equipment. Clause 1.4.97 Trunking cable. Cable trunking is a closed enclosure of rectangular or circular shape used for accommodating cables. Clause 1.4.98 Voltage. Voltage is the difference in electrical potential between 2 points. Clause 1.4.99 Wiring catenary. Catenary wiring is wiring suspended between supports, usually using a supporting messenger wire. Clause 1.4.100 Wiring enclosure. A wiring enclosure is any enclosure intended to provide mechanical protection for wiring. Clause 1.4.101 Wiring equipment. Equipment wiring refers to wiring that forms part of electrical equipment, rather than part of the fixed installation. Clause 1.4.102 Wiring installation. Installation wiring is the wiring of an electrical installation, excluding equipment wiring and flexible cords. Clause 1.4.103 Wiring underground. Underground wiring is wiring installed below ground level, with mechanical protection and insulation suitable for that environment. All definitions from Clause 1.4.1 to Clause 1.4.103 are now fully completed. Section 1.5 Fundamental Principles. Clause 1.5.1 Protection against dangers and damage. Section 1.5 explains the core safety ideas behind the ASNZS 3000 wiring rules. These principles are the foundation of the entire standard. If you understand these ideas, the rest of the book becomes much easier to make sense of. Clause 1.5.1 looks at what we must protect people, animals, and property from. Electrical installations can create several kinds of danger, but the standard highlights 3 main risk areas. A. Shock current. Shock current is electricity passing through a person or an animal. There are 2 kinds of electric shock we must think about. Direct contact. This happens when someone touches a part that is meant to be live in normal service. For example, an exposed terminal or a damaged cable where the active conductor is visible. Indirect contact. This happens when someone touches metalwork that is not meant to be live, but it has become live because of a fault. A common example is the metal case of an appliance when the insulation has failed. Why is this important? Because electric shock can seriously injure or kill. To manage this risk, the standard brings in a whole range of protective measures such as insulation, barriers, earthing, RCD protection, and automatic disconnection of supply. All of these are there to prevent electric shock, or at least reduce the risk as much as possible. B. Excessive temperatures. The second danger is excessive temperature. Electricity can create heat, and if that heat is not controlled, it can burn people, damage equipment, or start a fire. Typical causes of excessive heat include cables overheating, loose terminations arcing, overloaded circuits, and luminaires or appliances getting too hot for the materials around them. Anyone designing or installing an electrical installation needs to make sure that people, materials, and equipment are protected from hot surfaces, hot components, arcs or sparks, and heat buildup in general. C. Explosive atmospheres. The third danger is explosive atmospheres. Some locations have flammable gas, vapor, or dust in the air. In these places, even a small spark can ignite the atmosphere and cause an explosion. Examples include fuel storage areas, grain silos, spray painting booths, and certain industrial environments. In these locations, the electrical equipment must be specially designed, selected, and installed so it does not ignite the surrounding atmosphere. Section 1.5 Fundamental Principles. Clause 1.5.2 Control and Isolation. Now we look at control and isolation. Every installation must allow the circuits to be controlled and isolated safely. Control is the everyday switching, turning things on or off in normal use. Isolation is more serious. Isolation means disconnecting a circuit or a piece of equipment from all live parts, so that someone can work on it safely. A few key ideas apply here. Depending on the system, isolation may also be required in the neutral conductor. An isolating device must never disconnect the earthing conductor or APEN conductor. Safety services, such as emergency lighting, must have their own separate control system, so that ordinary switching cannot accidentally turn the safety equipment off. The main point is this: safe isolation is essential for electricians and maintenance staff. If isolation is done incorrectly, it creates a serious electric shock hazard. Clause 1.5.3 Protection against electric shock. Clause 1.5.3.1 Scope. This clause explains what the standard expects for electric shock protection. Both types of shock must be prevented. Direct contact shock happens when someone touches parts that are live in normal service. Indirect contact shock happens when someone touches metalwork that is not meant to be live, but it becomes live because a fault has occurred. To meet this requirement, live parts must not be accessible in normal use, and exposed metal parts must not become live in normal operation or under a single fault. Clause 1.5.3.2 Methods of protection. The standard uses two layers of protection. A. Basic protection. Basic protection prevents contact with live parts during normal service. This is achieved through insulation on live parts, barriers, enclosures, or placing live parts out of easy reach. These measures are designed to prevent accidental contact under normal conditions. B. Fault protection. Fault protection deals with indirect contact, where a fault makes exposed metal become live. The main protective methods are earthing, bonding, and automatic disconnection of supply using devices such as fuses, MCBs, and RCDS. The aim is that if a fault occurs, the supply will disconnect quickly enough to prevent harm. Enhanced protection. Enhanced protection is a special approach used only in specific situations. Here, one protective method on its own provides protection both in normal use and under a single fault, but it must meet strict conditions in ASNZS 3000. Examples include SELV systems, such as 12-volt pull lights or shaver outlets, where the voltage is low enough to be safe in normal use and still safe if a fault occurs. Another example is double-insulated equipment, such as Class 2 tools or chargers. Even if one layer of insulation fails, the second layer maintains safety. PELV control circuits are another example, using low voltage that remains within safe limits even when referenced to earth. These methods give protection in normal operating conditions and during a single fault, which is why they are considered enhanced protection. Clause 1.5.4 Basic protection, protection against direct contact. Clause 1.5.4.1 General. This clause is still about protecting people from touching live parts during normal operation. Basic protection is all about preventing direct contact under normal conditions. Clause 1.5.4.2 Methods. Basic protection can be provided by several methods. These include insulation of live parts, barriers or enclosures, obstacles, and placing live parts outside arm's reach. One very important point is that RCD devices on their own do not count as basic protection. An RCD is an additional layer, not the primary method of protection. Clause 1.5.4.3 Protection by insulation. When insulation is used as the basic protection, it must fully cover the live parts. The insulation must be able to withstand mechanical stress, heat, chemicals, and normal electrical stress. Clause 1.5.4.4 Protection by barriers or enclosures. When barriers or enclosures provide the protection, they must give at least IP210 or 1pxxb in general locations. On horizontal surfaces that can easily be touched, the requirement is IP4X. These ratings prevent fingers or objects reaching live parts by accident. Clause 1.5.5 Fault protection, protection against indirect contact. Clause 1.5.5.1 General. This part deals with protection when a fault has caused exposed metal parts to become live. The requirement is that people must not be exposed to dangerous voltages if that happens. Throughout the installation, one or more suitable fault protection methods must be used, taking into account the external conditions in that particular location. Clause 1.5.5.2 Methods of protection. Fault protection may be provided by one or more of the following methods. A. Automatic disconnection of supply. The supply must disconnect automatically if a fault creates a dangerous touch voltage. The disconnection time must be fast enough to prevent harmful shock. The detailed limits are explained later in Clause 1.5.5.3. B. Limiting the touch current using Class 2 equipment or equivalent insulation. Here, we rely on double insulated or Class 2 equipment, or equipment with equivalent insulation. This prevents fault current passing through a person. More details are given in Clause 1.5.5.4. C. Protection by electrical separation. Some circuits can be made safe by being electrically separated from other circuits and from earth. This is explained further in Clause 1.5.5.5, with extra guidance in Clause 7.4. D. Limitation of fault current. In some cases, the fault current can be limited so that it remains below the level that would cause a dangerous shock. This method is less common in everyday installations. The standard points out that the most common method used in practice is automatic disconnection of supply. Clause 1.5.5.3 Protection by automatic disconnection of supply. A. General. Automatic disconnection aims to limit dangerous touch voltage on exposed metalwork. This is done in two steps. First, all exposed conductive parts must be connected to the protective earthing system. Second, a protective device must disconnect the supply quickly when a fault occurs. This method may also be needed for overcurrent protection under Clause 1.5.9 and Clause 2.5. The standard also points us to other areas for more detail. Clause 5.6 covers equipotential bonding. Section 2 explains the detailed disconnection requirements. Appendix B provides guidance on earth fault loop impedance. B. Touch voltage limits. If a fault occurs between a live part and exposed metal, and the touch voltage rises above 50 volts AC, or 120 volts ripple-free DC, then the protective device must disconnect the circuit within the required time. In certain special locations covered in Section 6 and Section 7, stricter touch voltage limits may apply. C. Earthing system impedance, earth fault loop impedance. The characteristics of the earthing system and the protective devices must ensure that disconnection happens within the required time, even when the fault occurs at the furthest point in the circuit. If the earth fault loop impedance is too high, the fuse or circuit breaker may not operate fast enough. Clause 5.7 and Appendix B provide more detail on this point. D. Disconnection times. For a 230/400 volt installation, the maximum disconnection times are as follows. 0.4 seconds for final sub-circuit supplying. Socket outlets rated up to 63 amperes. Handheld Class 1 equipment, or portable equipment that is intended to be moved by hand during use. 5 seconds for other circuits, such as submains, and circuits supplying fixed or stationary equipment. The standard notes that these times can vary when different voltages or installation conditions apply. E. Supplementary equipotential bonding. Supplementary bonding may be used to help reduce earth fault loop impedance so that the protective device disconnects within the required time. This involves bonding exposed conductive parts together and bonding them to the earthing system. It does not replace a CD protection or other safety devices. It simply helps ensure that those devices operate correctly. Clause 1.5.5.4 Protection by Class 2 equipment or equivalent insulation. A. General. Protection can also be achieved by using equipment that has double or reinforced insulation. This includes Class 2 equipment, equipment with basic insulation plus supplementary insulation, switchgear constructed to ASNZS 3439.1, or equipment where supplementary insulation is added over the basic insulation. If options 3 or 4 are used, the overall level of safety must still be equivalent to Class 2 insulation. The standard also points out that paints, varnishes, and similar surface coatings do not count as insulation. If there is a chance that double insulation could be damaged, then extra precautions may be needed. B. Constructional requirements. Where the protection relies on a covering or an enclosure, a few rules apply. Screws or bolts made of insulating material must not be used if replacing them with metal would reduce the insulation level. If a lid or door can be opened with a tool or a key, then any live parts behind it must still be protected by an insulating barrier that gives at least IPXXB or IP2X. That barrier must only be removable with a tool. Clause 1.5.5.5 Protection by electrical separation. Electrical separation is normally applied to individual circuits. The idea is to prevent electric shock by making sure the live parts of the separated circuit are not connected to earth, and the exposed metal parts belonging to that circuit are not connected to earth and not connected to exposed metalwork of any other circuit. Usually, a separated circuit supplies only one item of equipment, unless the extra conditions in Clause 7.4 are met. Clause 1.5.6 Additional protection by the use of RCD devices. RCD devices are used as extra protective measures. They are not intended to replace basic protection. Clause 1.5.6.1 Basic protection. On their own, RCD devices do not provide basic protection during normal operation. However, they can be added on top of the basic methods to give an additional level of safety. Clause 1.5.6.2 Fault protection. RCD devices are recognized as a method of fault protection. They operate by disconnecting the supply when the earth leakage current reaches a dangerous level. Clause 1.5.6.3 Where required. When RCD devices are used for fault protection, they must be able to disconnect the part of the circuit they protect at the set leakage value. The standard requires RCD protection as additional protection in places such as socket outlet circuits, lighting points, and handheld equipment, in certain wiring systems, in electric heating cables, in equipment used in damp locations, and in special installations listed in other reference standards. The key message is this. RCD devices cannot be the only protection under normal conditions, but they are essential in higher risk areas or where the standard specifically requires them. Clause 1.5.7 Basic and fault protection using extra low voltage, SELV and PELV. SELV and PELV systems can provide both basic protection and fault protection, but only when certain conditions are met. The first condition is the voltage limit. The system must be arranged so that it cannot exceed extra low voltage levels of 50 volts AC, or 120 volts ripple-free DC. The second condition is separation from other circuits. These circuits must be kept separate, both electrically and physically, from each other and from any higher voltage circuits. For SELV systems, the live parts must not be connected to earth or to any protective earthing system used by other circuits. For PELV systems, if a person can touch the live parts, the voltage must always remain within the limits allowed for that particular environment. In short, SELV and PELV systems stay safe because they operate at very low voltage and are kept carefully separated from higher voltage systems and, where required, from earth. Clause 1.5.8 Protection against thermal effects in normal service. This clause returns to heat and fire issues during normal operation. The installation must be arranged so that, during normal use, electrical equipment does not ignite flammable materials because of high temperature or arcing, and does not harm people or animals through heat or sparks. If equipment normally runs warm or hot, it must have enough ventilation so that temperatures remain within safe limits. Designers must also consider how increased temperature could affect nearby equipment or materials. The summary is simple. During normal use, the installation must not become a fire risk and any heat produced must be kept under control. Clause 1.5.8 Protection against thermal effects in normal service. This clause returns to heat and fire issues during normal operation. The installation must be arranged so that, during normal use, electrical equipment does not ignite flammable materials because of high temperature or arcing, and does not harm people or animals through heat or sparks. If equipment normally runs warm or hot, it must have enough ventilation so that temperatures remain within safe limits. Designers must also consider how increased temperature could affect nearby equipment or materials. The summary is simple: during normal use, the installation must not become a fire risk and any heat produced must be kept under control. Clause 1.5.9 Protection against overcurrent. Overcurrent can create high temperatures and mechanical stress in conductors. Protection against overcurrent can be achieved in two main ways. One method is automatic disconnection, where the supply is cut off before the current becomes dangerous. The second method is limiting the maximum current, so it cannot exceed a safe value or duration. In everyday language, fuses and circuit breakers must stop the installation from carrying more current than it is designed to handle. Clause 1.5.10 Protection against earth fault currents. Any earthing conductor, or any part of the installation that is expected to carry earth fault current, must be sized and installed so that it can safely carry that current without overheating. In simple terms, the earthing conductors must be strong enough to handle the worst realistic earth fault. The conductor must not overheat, melt, or become damaged when a high fault current flows. This clause makes sure the earthing system remains reliable during a fault, so protective devices can operate correctly and disconnect the supply safely. Clause 1.5.11 Protection against abnormal voltages. This clause deals with voltages that should not normally appear in the installation. The system must be protected against harmful voltages that may be caused by faults between circuits operating at different voltages, by voltages induced or appearing unexpectedly in conductors, or by harmful influence between different circuits or systems. Clause 1.5.11.2 Circuits at different voltages. Where circuits operate at different voltages, protection must be provided to prevent injury or damage if a fault occurs between them. This can be achieved by keeping the circuits well separated or by using suitable protective devices. Clause 1.5.11.3 Voltage disturbances and electromagnetic influences. This part notes that protection against overvoltages from events such as lightning or switching operations is not required under this clause itself. However, the standard does provide guidance on these matters in other sections. Clause 1.5.11.4 Voltage in unused conductors. Unused conductors can still pick up unwanted voltages. These conductors must be terminated and protected at both ends in the same manner as live conductors. Clause 1.5.11.5 Interaction between different circuits and installations. Protection is also required to prevent harmful effects caused by interaction between different electrical installations, between different circuits in the same installation, between electrical and non-electrical installations, and between the installation and the structure it occupies. The main idea is that different systems can interfere with one another, and the installation must be designed so that dangerous interaction or unexpected voltages do not occur. Clause 1.5.12 Protection against the spread of fire. This clause focuses on fire safety. The electrical installation must not start a fire or make an existing fire spread or become worse. Equipment must be selected and installed so that it does not block escape routes with flames, smoke, or hot gases, does not add to a fire or help it spread, does not become so hot that it ignites nearby materials, and does not interfere with people trying to escape. Other parts of the standard provide more detail, including requirements for switchboard locations and fire spread control. The short message is that electrical equipment must never worsen a fire or restrict evacuation. Clause 1.5.13 Protection against injury from mechanical movement. Some electrically driven equipment includes moving parts, and these can be dangerous if not properly controlled. Protection is required wherever maintenance staff may be exposed to mechanical hazards while working on the equipment, or where the equipment may need to be stopped quickly in an emergency to remove danger. The standard requires that there must be a means to disconnect or isolate the equipment so that maintenance and emergency stopping can be carried out safely. In simple terms, if something moves, there must be a safe way to shut it down. Clause 1.5.14, Protection against external influences. This clause covers external influences, essentially, what the environment can do to the installation. The installation must be designed so that it can cope with the conditions that can reasonably be expected in the place where it is installed. These influences may include weather or water, dampness, corrosion, chemicals or salt, dust, steam or oil, temperature variations, vibration or mechanical impact, animals, plants, insects, seismic activity, explosive atmospheres, or any other influence that might reasonably affect the installation in normal service. The overall idea is simple: the installation must be built to handle the environment it lives in, whether that involves water, heat, dust, chemicals, animals, vibration, movement, or anything else that could realistically occur. Section 1.6, Design of an electrical installation. Clause 1.6.1, General. When you design an electrical installation, it must achieve 5 main objectives. First, it must protect people, animals, and property from harm. Second, it must work properly for whatever purpose it is intended to serve. Third, it must connect safely to the supply, whether that supply comes from the electricity distributor or another source, and it must remain safe during normal operation and during a fault. Fourth, it should minimize inconvenience when something goes wrong, so that one fault does not shut down the entire installation. And finally, the installation must allow safe operation, safe inspection, safe testing, and safe maintenance. In simple terms, a good installation design must be safe, must function as intended, must match the supply system, and must allow people to work on it safely later on. Clause 1.6.2, Supply characteristics. Before you size cables or choose equipment, you first need to understand the supply that the installation will connect to. The standard lists several characteristics the designer must know. The first is the nature of the current, whether the supply is AC or DC. Next, you need to know the number and type of conductors. For example, on an AC system you may have active or phase conductors, a neutral conductor, and a protective earthing conductor. On a DC system, you will have equivalent conductors for that system. You must also know the supply voltage and its tolerance. For low-voltage systems in New Zealand, the nominal value is 230/400 volts, with a tolerance of +6% and -6% in the 2007 edition of ASNZS 3000. You must also be aware of regulatory changes. From about late 2025, the allowable network voltage range under amended ESR requirements has been widened to around ±10%. So the designer must always check the current ESR rules. Those voltage and tolerance figures affect both the equipment you select and how the circuits are designed. You must also know the frequency and its tolerance, typically 50 Hz, along with the allowable variation. Another important point is the maximum current that the supply can provide. This tells you how much load the installation is permitted to draw. You also need to know the prospective short-circuit current at the point of supply. In practice, this value is usually supplied by the electricity distributor. It tells you how high a fault current the protective devices and switchgear must be able to withstand. Next, you look at the protective measures built into the supply system, for example, whether the supply uses an MEN earthing system. You must also find out any limits or conditions set by the supply authority, such as maximum demand limits, starting current limits, or power factor requirements. Lastly, you need to be aware of any limits on harmonic currents or other power quality issues. If the distributor has rules about harmonics or voltage disturbance, your design must comply with those limits. In summary, before you design the installation, you must fully understand the supply, its voltage, frequency, fault level, earthing system, and any conditions imposed by the distributor. Clause 1.6.3 Maximum demand. The next step is maximum demand. The designer must work out the maximum current the installation is likely to draw under normal use. To do this, you consider the total electrical load, how the load is distributed through the building, and how the equipment is expected to operate. Once the maximum demand is known, the consumer's mains, submains, final subcircuits, and all other relevant parts must be sized so they can carry that current safely. In simple terms, the installation must never draw more current than the supply, the cables, or the switchgear can safely handle. Clause 1.6.4 Utilization voltage. Utilization voltage is the voltage that actually arrives at the equipment. The installation must be designed so that, during normal operation, the voltage at each appliance or item of equipment is suitable for that equipment. To achieve this, the designer must consider voltage drop along the cables, the length of the cable runs, the loading on the circuits, and the supply tolerances discussed earlier. The standard refers to Clause 3.6 for the detailed voltage drop limits. It also notes that standalone systems must keep the point of supply voltage within the range given in Clause 1.6.2 subclause C during normal full load conditions. In simple terms, even when everything is switched on, the equipment must still receive a voltage that falls within its proper operating range. Clause 1.6.5 Electrical installation circuit arrangement. Finally, we look at circuit arrangement. The installation must be divided into circuits in a way that avoids danger, reduces inconvenience when a fault occurs, and allows safe operation, safe inspection, safe testing, and safe maintenance. This means you do not put everything on one circuit. Instead, you divide the installation logically so that one fault does not shut down the entire building, and so that parts of the installation can be safely isolated for maintenance. The detailed rules are given in Clause 2.3, and those requirements must be followed. In simple terms, circuits must be arranged so the installation is easy to control, easy to fault find, and safe to work on, and so that a single fault does not take everything out. Section 1.7, Selection and Installation of Electrical Equipment. Clause 1.7.1, Essential Requirement. When we choose and install electrical equipment, the standard gives one clear message. The equipment must be safe, must work properly, and must be installed the way the manufacturer intended. This means three things. First, the equipment must operate safely and reliably during everyday use. Second, it must not introduce danger, not electric shock, not fire, not overheating, and not physical injury, even when unusual conditions occur, such as an overload, a fault, or unexpected environmental conditions. And third, the manufacturer's installation instructions must be followed exactly. No shortcuts. In simple terms, choose equipment that is suitable for the job, install it correctly, and make sure it stays safe whether things go right or things go wrong. Clause 1.7.2 Installation Work Practice. To meet those safety requirements, installation work must follow good, safe practice. The standard highlights several key considerations. First, the equipment must be suitable for the environment. It must cope with the temperature, weather, mechanical forces, or any other environmental conditions where it is installed. Any built-in protection must still work after installation, and extra protection, such as an enclosure, must be added if needed. Second, the manufacturer's instructions must always be followed. Third, enough space must be provided for safe operation, inspection, testing, and maintenance. Fourth, mechanical fixings must be strong enough. Brackets, screws, and supports must hold the equipment securely and remain durable over time. Fifth, the design must consider the needs of the user and how they will operate the installation. Sixth, wiring colors must comply with the rules. Green, yellow, or green/yellow are only for earthing conductors. They must never be used for active or neutral conductors. Seventh, socket outlet polarity must be correct and must be consistent throughout the installation. And finally, Semi-enclosed rewirable fuses cannot be installed. They are not permitted. In simple terms, install equipment safely, mount it securely, wire it correctly, follow the instructions, and ensure the installation suits its environment. Clause 1.7.3 Equipment Selection. When selecting equipment, it must meet the essential safety requirements in the standard. The standard says equipment is acceptable if it meets at least one of the following pathways. 1. It complies with ASNZS 3820, the General Safety Standard for Low Voltage Equipment. 2. It complies with a relevant technical standard. This may be an Australian standard, a New Zealand standard, or a joint ASNZS standard for that specific type of equipment. If no suitable ASNZS standard exists, a recognized international or national standard from another country may be used, provided it is appropriate for the equipment and for the installation conditions in Australia or New Zealand. 3. The equipment carries the RCM mark, confirming it meets the required safety regulations. 4. In some cases, regulators may accept other recognized marks or evidence of safety. In simple terms, select equipment that complies with the correct standards or recognized safety approvals, and make sure it is appropriate for the installation. Clause 1.7.4 Damp situations. If electrical equipment is installed in a damp or wet location, the risks increase, and so do the requirements. The equipment must be selected and installed so that it operates safely around moisture, reduces the risk of electric shock in wet environments, and avoids damage that could reasonably occur due to damp conditions. In simple terms, in wet or humid areas, choose equipment designed for those conditions and install it so moisture cannot compromise safety. Section 1.8 Verification, Inspection and Testing. Before any installation is put into service, whether it is new, extended, altered, or repaired, it must be inspected and tested. This is not optional. The purpose is to confirm that the work complies with the standard. Inspection and testing must be carried out as far as practicable, meaning as thoroughly as site conditions allow. During this process, precautions must be taken to avoid danger to people and damage to equipment or property, alterations and extensions. When modifying an existing installation, you must confirm two things. 1. The new work complies with the standard. 2. The new work does not make the existing installation unsafe. In simple terms, when you add wiring or equipment, make sure you are not introducing hazards into the older part of the installation. Correct conductor connections. Verification also includes checking that all conductors are connected correctly, especially to protective devices, switching devices and control devices. This ensures that fuses, circuit breakers, RCD devices and switches will operate as intended. Reference to Section 8. Section 1.8 tells you what must be done. Section 8 provides the detailed procedures and tests, essentially, how to do it. In simple terms, Section 1.8 says test it, and Section 8 says here is how you test it. Section 1.9 Means of compliance. Section 1.9 explains the pathways that can be used to show that an installation complies with the standard. This is particularly important for special designs, alterations and additions. Clause 1.9.1 and Clause 1.9.2, Australia only. These pathways apply only in Australia and are not used in New Zealand. Clause 1.9.3, Alterations, Additions and Repairs. Whenever you alter or add to an existing installation, the new work is treated as if it were a new installation. This means the full requirements of the standard apply. If the original installation was built using a Part 1 design, the new work must not reduce its level of safety. When altering an installation, the new work must not carry currents or voltages above what the standard permits, and it must not be used in a way that is non-compliant. Repairs may use similar methods or materials to those originally installed, but only if the repaired part still meets the fundamental safety principles of Part 1. In simple terms, all new work must be safe, must comply with the standard, and must not make the existing installation unsafe. Clause 1.9.4 Compliance by specific design and installation. Sometimes an installation has unusual requirements and cannot follow the usual Part 2 methods. In these cases, the designer may create a specific design based on the principles in Part 1, but this is only allowed under strict conditions. Clause 1.9.4.1 Using a Part 1 design solution. A designer may use a Part 1 design if they can show that the installation meets the fundamental safety principles of Part 1, that the level of safety is at least equal to what would have been achieved using the normal Part 2 methods, and that all other relevant requirements of the standard are satisfied. Any portions of the installation that are not part of the special design must still comply with Part 2. In simple terms, a special design is allowed, but it must be just as safe as a standard installation. Clause 1.9.4.2 Acknowledgement by the owner. If Part 2 is not being followed, the owner or operator must formally acknowledge this departure. This ensures they understand and accept the design approach. Clause 1.9.4.3 Documentation. The designer must fully document the design. The documentation must explain why the usual Part 2 method was not used, specify the verification steps required to confirm compliance, show how Part 1 requirements are being met, include the owner's written acknowledgement, describe any special installation methods, and record the tests and inspections carried out. The documentation must be kept by the designer and also kept on site by the person responsible for the installation. In simple terms, a special design must be fully documented, and the owner must agree to it. Hi everyone, and welcome to this audiobook designed for the EWRB Electrician Regulation Exam. My name is Aria, and I work alongside Whit Roy as an electrical tutor. This audiobook explains the exam topics in simple spoken language, making it easier to understand and review anywhere, anytime. Before we get into the lesson, I want to explain what this audiobook actually is. This audiobook is not a word-for-word reading of ASNZS 3000. You must always refer to the real standard when you're doing electrical work or preparing for an assessment. What we do here is take the important ideas from the standard and rewrite them in simple spoken English. The goal is to make the rules easier to understand, easier to remember, and easier to revise, especially when you're listening on the go. So think of this audiobook as a learning guide, not a replacement for the actual standard. Alright, let's begin. Today we're beginning section 2 of ASNZS 3000. In this section we'll look at how to choose electrical equipment and how to install it so the whole system stays safe, reliable, and easy to work on. We'll talk about how circuits are arranged, how protective devices need to work together, and why isolation and switching are so important. We'll also look at RCDs, overvoltage and undervoltage protection, and the requirements for switchboards, including where they can be installed and how they must be built. Section 2 is all about making good decisions that support safety and performance in real installations. So let's get started and walk through the clauses one by one in simple spoken language. Clause 2.1.1 Application. This clause tells us that Section 2 sets the basic rules for selecting and installing all switchgear and control gear. To meet the safety requirements in Part 1, everything must follow the guidance in this section. So it sets the foundation for how we choose and use equipment throughout the entire installation. Clause 2.1.2 Selection and Installation. This clause explains what switchgear and control gear must be able to do. They must allow safe control and safe isolation of circuits so we can test, repair, or maintain equipment. They must automatically disconnect the supply during faults such as overloads, short circuits, or earth leakage problems. They must also protect equipment from unsafe voltage levels. And they must be installed in suitable locations where they are protected from damage and are easy to reach. The key idea is that equipment must not only work but must help maintain safety at all times. Clause 2.2 Arrangement of electrical installation. Clause 2.2.1 Circuits. Clause 2.2.1.1 General. This clause tells us that an installation must be divided into circuits in a sensible way. We think about how equipment operates, how much current it draws, and what needs to stay reliable. Circuits should be arranged so a fault on one part does not shut down large areas unnecessarily. Lighting, power, heating, motors, and safety services should each be placed on circuits that make sense for their function. Safety service circuits must always be kept separate from normal circuits so they stay active during emergencies. Clause 2.2.1.2 Common neutral. This clause explains when a neutral conductor may be shared between circuits. A neutral can be shared only when it is safe to do so, and when the continuity of the neutral does not depend on terminals of equipment like switches. When circuits share a neutral, the active conductors must be switched or protected together so the neutral is never left carrying current alone. The shared neutral must be clearly identified at the switchboard so anyone working on it understands the arrangement. The main idea is that shared neutrals are allowed, but only when installed safely and clearly marked. Clause 2.2.2 Maximum demand. Maximum demand is the highest likely load on the installation. We calculate or assess it so we can size mains, submains, and final circuits correctly. It can be found by calculation, by assessment, by measurement, or by using protective device settings. If actual measured demand turns out to be higher than the calculated value, then the measured value becomes the correct maximum demand. This ensures cables, switchboards, and protective devices can safely handle the load. Clause 2.2.3 Selection and installation of conductors. This short clause simply says that all conductors must be chosen and installed according to Section 3, which covers conductor sizing and installation methods. So this clause acts as a pointer to the detailed rules found later in the standard. Clause 2.2.4 Operating characteristics of equipment. Clause 2.2.4.1 General. Equipment must suit the way it will be used. If a device performs more than one function, it must meet the safety requirements for each function. Clause 2.2.4.2 Voltage. Equipment must have a voltage rating that matches the system voltage. Clause 2.2.4.3 Current. Equipment must carry the normal load current and withstand abnormal currents long enough for the protective device to operate. We think about inductive loads, heating loads, and any special characteristics. Clause 2.2.4.4 Frequency. If the frequency of the supply affects how a device works, then the device must be rated for the system frequency, which in New Zealand is 50 Hz. Clause 2.2.4.5 Power. Equipment must handle the maximum power it will be expected to deliver without overheating or becoming unsafe. Clause 2.2.4.6 Effects on operator or other equipment. When equipment is used normally, it must not create danger. It must not shock, burn, or interfere with other equipment. Switching operations must not cause unsafe conditions for the operator. Clause 2.3 Control of electrical installation. Clause 2.3.1 General. The installation must have devices that allow safe switching, safe operation, and safe maintenance. These devices include isolation switches, emergency shutdown switches, mechanical maintenance switches, and functional switches for normal control. If one device performs more than one of these jobs, it must meet the rules for each function. Clause 2.3.2 Common requirements. Clause 2.3.2.1 General. Every circuit must be able to be isolated from the supply. Isolation must require a deliberate action so it cannot happen by accident. We use things like padlocks, warning tags, or locked enclosures to prevent accidental operation. When equipment is supplied by more than one source, we must clearly warn people working on it so they know all sources need to be isolated. And if stored electrical energy exists, such as in capacitors, we must provide a way to safely discharge that energy. Clause 2.3.2.1.1 Alternating current systems. In AC systems, all active conductors must be isolatable. A neutral may only be switched in special situations, and when it is switched, it must open and close together with the active conductors. The neutral must never be left floating, as this can create dangerous voltage levels. Some circuits, such as fire pump controls, have special rules, but the general idea is simple: actives must be able to be isolated, and neutral switching must be safe and properly linked. Clause 2.3.2.1.2 Direct current systems. In DC systems, each pole must also be able to be isolated. There are a few exceptions, such as when one conductor is permanently connected to Earth, but the overall rule is that DC circuits must have safe, clear isolation. Clause 2.3.2.2 Devices for isolation. Clause 2.3.2.2.1 General. A device used for isolation must disconnect all active conductors. It must clearly show when it is open or closed, and it must not fall or snap into the closed position by accident. It must withstand the electrical stresses expected in the installation. If the isolator cannot break load current, we must use interlocking, warnings, or other controls so it is never operated under load. The key idea is safe, reliable, deliberate isolation. Clause 2.3.2.2.2 Identification. Every isolator must be clearly identified. Anyone working on the installation must immediately know what the device isolates. Labels or symbols may be used as long as they are clear and permanent. Clause 2.3.3 Main switches. This clause explains why we need main switches. A main switch allows a person to shut off power quickly and safely, including emergency services if they arrive during a fire or accident. It also helps keep important safety services running when other parts of the installation are isolated. The key idea is that the main switch is the primary control point for the whole installation. Clause 2.3.3.1 General. This clause tells us that every electrical installation must have a main switch located on the main switchboard. If the installation has more than one supply, such as a generator or solar system, each supply must have its own main switch. The main switch must be placed where it can control the whole installation or the part it is meant to protect. Alternative supplies may sometimes be connected in different locations, but only when allowed by other standards. Clause 2.3.3.2 Number of main switches. This clause explains that we should only install the number of main switches that are needed for safe and effective operation. In a normal home, you usually need only one main switch for the whole installation. If a building has separate metering for different parts, or different tenants, each part must have its own main switch so it can be isolated without affecting others. The aim is to keep things simple but still provide safe control where it is needed. Clause 2.3.3.3 Location. This clause is about where we place main switches. Main switches must be easy to reach, and the switching handle must not be higher than about 2 meters so most people can operate it safely. Main switches must not be located in places where someone could operate them accidentally or where access is restricted for safety reasons, such as public land or special equipment spaces. If an installation has more than one occupier, each occupier must have access to a switch that isolates only their part of the installation. Clause 2.3.3.4 Identification. This clause explains that every main switch must be clearly marked. It should have permanent wording saying main switch, and it must stand out from other switches so that anyone, even in an emergency, can find it quickly. If there are multiple main switches, each one must indicate which installation or which supply it controls. If operating the main switch also switches an alternative supply, such as a generator, this must be clearly shown. The whole purpose is to avoid confusion and allow fast, confident operation. Clause 2.3.3.5 Remote control. Sometimes a main switch is operated from a remote location. If so, the remote controls must be clearly marked and located so the operator knows exactly what they are switching. When a remote control system is used, it must be designed so the main switch cannot close by accident because of a fault in the wiring or controls. If closing the main switch is allowed remotely, the device must have a reliable way to keep the switch locked in the open position when needed. The general idea is that remote main switching must be as safe as operating the switch directly. Clause 2.3.4 Additional isolating switches. This clause introduces the idea that, aside from the main switch, some parts of the installation may need extra isolating switches. These additional switches are required when parts of the installation must be isolated independently for safety, for maintenance, or because of the way the building is arranged. The detailed requirements follow in the subclauses. Clause 2.3.4.1 Electrical installation in an outbuilding. This clause explains that an outbuilding can be treated as a separate electrical installation. If the outbuilding has a maximum demand of around 100 amps per phase, or if it has its own switchboard, then it must be treated separately. A main or isolating switch must be installed on the switchboard inside the outbuilding, and it must be able to isolate all supply to that outbuilding. If the outbuilding has more than one submain supplying it, each submain must have its own isolating switch. These switches do not have to be beside each other, but clear permanent notices must show where each switch is located. This prevents a person from thinking they have isolated the building when another supply is still live. Clause 2.3.4.2 Submains and final subcircuits greater than 100 amps. Any submain or final subcircuit with a rating above 100 amps per phase must have its own isolating switch at the switchboard where the circuit originates. This ensures safe control and safe maintenance of high current circuits, which carry more risk if left energized. Clause 2.3.4.3 Alternative supply. When an installation has an alternative supply, such as a generator or inverter, an isolating switch must be provided either at the point where that supply enters the installation or on the relevant switchboard. The isolating switch must be clearly marked to show which circuits the alternative supply covers. If the alternative supply can automatically energize part of the installation, the switch must also indicate clearly what will happen when it operates. This prevents confusion and accidental energizing during maintenance. Clause 2.3.4.4 Identification. All isolating switches in this clause must be clearly and permanently identified so anyone can see exactly what they isolate. If the control for an isolator must be placed away from the switchboard, then a clear warning notice must be installed, describing the operation of the isolator and the circuits it affects. The goal is to prevent a situation where someone misunderstands how the isolation works. Clause 2.3.4.5 Appliances and accessories. Many appliances and accessories require their own isolation or switching. These include water heaters, ovens, motors, room heaters, air conditioners, and safety services. The detailed requirements are found in sections 4 and 7. The main ideas: whenever an appliance might need service or might create danger if accidentally energized, it must have a way to isolate it safely and locally. Clause 2.3.5 Emergency switching including emergency stopping. This clause introduces the idea of emergency switching. Emergency switching is used when we need to quickly remove danger by stopping electricity from flowing. It is not about routine isolation or maintenance, it is specifically for unexpected danger, sudden risk, or unsafe operating conditions. Clause 2.3.5.1 General. This clause tells us that every electrical installation must have a way to perform emergency switching on any part of the installation where electrical power could create an unexpected danger. Emergency switching must be able to stop the supply fast enough to remove the hazard. This can include stopping machines, stopping motors, or cutting power to equipment that could harm a person. Clause 2.3.5.2 Emergency switching devices. This clause explains what equipment can be used for emergency switching. An emergency switch can be a single switching device that interrupts the incoming supply, or a combination of devices that work together so one single action removes power from the dangerous part of the installation. The device must be able to break the full load current of the equipment. It must also be manually operated, clearly marked, and must reliably stay in the off or stop position until reset manually. The device must not re-energize automatically. Power must only return once a person intentionally restores it by operating the switch or control. This prevents machinery from restarting suddenly and injuring someone. Clause 2.3.5.3 Installation. This clause explains how emergency switching devices must be installed. The device must be placed where it is easy to reach and easy to see when danger occurs. Anyone nearby must be able to operate it quickly. Emergency switches must be clearly marked, easy to understand, and located at a position where a person can use them without exposing themselves to extra danger. A socket outlet must not be used as an emergency switch, unless the equipment is supplied only through that socket and the switch on the socket acts as the emergency device. Clause 2.3.5.4 Identification. This clause tells us how emergency devices must be marked. Any switch used for emergency stopping must be clearly marked or colored so that it can be identified straight away. Push buttons or handles should normally be colored red with a contrasting background. The goal is that anyone, even someone not familiar with the equipment, can immediately tell which switch will stop the danger. If a remote lanyard or chain is used, such as above a conveyor, it does not need to be colored red. Clause 2.3.6 Shutting down for mechanical maintenance. This clause introduces the requirement for equipment to be safely shut down when mechanical maintenance work is needed. Mechanical maintenance can involve physical injury risks, such as moving machinery, heat, rotating parts, hydraulic pressure, or unexpected movement. To protect workers, electrical supply must be able to be disconnected safely. Clause 2.3.6.1 General. This clause explains the general rule. A safe means of disconnecting electrical supply must be available whenever mechanical maintenance is carried out on electrically powered equipment. Many machines, like cranes, elevators, conveyors, or pumps, need clear isolation because mechanical hazards may continue even after electrical power is removed. For this reason, the means of shutting down must be secure, reliable, and capable of being locked or secured in the open position if required. Some equipment powered by hydraulic or pneumatic systems may need additional precautions, because removing electrical power alone may not remove the hazard. Clause 2.3.6.2 Devices for shutting down. This clause details the requirements for the devices used for shutting down equipment during mechanical maintenance. The device must be manually operated, clearly show that it is in the off position, be designed to prevent accidental closure caused by impact, vibration, or other disturbance. This ensures the equipment cannot restart unexpectedly while someone is working on it. Clause 2.3.6.3 Installation. Here the standard explains how the shutting down device must be installed. It must be inserted into the main circuit of the equipment, and if it is a switch, it must be capable of interrupting the full load current of that equipment. If the machine uses a control system where stopping the control circuit alone removes the hazard, the standard allows this, but only when suitable safeguards are in place. A remote device may be used for shutting down, provided it can be locked or secured in the open position and prevent accidental operation. Clause 2.3.6.4 Identification. This clause requires all shutting down devices for mechanical maintenance to be clearly marked and easy to identify. Anyone performing maintenance must be able to find the device quickly and confirm that it controls the correct part of the installation. Clause 2.3.7 Functional control switching. This clause deals with switching that is used for normal operation of equipment. This is not about safety, and not about emergency shutdown. Functional switching is simply the switching we use every day to turn equipment on and off during normal use. Clause 2.3.7.1 General. Functional switching is used when we need to control equipment in the normal course of operation. For example, turning lights on or off, controlling motors, controlling appliances, or switching different functions of machinery. A functional switching device must be provided for each part of a circuit or each piece of equipment that needs to be controlled separately from other parts of the installation. One functional switch may control several items at the same time, if they are meant to operate together. Sometimes the switching device is physically part of the equipment itself, for example, a power button on a machine. The key idea is that the device is intended for normal operating control, not for isolation or emergency stopping. Clause 2.3.7.2, Functional switching devices. This clause explains what devices can and cannot be used for functional switching. Functional switching must not be carried out by disconnectors, fuses, or links. Those devices are not designed to handle the regular switching duty that comes with everyday operation. Instead, the switching device must be suitable for the heaviest or most demanding duty that it may need to handle. This includes the type of load, how often the switch will be operated, and the electrical stresses it will face. Functional switches do not need to switch all live conductors, because they are not used for isolation. When functional switching controls equipment with a very low power factor, such as motors or fluorescent lighting, the switch may need a derating factor. This is because low power factor loads place more stress on the switching contacts. However, if a switch is specifically designed for that purpose, the derating may not be needed. The key teaching point is, functional switches must be selected for the operational duty of the load, not for isolation or safety functions. Clause 2.3.7.3, Identification. In this clause, the standard explains that functional switching devices do not need to show on or off positions. This is because their purpose is purely operational, not safety related. However, appliance switches must still show the off position so the user can clearly confirm when the appliance has been switched off. The main idea is that functional switching devices do not need formal identification markings unless other standards require it. Clause 2.3.7.4, Control circuits. This clause deals with control circuits used for switching operations. Control circuits must be designed and arranged so they do not create danger if a fault occurs. For example, a fault in a control wire must not cause machinery to start unexpectedly, stop unpredictably, or operate in a way that could cause harm. Control circuits must also be protected from faults that could cause them to malfunction or cause unintended equipment behavior. A simple way to explain this is: the control circuit must be safe, reliable, and must not allow equipment to behave in a dangerous or uncontrolled way if something goes wrong. Clause 2.4, Fault protection. This whole part of Section 2 explains how we protect people and property when a fault occurs, such as a live conductor touching exposed metalwork, or insulation failing. Fault protection is all about preventing electric shock, fire, or damage when something goes wrong in the electrical system. Clause 2.4.1, General. Here the standard explains the main methods used for fault protection. The first method is automatic disconnection of supply. This means that if a fault occurs, a protective device must disconnect power fast enough to keep touch voltages at a safe level. You'll learn more about that in the later clauses. The second method is using Class 2 equipment or equivalent insulation, which means equipment that does not rely on earthing for safety. The third method is electrical separation, which is used in special situations to limit the risk of shock by isolating a circuit from earth. This clause reminds us that the detailed rules for automatic disconnection are found in clauses 2.4.2, 2.4.3, 2.5, and 2.6. Clause 2.4.2, Protection by automatic disconnection of supply. This clause explains what automatic disconnection is trying to achieve. When a fault occurs between a live part and exposed metalwork, we want the voltage on that metalwork to rise only briefly and then quickly return to a safe level. This is done by ensuring the protective earthing system creates a fault current large enough to operate a protective device, like a circuit breaker or an RCD, which then disconnects the supply. Two things must happen. First, all exposed metal parts must be connected to a suitable earthing system. This allows the fault current to flow safely and ensures the voltage rises high enough to operate the protective device. Second, the protective device, whether an overcurrent device or an RCD, must disconnect the fault fast enough to prevent danger. The basic message is: a good earth connection plus a fast protective device equals safe fault protection. Clause 2.4.3, Types of devices. This clause lists the types of devices that can be used to provide automatic disconnection of supply. But the main idea is simple. The device must be able to disconnect power safely and must not close again automatically. Devices used include fuse links that comply with their correct standard, miniature circuit breakers, molded case circuit breakers, fixed setting RCDs, other protective devices that do not have an automatic reclosing function. Semi-enclosed rewirable fuses are not allowed for this purpose. The key requirement is that the protective device must operate correctly on a fault and must not reconnect itself after clearing that fault. Clause 2.4.4 Auto Reclose Devices. This clause deals with devices that can automatically reclose after a fault, such as some circuit breakers used in other parts of the industry. In normal electrical installations, auto-reclose devices are not generally suitable for fault protection unless very specific safety conditions are met. For an auto-reclose device to be allowed, the following conditions must all be satisfied. Condition A. The device cannot be used to meet basic shock protection requirements. Condition B. After someone manually switches the device off, the automatic reclose must not be able to operate. This prevents accidental re-energizing during work. Condition C. A clear warning notice must be present, telling users that the auto-reclose must be disabled before doing any work, and reminding them to follow isolation requirements. Condition D. There must be a time delay before the first automatic reclose, often several minutes, to reduce the risk of an immediate reclosing on a persistent fault. Condition E. The number of reclosing attempts must be limited. Some devices are allowed to skip condition A if they can automatically test the insulation before reclosing. This ensures the circuit is still safe before power returns. The overall lesson here is this. Auto-reclose devices are only permitted when they have built-in safeguards to prevent unexpected energizing that could harm a person working on the system. Clause 2.5. Protection against overcurrent. This part of the standard deals with protecting conductors and equipment when too much current flows. Too much current can be caused by an overload or by a short circuit. If we do not control overcurrent, conductors may overheat, insulation may fail, and equipment may be damaged or catch fire. Clause 2.5.1 General. This clause explains the overall purpose of overcurrent protection. All active conductors must be protected by devices that automatically disconnect the supply whenever current rises above a safe limit. The idea is to disconnect the circuit before the excessive current causes injury or damage. A neutral conductor must never contain a fuse, because disconnecting the neutral alone can create dangerous situations. If a device switches the neutral, it must meet the rules for switching all supply conductors. Protection against overcurrent must cover two conditions. First, protection against overload current, when a circuit carries more current than it is designed for over a period of time. Second, protection against short-circuit current, when a fault causes extremely high current to flow suddenly. These two forms of protection must work together and must coordinate correctly so that the right device operates at the right time. Clause 2.5.1.1 Consumers' Mains. This clause explains how overcurrent protection applies to consumers' mains, the conductors supplying a building from the point of supply. There are several ways the overcurrent protection for consumers' mains may be arranged. Option A is to provide both short-circuit protection and overload protection at the origin of the consumer's mains. Option B is to provide short-circuit protection at the origin of the mains, and provide overload protection later at the main switchboard. Option C allows cases where overload protection at the main switchboard is considered enough, when the mains are installed in a way that limits the risk of overtemperature. In this case, short-circuit protection may be supplied by equipment at the switchboard or by a service protective device. The key teaching point is that consumers' mains must always have effective short-circuit protection, and overload protection must be provided either at the origin or at the main switchboard, depending on the installation method. Consumers' mains that feed circuits already individually protected against overload are considered to have overload protection, as long as the combined ratings of those downstream devices do not exceed the current carrying capacity of the mains. Clause 2.5.1.2, Submains and Final Subcircuits. This clause explains that every submain and final subcircuit must have overcurrent protection at the point where the conductor size reduces or at the point where the circuit begins. The protective device must protect the conductor against both overload current and short-circuit current. There are a few exceptions. Overcurrent protection must not be installed where opening the circuit could create a greater hazard, for example, in some safety-critical circuits. Overcurrent protection may be placed at another location, as allowed in later clauses. In some situations, the device may be omitted if other parts of the installation already provide equivalent protection. In simple terms, every cable must be protected where it starts or where it becomes smaller, unless a special rule says otherwise. Clause 2.5.1.3, Omission of protective device for safety reasons. This clause explains when a protective device may not be installed. If opening a circuit unexpectedly could create a dangerous situation, then overcurrent protection may be intentionally omitted. This applies to certain safety systems, lifting magnets, emergency supplies, or control circuits that must never lose power suddenly. In these cases, other safeguards, such as alarms or supervision, may be required to manage risks without relying on overcurrent protection. The main idea is, if disconnecting the circuit is more dangerous than leaving it energized, then we do not use a protective device that can open automatically. Clause 2.5.2, Devices for protection against both overload and short-circuit currents. This clause describes devices that can provide full overcurrent protection. A protective device must be able to break any overload or short-circuit current that might occur at its location. This includes very high prospective fault currents. If a device cannot break the full fault current, it may still be used, but only if another device is installed in series to provide the required breaking capacity. This is sometimes called backup protection. The device must comply with the requirements of the later clauses 2.5.3 and 2.5.4. Suitable protective devices include circuit breakers with both overload and short-circuit protection, fuse switch combinations, high rupturing capacity fuses, circuit breakers used together with fuses. Semi-enclosed rewirable fuses cannot be used for full fault protection. The key learning point here is, the protective device must safely interrupt the worst-case fault current that could appear at that point in the installation. Clause 2.5.3, Protection against overload current. This clause explains how we protect conductors and equipment from overload, which means current that is too high for too long, but not necessarily caused by a fault. Overload currents can overheat cables and damage insulation if they are not controlled. Clause 2.5.3.1, Coordination between conductors and protective devices. This clause tells us that the protective device and the conductor must be matched correctly. A conductor has a certain current carrying capacity, called IZ. The protective device has a rated current, IN, and the circuit is designed for a certain current IB. To prevent damage, IB must be less than or equal to IN, and IN must be less than or equal to IZ. This simply means design current less than or equal to fuse or breaker rating less than or equal to cable capacity. The device must also operate in time to protect the cable when an overload happens. Circuit breakers and fuses have different operating curves, but the goal is the same: prevent cable overheating. For fuses, the rating is usually reduced to ensure the cable is still protected. For example, a fuse is often chosen at not more than 90% of the cable's capacity. The big idea is, the cable must always be able to safely carry whatever current the protective device allows. Clause 2.5.3.2, Position of overload protective device. This clause says the overload protective device must normally be installed at the point where the circuit begins, or where the cable size reduces. This prevents a long length of cable from being unprotected. There are exceptions covered in later clauses, but the general rule is simple. Protect the cable at the start of the run. Clause 2.5.3.3, Alternative position of overload protective device. This clause explains when the overload device may be installed somewhere other than the start of the cable. This is allowed when the cable does not supply branch circuits or socket outlets before reaching the protective device, or the cable only supplies circuits that already have overload protection, and the total downstream ratings do not exceed the cable's capacity. This arrangement is common inside switchboards or bizways, where the layout makes it safe to place the protective device further along the cable. The key idea: you can move the overload protection, but only if the cable is not placed at risk in the unprotected section. Clause 2.5.3.4 Omission of overload protective device. In some situations, overload protection may be intentionally left out. This is only allowed when: first, opening the circuit unexpectedly could create a more dangerous situation than the overload itself. This applies to some safety systems and specialized industrial equipment. Second, the conductor must not be in a location where fire risk or explosion risk is high. Third, the equipment supplied must not be capable of causing overload, for example, some heating appliances or transformers with known characteristics. Fourth, the conductor must not supply branch circuits or socket outlets before reaching a device that does provide protection. The big message here is: overload protection can be omitted only when the installation design makes overloads impossible or when disconnection would be unsafe. Clause 2.5.4 Protection against short-circuit current. This clause deals with very high fault currents caused by short circuits. Short circuits can reach thousands of amps and must be cleared extremely quickly to prevent fire or severe damage. Short circuit protection must take into account all possible fault paths between conductors of the same circuit. Clause 2.5.4.1 Determination of prospective short circuit current. Before choosing protective devices, the installer must know the highest short circuit current that may occur at each point in the installation. This can be calculated or measured. Knowing this value ensures that circuit breakers or fuses are rated to interrupt the maximum possible fault current safely. A device with too low a breaking capacity can explode or fail dangerously. Clause 2.5.4.2 Position of devices for short circuit protection. Short circuit protection must usually be placed at the point where the circuit begins or where the cable size reduces, similar to overload protection. This ensures no section of cable is exposed to the risk of a high fault current without protection. There are exceptions, covered in the next subclauses. Clause 2.5.4.3 Alternative position of short circuit protective device. This clause explains when short circuit protection can be moved from the normal position. Clause 2.5.4.3.1 Condition 1. A protective device may be installed later in the circuit if the unprotected cable is not longer than about 3 meters. The cable is installed so that mechanical damage is unlikely, and it is located where fire or shock risk is very low. This is often used inside switchboards or between closely located enclosures. Clause 2.5.4.3.2 Condition 2. The protective device may also be installed on the supply side of a reduction in cable size if the device still protects the smaller conductor, and the let-through energy of the device is low enough that the smaller cable will not be damaged. This requires coordinating the characteristics of the protective device with the cable. The big idea: short, safe cable sections may be left temporarily unprotected, but only under tightly controlled conditions. Clause 2.5.4.4 Omission of devices for short-circuit protection. This clause lists cases where short-circuit protection may be omitted. These include circuits where disconnection would be dangerous, certain consumers' mains installed in specific ways, cables connecting generators, transformers, or batteries to switchboards, provided the wiring is arranged to minimize short-circuit risk and the protective device is located at the associated switchboard. In summary, short-circuit protection may be omitted only when the wiring method itself keeps the risk extremely low. Clause 2.5.4.5 Characteristics of short-circuit protective devices. This final clause describes what a short-circuit protective device must be able to do. The device must have a breaking capacity that is equal to or greater than the fault current at the point where it is installed. If a device with a lower rating is used, it must be backed up by another device on the supply side that limits the energy to a safe level. The protective device must also operate fast enough to keep the cable temperature below its maximum safe limit. This prevents insulation damage. In simple terms, short-circuit devices must interrupt the fault safely and quickly without letting the cable overheat. Clause 2.5.5 Protection against switchboard internal arcing fault currents. This clause deals with arcing faults that happen inside a switchboard. An arcing fault is when electricity jumps through the air between conductors or metalwork, creating extremely high heat and pressure. These faults are dangerous, and heavy current switchboards must be designed to reduce the chance of an arc starting, and to reduce the damage if one does occur. A heavy current switchboard means the supply to the switchboard is 800 amps or more per phase. The rule is that the supply conductors, right up to the line side of the protective device, must be arranged so that the chance of an arcing fault is reduced, usually by insulation or by separation. Then the switchboard itself must comply with one of the following. First option, clause 2.5.5.2, reduce the chance of the arc starting. Second option, clause 2.5.5.3, if an arc does start, limit the harmful effects as much as possible. Third option, use both ideas together, provide internal separation as required in clause 2.5.5.2, and also limit the harmful effects under clause 2.5.5.3. Clause 2.5.5.1 General. This clause explains the overall intention. During normal operation or during maintenance, the switchboard must have features that reduce the chance of an arcing fault starting. It also reminds us that internal separation is not always about preventing contact with live bare bus bars. For example, an enclosure rated IP2X can still use bare bus bars inside, because the protection prevents people from touching them. Clause 2.5.5.2 Reduction of the probability of the initiation of a switchboard internal arcing fault. This clause explains how separation inside the switchboard reduces the chance of an arc starting. Heavy current switchboards must have internal separation to at least the level described in the switchboard standards. This separation applies between bus bars and functional units from each other, terminals for external conductors, and in some cases, a safety service section. The general idea is that by physically separating parts, a fault in one part is less likely to spread or initiate an arc elsewhere. Clause 2.5.5.3 Limitation of the harmful effects of a switchboard internal arcing fault. If an arc does start, protective devices must try to minimize the damage. The standard assumes that internal arcing fault current will usually be between 30% and 60% of the prospective short-circuit current. This is lower because the arc voltage reduces the current. Protection must operate quickly. It must pick up at a current less than 30% of the three-phase prospective current. There is also a calculation to find the maximum clearing time that still keeps damage acceptable. The calculation uses a constant K sub E, the current rating of the switchboard, and 30% of the prospective fault current. The aim is to clear the arc quickly enough so the switchboard is not destroyed. The example shows how an 800 amp switchboard with a fault of 16.67 kA leads to a required clearing time of less than 0.57 seconds. The settings of protective devices must be as low as possible while still allowing equipment like motors to start. And earth fault devices must not be set above 1200 amps. Where arc detection equipment is used, it must ignore stray light sources but must still detect real arcs. Arc detectors do not remove the need for discrimination between protective devices. Clause 2.5.6 Coordination of overload and short-circuit protective devices. This clause explains how overload protection and short-circuit protection must work together so that conductors and equipment are fully protected. There are two ways this coordination can be achieved. either by one protective device or by separate devices that work together. Clause 2.5.6.1 Protection afforded by one device. Here the standard explains that one device can provide both overload and short-circuit protection as long as it meets the overload protection rules in Clause 2.5.3 and it has a breaking capacity at least equal to the prospective short-circuit current at its installation point. If both of these conditions are met, the device is considered to protect the whole load side conductor from both overload and short-circuit. There is a note that says this may not always be true for extremely high short-circuit currents or for certain circuit breaker types, especially non-current limiting types. If there is any doubt, the characteristics of the device must be checked using Clause 2.5.4.2. Clause 2.5.6.2 Protection afforded by separate devices. Sometimes overload protection and short-circuit protection are provided by different devices. In this case, the overload device must meet Clause 2.5.3. The short-circuit device must meet Clause 2.5.4. And both devices must be coordinated so that the energy allowed through during a short circuit does not exceed what the conductor or equipment on the load side can withstand. This prevents the conductor from overheating or being damaged before the short circuit device disconnects. The coordination is normally confirmed by checking manufacturer data or by inspection under Clause 8.2.2. Clause 2.5.7 Reliability of supply. Clause 2.5.7 is all about keeping the power on as much as possible when something goes wrong. The idea is simple. When we design an electrical installation, we don't want one fault to shut down the whole place. So the installation should be divided into sensible circuits, and each circuit should have protective devices chosen and set so they work together properly. This means if a fault happens on one circuit, only that affected circuit loses supply. Everything else keeps running normally. The protective devices should be selected so they do not trip too easily, and should also be adjusted to work in the right order. The standard also reminds us that the settings of these devices must be checked during inspection. That makes sure the discrimination is correct and the supply stays reliable. Clause 2.5.7.1 General. Clause 2.5.7.1 repeats the key idea in a simple way. The installation must be arranged so supply is reliable. That reliability is achieved by dividing the wiring into suitable circuits and choosing protective devices that will operate in the right sequence. The goal is that when a protective device trips, it affects the smallest area possible. Only the faulty part goes off, and all the other parts continue supplying power. Again, the settings must be inspected to ensure the protective devices are coordinated properly. Clause 2.5.7.2 Coordination of protective devices. Clause 2.5.7.2 introduces the idea of coordinating different protective devices. When we have more than one protective device on a circuit path, they must work in the correct order. This is often called discrimination or cascading. We want the device closest to the fault to trip first. The upstream devices, the ones further back toward the supply, should not operate unless absolutely necessary. That prevents large parts of the installation from losing power due to a small fault. The overall aim is to make sure protective devices understand their job, so the right device trips at the right time, and supply to the rest of the system is maintained. Clause 2.5.7.2.1 General. Clause 2.5.7.2.1 explains the general idea of discrimination between protective devices. It tells us that discrimination is achieved when a downstream device clears the fault while the upstream device stays closed. In other words, the protective device nearest the fault trips, and everything upstream carries on supplying power normally. The clause also highlights that discrimination depends on the time and current curves of the devices. The downstream device must operate faster or at a lower current than the upstream device. That way, only the faulty section is disconnected. Clause 2.5.7.2.2 Safety Service Circuit Discrimination. Clause 2.5.7.2.2 focuses on safety services. These are installations that must keep working during an emergency, such as alarms, evacuation systems, and some lighting. For these circuits, discrimination must ensure that a fault on a normal circuit will not interrupt the safety service. Likewise, a fault on the safety service circuit must not cause loss of supply to other safety circuits. The design must protect the function of these essential systems, even during faults. Clause 2.5.7.3, General Supply Circuit Discrimination. Clause 2.5.7.3 deals with normal electrical circuits. Just like the earlier clauses, the goal is to minimize loss of supply. Protective devices must be arranged so that downstream devices trip before upstream devices. The clause goes on to explain the different ways this discrimination can be achieved, especially when using circuit breakers or fuses. The operating curves must be chosen so they do not overlap in a way that causes the wrong device to trip first. The designer must ensure the protective devices are selected and adjusted so that overload and short-circuit discrimination is maintained as much as possible. Clause 2.6, Additional protection by residual current devices. Clause 2.6 introduces the idea of extra protection using RCDs. This section explains when RCDs are needed, what types should be used, and how they should be arranged in an installation to give better protection against electric shock and fire risk. Clause 2.6.1 General. Clause 2.6.1 explains that a fixed setting RCD with a rated residual current not greater than 30 mA is recognized as providing additional protection. This is especially useful in situations where a basic fault, or careless use of equipment, could expose someone to dangerous shock. This extra protection does not replace the main protective measures in Clause 2.4. It simply adds another layer of safety. An important point in this clause is that RCDs do not protect against faults between active conductors, and they do not protect against voltages imported through the neutral of the supply system. They are designed mainly to protect people from leakage to earth. This clause also tells us that when Clause 2.6.3 requires it, the RCD must disconnect automatically when the leakage current reaches the trip value. Clause 2.6.2, Selection and Arrangement of Devices. This clause explains how to choose the right type of RCD and how to arrange them in an installation. Clause 2.6.2.1, General. Clause 2.6.2.1 sets out the basic requirements for choosing the RCD. Any RCD used for additional protection must be able to interrupt the supply when the earth leakage current exceeds the designed limit. The RCD must have a load current rating high enough for the part of the installation it protects. This means the RCD must handle the maximum load expected on that circuit, and the rating cannot be less than the rating of the overload device on the circuit. The earth or bonding conductor must not pass through the RCD's magnetic core, because that would stop the RCD from sensing the leakage current properly. RCDs must also be arranged in a way that avoids nuisance tripping. This means the normal leakage from equipment on that circuit should not be too close to the RCD's trip level. Clause 2.6.2.2, Types of RCD. Clause 2.6.2.2 explains the different RCD types used in New Zealand, and what types of leakage each device can sense. In simple spoken form, Type A RCDs respond to AC leakage and pulsating DC leakage. Type F RCDs respond to more complex leakage, including leakage from equipment with electronic speed control or frequency converters. Type B RCDs respond to almost all forms of leakage, including smooth DC and higher frequency components. These are used for specialized loads. This clause also mentions that the shape of the leakage current, the waveform, affects how the RCD operates. Selecting the correct type ensures reliable protection. Clause 2.6.2.3, Protection against initiation of fire. Clause 2.6.2.3 explains that RCDs can also help reduce the chance of electrical fires caused by insulation failure. This is not a compulsory part of the standard, but a Type S RCD with a higher rated residual current, typically 100 to 300 mA, may be used where extra fire protection is wanted. This is in addition to the requirements of Clause 2.6.3. These devices do not provide personal shock protection. Their purpose is to limit overheating of insulation and reduce fire risk. Clause 2.6.2.4 Arrangement. Clause 2.6.2.4 explains how final subcircuits must be arranged when additional RCD protection is required. The rules are simple. In any installation with more than one RCD and more than one lighting circuit, the lighting circuits must be shared between the RCDs. This avoids the whole building becoming dark if one RCD trips. In a residential installation, not more than 3 final subcircuits should be connected to a single RCD. If the home has more than one final subcircuit, then at least 2 RCDs must be installed. The aim is to reduce inconvenience and improve safety by avoiding a single point of failure. Clause 2.6.3, where additional protection is required. Clause 2.6.3 explains when RCDs must be used to give additional protection on final subcircuits. The goal is to reduce shock risk in places where people commonly plug in equipment, touch appliances, or where children may be present. Clause 2.6.3.1 Residential electric installations. Clause 2.6.3.1 tells us that a 30 mA RCD must protect certain final subcircuits in residential-type areas. These include subcircuits supplying one or more socket outlets, subcircuits supplying lighting points, subcircuits supplying directly connected handheld equipment, such as hairdryers or portable tools. These requirements apply to individual domestic homes, the residential areas of other buildings, groups of residential units that share common areas, external lighting in shared spaces around residential buildings. This clause also states that the RCD must be installed at the switchboard where that final subcircuit begins. There are some exceptions. For example, medical treatment areas used for home dialysis follow the special rules in ASNZS 3003. Some alterations or repairs may not require RCD protection if they meet the conditions in Clause 2.6.3.4. A socket outlet for a fixed cooking appliance may not need an RCD if it is in a location not normally accessed by the general public and is clearly marked for its restricted purpose. This clause aims to make sure that places where people live and move around most often have strong shock protection. Clause 2.6.3.2 Other electrical installations. This clause covers non-residential installations. It has different rules depending on the type of space. Clause 2.6.3.2.2 New Zealand. Clause 2.6.3.2.2 explains that in New Zealand, certain areas used for children must have extra protection using a 10 mA RCD. These areas include kindergartens, daycare centers for preschool children, schools for children up to around year 8. There are exceptions. For example, socket outlets mounted higher than 1.8 meters. Outlets used only for clearly marked equipment such as IT gear or cleaning equipment. Outlets in corridors, halls, gymnasiums or similar places where children are unlikely to use portable appliances. Places where other methods of protection exist, such as separated supply. Places where other standards require different RCD arrangements. Special locations in Sections 6 and 7, where different protection rules apply. This clause aims to protect younger children, who face a higher risk of electric shock. Clause 2.6.3.3 Home medical patient treatment installations. Clause 2.6.3.3 applies to homes where medical electrical equipment is used under the rules of ASNZS 3003. These installations must be supplied by a dedicated circuit, be protected by a Type A RCD rated at 10 mA, allow the patient or carer to reset the RCD if needed. The idea is to provide both safety and practicality in home healthcare environments. Clause 2.6.3.4 Alterations, additions and repairs. Clause 2.6.3.4 explains that when a switchboard's circuit protection is replaced, the new arrangement must include RCD protection for all the final subcircuits supplied from that switchboard, if required by Clause 2.6. Any new socket outlet added to an existing circuit must be protected by an RCD. There are exceptions. If a socket outlet or lighting point being replaced was not originally RCD protected, you do not need to add RCD protection just for a straight replacement. If lighting-only subcircuits are being extended, RCD protection is not required if the existing lighting subcircuit was not RCD protected. If socket outlets are added in a situation where an exception from Clause 2.6.3.1 or 2.6.3.2 applies, then RCD protection may not be required. The purpose of this clause is to make sure upgrades bring improved safety, while avoiding unnecessary work when the risk is low. Clause 2.7. Protection against overvoltage. Clause 2.7 introduces the requirements for protecting an electrical installation from dangerous overvoltage conditions. Overvoltage can damage equipment or create hazards for people and animals. Clause 2.7.1 General. Clause 2.7.1 explains that if overvoltage could cause danger, then the installation must be protected in line with clauses 2.7.2 and 2.7.3. It also highlights common causes of overvoltage, such as faults between circuits of different voltage levels, switching operations, lightning, resonance effects. Protection against overvoltage is especially important in regions with frequent lightning activity. Clause 2.7.2. Protection by insulation or separation. Clause 2.7.2 covers how insulation or physical separation can prevent dangerous overvoltage effects between parts of the installation. This includes using adequate insulation or screening for conductors, providing insulation or screening between transformer windings operating at different voltages, ensuring that if a transformer fault occurs, the protective earthing system causes the supply to disconnect. The key idea is that physical barriers or insulating materials help stop high-voltage faults from affecting low-voltage circuits. Clause 2.7.3. Protection by protective devices. Clause 2.7.3 describes how protective devices, such as surge protection devices, can be used to handle overvoltage from lightning or switching operations. Where these devices are installed, they must limit the overvoltage to a safe level below the insulation rating of the equipment, operate at voltages appropriate for normal conditions, not cause hazards to people or animals during operation. This clause also explains that the standard does not force every installation to have surge protection. Instead, Appendix F gives guidance on when surge protection may be appropriate and how it should be selected. Clause 2.8. Protection against undervoltage. Clause 2.8.1 General. This clause explains that we need protection when the supply voltage drops too low, or when the voltage disappears and then suddenly returns. Either situation can create danger to people or property. A sudden return of voltage can cause machinery to restart without warning. A low voltage can make motors struggle, stall, overheat, or fail to start at all. So if these risks are present, undervoltage protection must be installed. There is one exception. If the only risk is damage to equipment, and the owner accepts that risk, then undervoltage protection may be left out. Clause 2.8.2. Selection of protective device. The undervoltage protective device must be suitable for the type of equipment it is protecting. It must follow the rules in the relevant standards, especially for motor starting. If automatic reclosing of the device could be dangerous, it must not reclose automatically. In other words, when the voltage comes back, the equipment should not restart if that restart could harm someone. The device must disconnect quickly when the voltage drops. But if the equipment can safely tolerate a very short dip, then a brief delay is allowed. Examples of undervoltage devices include relays operating a switch or breaker, and non-latched contactors that release when voltage falls. Clause 2.9 Switchboards. Clause 2.9.1 General. Every electrical installation must have one or more switchboards. This is where the main switch and protective devices are located and controlled. There is an exception for some underground distribution systems that use special cable cabinets instead of a normal switchboard. A main switchboard must be provided for each electrical installation. This board holds the main switch, protective devices, and control equipment. Clause 2.9.2 Location of switchboards. Clause 2.9.2.1 General. Switchboards must be installed in well-ventilated places. They must be protected from moisture. They must also have enough space around them so electricians can install, test, maintain, and repair equipment safely. Clause 2.9.2.2 Accessibility and emergency exit facilities. Switchboards must be placed so that access is not blocked by walls, fittings, or furniture. There must be enough space around all sides where work may be done. People must be able to leave the switchboard area quickly in an emergency. This includes a clear working space of at least 0.6 meters in front of the switchboard, an alternative exit path if the switchboard is longer than 3 meters, or if the fault current is high, or if the installation needs 2 escape routes. Doorways must be at least 0.75 meters wide and 1.98 meters high to allow safe entry and exit. Switchroom doors must open in the direction of escape and must be able to open without a key or tool. Where a switchboard has 2 doors, those doors should be spaced well apart. If a switchboard is in a narrow space, the door must be able to be fixed in the open position so that workers are not pushed toward live parts. There is one exception. These special door and emergency exit rules do not apply to small domestic electrical installations. Clause 2.9.2.3 Location of main switchboard. The main switchboard needs to be easy for people to reach. It must be placed where someone can quickly get to it from an entrance to the building. This is because the main switchboard is the central point for controlling the installation. In places with more than one electrical installation inside the same building, the main switchboard cannot be hidden inside one tenancy or one private area. It has to be in a shared location so that it is available for everyone who needs access, including emergency services. Clause 2.9.92.4 Identification of main switchboard. The main switchboard must have a clear and permanent label that says main switchboard. If the switchboard is inside a room or an enclosure, then any door that someone must open to reach the switchboard also needs a clear label showing that the switchboard is inside. The position of the main switchboard must be identified by a sign at each entry to the building that emergency workers might use. These signs must be permanent and must stand out. The words main switchboard need to be shown in contrasting colors so they can be seen easily. There are situations where these markings are not required. If it is a single domestic home, the switchboard does not need this level of identification. If the location of the switchboard is already clearly shown on a fire indicator panel at the entrance, another sign is not needed. If the switchboard can be seen immediately when you enter the building, no extra marking is required. In New Zealand, any sign showing the location of the main switchboard must meet the New Zealand Building Code. Clause 2.9.2.5 Restricted locations. There are some places where you are not allowed to install switchboards because it is unsafe or impractical. A switchboard must not be installed higher than 1.2 meters above the ground, the floor, or a platform. This is to make sure it can be reached safely. There is an exception if access to the live parts has been arranged safely under Clause 2.9.3.1. A switchboard must not be installed near water containers or near fixed or stationary cooking appliances. Water, steam, or heat would affect the switchboard. An exception is allowed when the switchboard is enclosed with tight-fitting doors or placed in an enclosure that protects it from splashing or steam. If a switchboard is placed inside a cupboard or enclosure, the cupboard must be designed properly. The switchboard must be in its own section of the cupboard. It must be positioned at the front so a person can operate or maintain it without reaching awkwardly. The cupboard door must not push objects into the switchboard when closed. There must also be no objects in front of the switchboard that make access difficult. A switchboard must not be placed near baths or showers because of moisture and condensation risks. The same rule applies near saunas, swimming pools, or spa areas, as explained in Clause 6.3. A switchboard must not be installed inside a refrigeration room. Switchboards inside areas used for sanitizing or hosing down must have an enclosure with at least IP6X protection. Switchboards must not be installed where people need to pass during an emergency exit. Smoke from a fault inside the switchboard could block escape routes. Switchboards must not be installed in cupboard spaces that contain fire hose reels. They must also not be installed directly under automatic fire sprinkler heads unless certain protective features are provided, such as IP4X protection or splash shields. Switchboards cannot be installed in hazardous areas unless they are specifically designed for those environments in accordance with as NZS 6007 9.10.1 or as NZS 6007 9.10.2. Hazardous areas may include places with heavy bottled gas cylinders, gas tank filling points, or pressure relief discharge points for gas installations. New Zealand examples include LPG cylinder areas and natural gas system regulators. Clause 2.9.3 Construction. Clause 2.9.3.1 Access to live parts. This clause explains how a switchboard must be built so people are kept safe from live parts. Live parts must be enclosed so that basic protection is always there. The enclosure is the main safety barrier that keeps people from touching anything energized. There is one situation where live parts may be exposed, but only non-domestic electrical installations. In that case, the live parts must still be arranged so that barriers give basic protection, or the area must only be accessible to authorized people, with proper lockable access. Anytime a cover is removed and live parts become exposed, the switchboard must have clear identification so people know the risks, following the rules in as NZS 3439. Domestic switchboards do not use this exception. In homes, we never expose live parts. Clause 2.9.3.2 Suitability. Switchboards must be strong enough to handle the real-world stresses they face. They need to withstand mechanical stress, electrical stress, and thermal stress that may happen during normal service or during faults. If a switchboard is built to the as NZS 3439 series, it is considered suitable. That standard sets the performance expected. There are also extra design requirements for segregation of safety services and for protection against arcing faults, which appear in other parts of as NZS 3000. Clause 2.9.3.3 Minimum clearances and creepage distances. Bare live conductors must never be too close to other conductors or to earth. A minimum air clearance and a minimum creepage distance must always be maintained. These distances help prevent flashover. Sometimes smaller distances are allowed, but only when the equipment already complies with its own standard, or when a neutral bar or link is insulated from earth. Clause 2.9.3.4 Orientation of circuit breakers. When two or more circuit breakers are mounted in a row, they should all open in the same general direction. This makes it obvious how the device operates and reduces confusion. If the design of a breaker makes the open position very clear, different orientations may be accepted. Clause 2.9.3.5 Screw-in fuses. Where screw-in fuses are used, the connection point must be arranged so the live supply connects to the center contact of the fuse base. This reduces the risk of accidental contact with live threads when changing a fuse. Clause 2.9.4 Bars or links. Clause 2.9.4.1 General. Bars or links must be able to securely terminate conductors. Their design must follow the rules of Clause 3.7 to ensure reliable electrical connections. Clause 2.9.4.2 Tunnel-type terminals. Tunnel-type terminals use screws that clamp the conductor. Any screw that touches a conductor must be designed so it does not cut into the conductor strands. These terminals are often used for important conductors such as the incoming neutral, the main earthing conductor, the MEN link, or APEN conductor. Because these are critical conductors, the terminal must either use two screws or use one screw with a large enough diameter so the conductor is not damaged. Clause 2.9.4.3, neutral bar or link. Every switchboard must have a proper neutral bar. It must have adequate current carrying capacity and be easy to access so conductors can be connected safely. The bar must also be designed so the incoming neutral cannot be accidentally disconnected. This is important because the incoming neutral stabilizes the whole installation. There must also be separate terminals for the main neutral conductor and the neutral conductors of each outgoing circuit. Where tunnel-type terminals are used for neutrals, the earlier rules for tunnel terminals apply. In some cases, a single neutral bar may be shared across multiple devices on the board, but it must still follow the rules for safe termination and identification. Clause 2.9.4.4, marking of bars and links. Bars and links must be clearly marked as active, neutral, or earth. This helps anyone working on the switchboard quickly identify the correct connection point. When the insulation color of the connected conductors already makes the function obvious, extra marking may not be required. Clause 2.9.4.5, terminals of switchboard equipment. All terminals on the switchboard, such as for breakers, fuses, RCDs, and similar devices, must be marked so you can tell which active and which neutral belong together. The MEN connection and the main neutral conductor must also be clearly and permanently marked on the neutral bar, except where the MEN link is at the far end or the neutral bars are directly adjacent and obvious. Where the MEN is at a different location, such as a substation, the main switchboard must still be marked so anyone can identify the correct neutral point. Clause 2.9.4.6, fuses. If the marking on a fuse holder does not match the actual fuse rating, the correct rating must be clearly marked at the fuse location. This could be on the fuse base, the enclosure, or the switchboard panel. When several identical fuses are used as a group, the rating only needs to be displayed once as long as they are side by side and all have the same rating. Clause 2.9.5, equipment identification. Clause 2.9.5.1, general. Everything inside a switchboard must be clearly and permanently identified in English. This includes all equipment, switches, breakers, fuses, RCDs, and other devices. Clause 2.9.5.2, relationship of electrical equipment. The labeling must show which device controls which part of the installation. Each circuit and each protective device must be marked so there is no confusion. Clause 2.9.5.3, bars and links. Bars and links must be marked so anyone can tell whether they belong to active, neutral, or earth. If the conductor insulation already makes this obvious, extra marking may not be needed. Clause 2.9.5.4, terminals of switchboard equipment. Terminals must be marked clearly so each active conductor and its matching neutral conductor can be identified. This prevents wiring mistakes and helps with maintenance. The MEN termination and the main neutral conductor must be marked unless the layout makes it unmistakable. Clause 2.9.5.5, common neutral. When more than one circuit shares a neutral, that neutral must be permanently marked so the associated active conductors are easy to identify. Clause 2.9.5.6, fuse. If a fuse base does not clearly show the correct fuse rating, the correct rating must be added as permanent marking. This is important when fuses are grouped or when the original marking is unclear. Clause 2.9.6, wiring. Wiring inside a switchboard must be installed so it can handle heat, magnetic effects, and movement from hinged panels. Conductors must be long enough so a panel can swing open or be removed without straining the terminals. Wiring must be fixed securely so it does not pull on equipment when the panel moves and so it does not press against devices behind the panel. Clause 2.9.7, fire protective measures. Wiring around switchboards must be arranged so that if a fire starts in the switchboard, it does not spread easily. Where wiring enters a switchboard enclosure, the entry points must fit closely around the wiring so flames or smoke cannot easily pass through. In many cases, this means using close-fitting openings or fire-resistant sealants. Large openings may need sealing to stop the spread of fire. Internal conduits or wiring ducts inside the switchboard also need sealing if they could allow fire or hot gases to move inside the board. Now that brings us to the end of Section 2 of ASNZS 3000. We have walked through a very big part of the standard, from the basic ideas of protection, through switching, fault protection, overcurrent protection, RCD requirements, overvoltage, undervoltage, and finally the full set of rules for switchboards. It is a long section, but every part of it links back to one simple purpose, and that is to keep people safe and to keep installations working the way they should. If you have followed the whole section with me, you should now have a clearer picture of why each protective measure exists, what the devices are expected to do, and how an installation is arranged so that faults are managed safely. These ideas are the foundation for almost everything you will do as an electrician in New Zealand, whether you are designing, installing, testing, or fault finding. As you move on to the next sections of the standard, keep these principles in mind. Section 2 is really the heart of electrical protection, and the rest of the book builds on the thinking you have learned here. Thanks for staying with me through this whole section. When you're ready, we will continue our journey into the next section of ASNZS 3000. Hi everyone, and welcome to this audiobook designed for the EWRB Electrician Regulation Exam. My name is Aria, and I work alongside Whit Roy as an electrical tutor. This audiobook explains the exam topics in simple spoken language, making it easier to understand and review anywhere, anytime. Before we get into the lesson, I want to explain what this audiobook actually is. This audiobook is not a word-for-word reading of ASNZS 3000. You must always refer to the real standard when you're doing electrical work or preparing for an assessment. What we do here is take the important ideas from the standard and rewrite them in simple spoken English. The goal is to make the rules easier to understand, easier to remember, and easier to revise, especially when you're listening on the go. So think of this audiobook as a learning guide, not a replacement for the actual standard. Alright, let's begin. Today in this part of the lesson we are moving into Section 3 of ASNZS 3000. This section is all about the selection and installation of wiring systems. The goal is to help you understand not just what the rules say, but why they matter in real installations. Wiring systems have to deal with heat, moisture, movement, sunlight, vibration, and all kinds of everyday hazards. If we choose the wrong wiring method, or install it poorly, we can end up with faults, shocks, or fires. So in this section we slow down, take each clause one by one, and unpack the key ideas in clear and simple language. By the end of Section 3, you will have a solid understanding of how to select the right cable, how to support it, how to protect it, and how to install it in a way that stays safe for many years. Clause 3.1 General. This clause introduces the overall requirements for wiring systems in this section. It explains that the rules in Section 3 set the minimum safety standard for selecting and installing wiring systems so the installation will operate safely and reliably. Clause 3.1.1 Application. This part explains that the rules in Section 3 set out the minimum requirements for choosing and installing wiring systems. The wiring work must meet the safety principles in Part 1 of ASNZS 3000. Everything in this section guides you towards safe, reliable, and suitable wiring for any installation. Clause 3.1.2 Selection and Installation. This clause tells us that wiring systems must be chosen and fitted so they keep people safe and make the installation work properly. The wiring must stop people touching live parts, either by strong insulation or by keeping live parts out of reach. It must also carry the required current safely, keep voltage drop within limits, and meet all the normal rules for conductor size. The wiring system must stay reliable, keep good electrical continuity, and allow secure joints and terminations. It must also be supported properly so it will not pull apart or sag. The chosen wiring must suit its job, including special requirements such as fire resistance or explosion protection where needed. And finally, it must resist environmental and mechanical damage, either by being enclosed or by other suitable means. The standard also reminds us that many cable characteristics matter, such as insulation type, conductor material, bending limits, temperature ratings, and how the cable handles tension. Clause 3.2, Types of wiring systems. This clause explains that each wiring system must either follow the methods shown in Table 3.1, or provide an equal or better level of safety while still meeting the rules of Section 3. Clause 3.3, External influences. This clause introduces the general requirement that wiring systems must be able to operate safely and continue to function properly under all the environmental conditions they are likely to face. It leads into the detailed clauses that explain how to manage different types of external influences. Clause 3.3.1, General. This part explains that wiring systems must stay safe and work properly in whatever conditions they face once installed. The shape, design, and construction of the wiring system all contribute to how well it handles these external influences. The installation may also include extra protection or features that help it cope with the environment. The system must be able to protect itself against things like moisture, impact, dust, and other environmental factors. There is also a reminder that the IP classification system, in another standard, is a guide to how well equipment resists entry of water and solid objects. Clause 3.3.2.1, Ambient temperature. This clause explains that wiring must be chosen and installed so it can handle the highest and lowest temperatures found in its location. If materials are used above 60 degrees or below 0 degrees, you must follow the manufacturer's instructions. We also allow for expansion and contraction of materials as temperatures change. When current carrying capacity is taken from ASNZS 3008.1, we must use a reference ambient temperature of 30 degrees for New Zealand for cables in air. For cables buried direct in the ground or underground conduits, the reference ambient temperature for New Zealand is 15 degrees. Clause 3.3.2.2, External heat sources. This clause explains that wiring must be protected from heat coming from outside sources, including solar gain. This can be done by shielding, by keeping the wiring far enough from the heat source, by choosing cable that can handle the extra heat, by limiting the current so the cable runs cooler, or by adding insulation where needed. If the wiring is inside equipment, accessories, or luminaires, it must be suitable for the temperatures it will meet inside those items. Extra insulation may be required if the temperatures are high. Clause 3.3.2.3, Presence of water or high humidity. Wiring must be chosen and installed so that water or moisture does not cause damage. If condensation can form and become a hazard, the system must allow water to drain safely through suitable outlets. If the wiring may be exposed to wave action or similar forces, it must be protected from excess movement and mechanical stress, using the other clauses that deal with mechanical protection. Clause 3.3.2.4, Presence of solid foreign bodies. This clause says wiring must be protected so solid material like dust or debris does not enter and cause problems during installation, use, or maintenance. If large amounts of dust or other substances are present, extra steps must be taken to reduce the buildup, because too much material can affect the cable's ability to lose heat and remain safe. Clause 3.3.2.5, Presence of corrosive or polluting substances. When corrosive or polluting substances are present, any wiring exposed to these materials must be protected or made from materials that resist corrosion. Different metals that may react with each other must not be placed in contact. Materials that can damage each other, or that may break down when placed together, must be separated. Some chemicals, such as esters, ketones, ethers, and chlorinated hydrocarbons, can affect insulation materials, so we must consider this when choosing conduits, enclosures, or cable types. Clause 3.3.2.6, Impact. This clause explains that wiring systems must be chosen and installed so the risk of mechanical impact is as low as possible. The wiring must be able to cope with whatever knocks or strikes it might face. The protection can come from the strength of the wiring itself, from where it is located, or from adding mechanical protection such as covers or enclosures. Clause 3.3.2.7, Vibration. Wiring that is exposed to vibration must be suitable for it. Any vibration strong enough to damage cables, Fixings or connections means the entire wiring system must be able to withstand constant movement without failing. Everything must stay secure and reliable under those conditions. Clause 3.3.2.8 Other mechanical stresses. This clause explains that wiring must be installed so that stresses do not damage the insulation, sheathing, or connections throughout the life of the installation. Damage can come from weight, movement, bending, or pulling forces. To reduce these risks, the wiring should be supported at distances suitable for the cable's mass, fixed in place using suitable fixings, and connected with fittings that reduce strain at joints and terminations. Bending must follow the cable's minimum radius, and the cable must be free to move slightly where needed so it is not pulled tight under tension. Clause 3.3.2.9 Presence of flora. Where plants or vegetation could create a hazard, the wiring must be chosen or protected so it remains safe. This may mean using a different wiring method or adding extra protective measures. Clause 3.3.2.10 Presence of fauna. Where animals or insects could damage wiring, the wiring must be selected or protected so it remains safe. Some locations require tougher wiring systems or barriers to stop animals chewing, nesting, or interfering with cables. Clause 3.3.2.11 Solar radiation. When wiring may be exposed to direct sunlight, it must be selected so it can handle the conditions or must be shielded. Sunlight can cause heating or ultraviolet damage, so the wiring must be protected in accordance with earlier clauses dealing with heat sources. The notes explain that many sheathed cables already have ultraviolet protection, but some colors or types may still need extra shielding, and the manufacturer's advice should be followed. Clause 3.3.2.12 Hazardous areas. Where wiring is installed in places with explosive gas or explosive dust, the wiring system must meet the special rules for hazardous locations. The wiring must be chosen and installed to prevent ignition risks and must meet the requirements of Clause 7.7. Clause 3.4 Current carrying capacity. This clause introduces the rules for choosing a conductor size that can safely carry the current expected on the circuit, taking into account installation conditions and any external factors that may affect the cable's temperature. Clause 3.4.1 General. Every conductor must have a safe current carrying capacity, as defined in ASNZS 3008.1. The cable must be able to carry the expected current without overheating. When choosing the correct capacity, we must allow for external influences, including thermal insulation around the cable. In New Zealand homes, wiring must be selected with the assumption that thermal insulation in ceilings, walls and sometimes floors may be added in the future, even if it is not installed yet. The notes remind us that alternative current carrying capacity values exist in Appendix C, that building codes may require thermal insulation, and that modern cable materials may handle higher temperatures than older ones. It also explains that busbar ratings come from the manufacturer, with more detail in other standards. Clause 3.4.2 Operating temperature limits. The operating temperature of the conductor must not go above the maximum shown in Table 3.2. Most common cable types in New Zealand have normal operating temperatures of 75 degrees, although some special cables have higher limits. The notes explain that maximum temperatures may be lower in some locations, that some cable materials soften when exposed to heat, and that the temperature of flexible cords is based on a 75-degree rating. High temperatures may be allowed only if the cable is fully protected from mechanical strain and other stress. Clause 3.4.3 Conductors in parallel. Where more than one cable is run in parallel to share current, the combined current carrying capacity may be based on the sum of the individual cable ratings. However, parallel cables must meet strict conditions. Each cable must be at least 4 square millimeters. The arrangement of the cables must not restrict cooling. The load current must be shared evenly so one cable does not overheat. Equal sharing happens when cables are the same size and material, have the same length, are arranged so each cable sees the same conditions, and the positions of the phase and neutral conductors reduce the effects of mutual heating. An exception allows unequal sharing in some cases, but only if each cable is protected individually according to Part 1. Clause 3.4.4, Coordination between conductors and protective devices. This clause explains that the cable's continuous current carrying capacity must match the rating of the protective device for that circuit. This ensures the cable is never asked to carry more current than it can safely handle. For circuit breakers, the rating must not be greater than the cable's current carrying capacity. For HRC fuses, the fuse rating must not be more than 90% of the cable's current carrying capacity. This ensures the fuse will operate before the cable overheats. Clause 3.5, Conductor size. This clause introduces the minimum sizes required for conductors in different wiring systems. The aim is to make sure the conductor is large enough to carry the expected current safely and reliably. Clause 3.5.1, General. This clause explains that the nominal cross-sectional area of any conductor must not be smaller than the value shown in Table 3.3. The table lists the smallest acceptable sizes for socket outlet circuits, lighting circuits, signal circuits, bare conductors, flexible conductors, and aerial wiring. There is also an exception explaining that in some cases, smaller conductors may be used on socket outlet subcircuits if they still meet the requirements for voltage drop, current carrying capacity, and connection reliability. Clause 3.5.2, Neutral conductor. This clause describes how to select the minimum size of the neutral conductor. For a single-phase 2-wire circuit, the neutral must have a current carrying capacity at least equal to the active conductor, or large enough to carry the total current if more than one active conductor is involved. For multi-phase circuits, the neutral must be sized according to the expected neutral current. In many modern installations, harmonic currents can be significant. Some loads, such as fluorescent lighting, computers, switch mode supplies, and electronic drives, create third and higher order harmonics. These harmonics add together in the neutral conductor and can exceed the current in the active conductor. For this reason, the neutral in such installations must be sized to carry the highest load-producing harmonic current on any phase. In consumers' mains, submains, or final subcircuits, the neutral must not be smaller than the associated active conductor when multiple phases are present. The notes explain that a harmonic load above 40% of the single-phase load is regarded as substantial, and that information about harmonic currents can be found in other standards. There are also exceptions describing situations where out-of-balance currents or protected neutral arrangements allow the neutral to be sized differently, provided the neutral cannot exceed the protective capacity of the circuit. Clause 3.5.3, Earthing conductor. This clause explains that the size of an earthing conductor must be chosen in accordance with Clause 5.5.3.3. The earthing conductor must be large enough to carry any fault current safely and maintain the integrity of the earthing system. Clause 3.6, Voltage drop. This clause introduces the requirement that voltage drop in a circuit must remain within limits so that equipment receives a safe and usable voltage supply. Clause 3.6.1, General. Under normal service conditions, the voltage at the terminals of any equipment must not fall below the minimum value specified by the relevant equipment standard. If the equipment does not have its own standard, then the voltage must remain high enough that the equipment can operate safely and properly. Clause 3.6.2, Value. This clause explains that the size of each current-carrying conductor must be chosen so the voltage drop between the point of supply and the equipment does not exceed 5% of the nominal supply voltage. To calculate voltage drop, the current used may be the connected load, the maximum demand of the circuit, or the current rating of the protective device. Several exceptions apply. For final subcircuits with evenly distributed loads, only half of the protective device rating may be used in the calculation. High voltage and extra low voltage circuits are not included in this rule. When the transformer supplying the premises is dedicated to that installation, the allowable voltage drop may be increased to 7%. For standalone power systems, the combined voltage effects from the source and the installation must not cause the equipment to operate at an unsafe low voltage, and in these cases the total allowable drop may be 11%. Clause 3.6.3, Conductors in parallel. This clause explains how to calculate voltage drop when a circuit has conductors running in parallel. In this case, the voltage drop is taken as the drop in one conductor, with the current adjusted based on the proportion of current actually carried by that conductor. The calculation must follow clause 3.6.2, but the current in the formula is divided according to the number of parallel conductors. Clause 3.7, Electrical connections. This clause introduces the requirements for how conductors must be connected so that electrical continuity, insulation integrity, and mechanical strength are maintained throughout the life of the installation. Clause 3.7.1, General. This clause explains that every connection between conductors, or between conductors and equipment, must provide a reliable electrical pathway, proper insulation, and enough mechanical strength to stay secure. The way cables are joined must suit the application, and the joint must conduct electricity at least as well as the conductor itself. There must be no unnecessary pressure on the conductor either before or after the connection is made. Clause 3.7.2, Connection methods. This clause introduces the different ways conductors may be joined or connected and the requirements for ensuring each method is safe and reliable. Clause 3.7.2.1, General. The method of connection must be chosen carefully. Factors such as the conductor material, the insulation type, the shape and number of wires, the cross-sectional area, the number of conductors being joined, the temperature reached at terminals in normal use, and protection against moisture and water entry all influence the correct choice of connection method. Clause 3.7.2.1.1, Common requirements. This clause reinforces that the above factors must be considered so the connection remains electrically sound and the insulation remains effective. Moisture control must also be considered to stop water entering the joint or moving along conduits or enclosures. Clause 3.7.2.1.2, Aluminium conductors. Aluminium conductors need special care. Joints and terminations must use parts specifically designed for aluminium and must follow the manufacturer's instructions. When working with aluminium, the oxide layer must be removed, the softness of aluminium must be considered, and differences in expansion rates between aluminium and other metals must be taken into account. The conductor must also be protected from contact with dissimilar metals that can create galvanic corrosion. Clause 3.7.2.2, Preparation for connection. Insulation must only be removed as much as is needed to form the connection. When joining insulated conductors, the finished connection must have an insulation level that matches the original conductor. Any damaged insulation must be repaired or reinstated. Clause 3.7.2.3, Loosening of connections. Clause 3.7.2.3.1, General. Connections must be made so they do not loosen under vibration, material movement, or normal temperature changes. The connection must remain secure throughout its service life. Clause 3.7.2.3.2, Crimp joints. Conductors joined by crimping must use the correct type of crimping tool and the correct components approved by the manufacturer. When a crimp is correctly made, it forms a permanent and secure mechanical and electrical joint. Clause 3.7.2.3.4, Mechanical connection devices. This clause explains the requirements for mechanical devices used for connecting conductors. These devices must comply with an appropriate standard, must not rely on compressing the insulation to make an electrical connection, and must carry fault current safely. They must have a long-term current carrying capacity equal to the conductors, must not deteriorate if reused, must include the manufacturer's instructions, and must be installed exactly as the manufacturer specifies. Clause 3.7.2.5, Retention of stranded conductors. The ends of stranded conductors must be secured so individual strands cannot spread or escape. They must not be soft soldered before being tightened under screws or clamps. Clause 3.7.2.6, Mechanical stress. Cables and conductors must be installed so no unnecessary mechanical stress is applied to the connection or the conductor. Clause 3.7.2.7, Soldered connections. Where soldered joints are used, the design must consider mechanical stress and how the connection behaves during a fault. Soft soldered joints must not be clamped under screws or between metal plates. Soldered joints are not allowed for aerial conductors under tension. Clause 3.7.2.8 Flexible cords. Joints must not be made in flexible cords, except where the flexible cord is being used as installation wiring and the requirements of earlier clauses are met. Connections between flexible cords and fixed wiring must be made in purpose-designed devices such as flex connectors or cable couplers. Any flexible cord must be installed so that no undue stress is placed on the connections due to pulling, twisting, or sharp bending. Clause 3.7.2.9 Aerial conductors. Clause 3.7.2.9.1 Joints and connections. Connections in aerial conductors must not be soldered, must be reliable, must be protected from sun, moisture, and movement, and must be kept short. Where different metals are joined, galvanic action must be prevented by using suitable connectors. Clause 3.7.2.9.2 Prohibited joints. Certain types of aerial cable must not be jointed at all while under tension. This includes parallel webbed or twisted aerial cables, neutral screened cables, multi-core aerial cables, and cables made from different metals. Clause 3.7.2.10 Underground cables. Joints in underground wiring must be sealed to prevent water entry. Proper sealing ensures long-term reliability and prevents corrosion. Clause 3.7.2.11 Earthing conductors. If the earthing conductor is joined by soldering, the joint must be secured by additional mechanical means so the conductor remains firmly held even if the solder softens. Tunnel-type connectors used with earthing conductors must have either two screws or one large screw able to grip the conductor without cutting it. Where clamping over insulation is not necessary, bare conductors must be clamped directly using suitable ferrules or plates. Clause 3.7.3 Joints and cables. Joints and cables must be enclosed, typically in a junction box, to protect the joint from external influences. However, a cable joint does not need to be enclosed if it is not under strain, if it meets the requirements for proper connection, if any damaged mechanical protection has been restored, and if the insulation and sheathing are reinstated to an equivalent standard. Clause 3.7.4 Installation couplers. Installation couplers may be used for connecting cables, including flexible cords and rigid conductors, as long as they comply with ASNZS 61535. These couplers are designed for permanent connection and must be used correctly. Some require deliberate action to disconnect, and they must not be engaged or disengaged under load unless designed for that purpose. Clause 3.8 Identification. This clause introduces the requirement to clearly identify conductors so their function as active, neutral, earthing, or equipotential bonding is unmistakable. Clause 3.8.1 General. Installation wiring must be clearly identified so anyone working on the installation can immediately recognize each conductor's purpose. When colors are used for identification, they must follow the colors listed in Table 3.4. Green, yellow, or the green and yellow combination must never be used as active or neutral conductors in installation wiring. These colors are reserved for earthing and equipotential bonding only. Clause 3.8.2 Color identification by sleeving or other means. In some situations, conductors may be identified by sleeving or other methods instead of relying on the insulation color alone. Sleeving must use colors that match those listed in Table 3.4 and must be applied at each termination. Conductors with black or light blue insulation may be identified as active if sleeved correctly. Conductors with colors other than green, yellow, green and yellow, black, or light blue may be identified as neutral. Cores within multi-core cables that are not green, yellow, or green and yellow may be identified as earthing conductors when sleeved correctly. The sleeving must be color-fast, non-conductive, and suitable for the environment. Single-core cables that are not already green, yellow, or green and yellow must show continuous identification along their full length if used as earthing conductors. Clause 3.8.3 Exceptions and special applications. This clause explains where the identification rules of clauses 3.8.1 and 3.8.2 do not have to be followed. Clause 3.8.3.1 Protective earthing and equipotential conductors. A bare or aerial conductor used as a protective earth does not require green and yellow identification. If a multi-core cable includes a protective earth within a screened layer, the individual conductor does not need green and yellow insulation. The core may instead be marked at its ends where it joins the earthing system. Some insulated protective earths are made using materials that cannot be colored green and yellow. In these cases, sleeving at terminations is recommended unless the conductor's purpose is already clear. Clause 3.8.3.2 Active and neutral conductors. This clause describes situations where active or neutral conductors do not need to follow the color rules in Table 3.4. In multi-core flexible cables, each core may be identified by numbering, lettering, or other methods that clearly show its function. Flexible cords and cables may also use alternative identification systems, provided they match the relevant requirements in earlier clauses. Some aerial conductors are identified by small ribs or markings along the insulation rather than by color. The neutral conductor may use a special rib pattern that is repeated along the cable to make the identification clear. Clause 3.8.3.3 European Cable Identification Colors. This clause explains that some imported equipment and cables follow European color codes. These differ from ASNZS conductor colors but may still be encountered in practice. To ensure safety, the installer must confirm the function of each conductor when European coded wiring is encountered, particularly with imported appliances or lighting equipment. Clause 3.8.3.4 Aerial earthing conductors. Aerial earthing conductors must be identified directly at each end of their run. The marking must clearly show that the conductor is an earth, either by using the letter E or by using an earthing symbol placed at the termination point. Clause 3.9 Installation requirements. This clause introduces the general rules for how wiring systems must be installed so they remain safe under normal use, wear and tear, and any unusual conditions that can reasonably occur. Clause 3.9.1 General. Wiring systems must be installed following recognized safe practices. They must be installed in a way that protects the installation against mechanical or electrical failure, both during normal operation and under conditions that may arise over time. Any installation method that is used must take into account external influences that may affect the wiring system. Clause 3.9.2 Methods of installation. This clause explains that many acceptable wiring methods exist, and examples are listed in Table 3.1. Other methods may be used as long as they meet the general requirements of this section and take external influences into account. If a relevant product standard applies to a wiring system, that product standard takes priority over this clause. Clause 3.9.3 Support and fixing. This clause explains how wiring systems must be supported and secured so they remain safe and do not move or sag over time. Clause 3.9.3.1 General. Wiring systems must be supported by suitable means as required earlier in Clause 3.3.2.8. They must be fixed using clips, saddles, clamps, or any method that does not damage the wiring and is not affected by external influences. When wiring is installed in a building structure, the size and position of any openings must not weaken the structural strength required by building codes. Where sheath cable passes through metallic structural members, an aperture must be bushed or shaped so that the cable is not damaged. If the wiring is likely to be disturbed, the cable must be fixed at a point near the opening. Clause 3.9.3.2 Suspended ceilings. Wiring installed above suspended ceilings may be supported by the ceiling system unless the ceiling manufacturer prohibits it. Cables must have extra protection in any place where they may be damaged by ceiling runners or other conductive supports. Wiring above suspended ceilings must be fixed at suitable intervals so it does not sag. Clause 3.9.3.3 Wiring systems likely to be disturbed. Some locations require extra support because the wiring is more likely to be touched, moved, or affected by normal activity. This includes wiring on the surface of walls or ceilings, wiring between a floor and an area where people may gain access, wiring in ceiling spaces with access heights over 0.6 meters, wiring within 2 meters of any access point, and wiring under raised floors. Clause 3.9.4 Protection against mechanical damage. This clause explains where wiring is likely to be exposed to mechanical damage and must therefore be protected. Clause 3.9.4.1 General. Where it is reasonable to expect mechanical damage, the wiring system must be protected in accordance with Clause 3.3.2.6 and the detailed requirements that follow. Clause 3.9.4.2 Wiring systems near building surfaces. Wiring fixed in place by fasteners or passing through structural members must be protected by one of the approved methods if it is less than 50 mm from a wall, floor, ceiling, or roof surface. Protection is also required where the cable is located more than 150 mm from wall-to-wall or wall-to-ceiling corners. These requirements do not apply to wiring systems that can move freely enough to avoid being struck by nails or screws driven into the surface. Clause 3.9.4.3 Wiring systems under wall lining or roofing material. Clause 3.9.4.3.1 Prohibited locations. Wiring must not be installed in the space between roofing material and its immediate supporting members, or in similar spaces behind wall linings where a person may reasonably drive a nail or screw. These locations include the space between battens and roofing tiles, or between corrugated roofing sheets and their supporting members. Clause 3.9.4.3.2 Protection required. If wiring passes through a structural member, or is fixed in position within 50 mm of the surface to which roofing or wall material is attached, one of the approved protection methods must be used. Clause 3.9.4.4 Protection methods. Where protection is required, the wiring system must either have adequate mechanical protection, or be enclosed in an earthed metallic covering, or be protected by an RCD with a maximum residual operating current of 30 mA. Clause 3.9.5 Wiring systems installed vertically. Wiring systems installed vertically must comply with earlier support requirements and must be arranged so that no damage occurs due to the cable's own weight or the method of support. If wiring is enclosed in a vertical riser, cable supports must be placed at intervals not exceeding 8 meters or as recommended by the cable manufacturer. Clause 3.9.6 Change of direction. When wiring systems change direction, bends must be made so that they do not damage the sheathing or insulation. The minimum bending radius recommended by the manufacturer must be followed. If this information is not available, unarmored sheathed cables should have a bending radius of at least 6 times the diameter of the cable, and armored cables should have a radius of at least 12 times the diameter. Any support in contact with the cable must not have sharp edges that could damage the insulation. Clause 3.9.7 Particular requirements. This clause sets out additional installation requirements for specific wiring systems. Clause 3.9.7.1 Consumers' mains. Consumers' mains must be installed so the risk of short circuit is kept as low as possible. Clause 3.9.7.1.1 Protected. Where consumers' mains are protected on the supply side by a short circuit protective device, they must comply with all the relevant requirements of this section. Sometimes the electricity distributor's protective devices already provide this protection. Clause 3.9.7.1.2 Unprotected. Where consumers' mains are not protected on the supply side, the wiring must be constructed to minimize the risk of short circuit and must follow any additional requirements set by the electricity distributor. Certain wiring systems are taken to provide minimum short circuit risk. These include insulated and sheathed cables in heavy-duty insulating conduits, insulated and sheathed cables in underground wiring enclosures, aerial conductors of specified types, and busway systems that provide insulation up to the first protective device. Clause 3.9.7.2 Insulated and sheathed cables. Armored sheathed cables may be installed in concrete or plaster or cement render without an extra wiring enclosure, provided they meet all installation requirements for mechanical protection. Unarmored sheathed cables installed in concrete must be enclosed in an appropriate wiring enclosure that meets the rules for concealed wiring. Clause 3.9.7.3 Mineral insulated metal sheathed cable. This clause deals with MIMS cables. For corrosion protection, these cables must be installed in locations where corrosion is unlikely, or they must be protected by suitable methods. For vibration protection, a loop of cable may be needed before the termination to absorb movement. Supports and fixings must suit the highest temperature that the cable may reach in service, and must prevent damage. Clause 3.9.7.4 Flexible cords used as installation wiring. Flexible cords used as installation wiring must be heavy-duty sheathed types and must be installed using the same rules that apply to insulated sheathed cables. There are limited exceptions where flexible cords do not need to be heavy-duty. These include cords used for pendant socket outlets, cords installed inside a suitable wiring enclosure, and cords used as equipment wiring as allowed elsewhere in the standard. Flexible cords used as installation wiring must follow all requirements of this section and must not be open to view. Clause 3.9.7.5 Low voltage track systems. Low voltage track systems must be installed so the track is open to view for its full length but does not need to be visible from every position. The system must be positioned to reduce dust entry, and the supports must be appropriately designed, correctly spaced, and arranged so the track is held securely without sagging. Clause 3.9.7.6 Undercarpet wiring systems. Undercarpet wiring may be used only as a floor-mounted system, and only in areas not larger than 1 meter by 1 meter. The system must be installed according to the manufacturer's instructions. Systems of different designs must not be interconnected unless the manufacturer specifically permits it. Clause 3.9.8 Prevention of mutual detrimental effects between services. Wiring systems must be arranged so they do not adversely affect other electrical services or non-electrical services. Clause 3.9.8.1 General. This includes preventing detrimental effects between different electrical installations, different parts of the same installation, circuits of different voltages, safety services, non-electrical services such as gas and water supply, and telecommunications or data cabling. Clause 3.9.8.2 Different electrical installations. Conductors belonging to different electrical installations must not be installed in the same wiring enclosure unless proper segregation is provided. Where different installations terminate in a common enclosure, they must be effectively segregated. This may be achieved by using sheathed cables, barriers, or by spacing. Clause 3.9.8.3 Segregation of different voltage levels. Cables of high voltage circuits and low voltage or extra low voltage circuits must not be installed in the same wiring system unless effective segregation is provided. Low voltage and extra low voltage circuits may share the same wiring system only if the cables provide equivalent protection or the cables are enclosed in separate compartments with continuous barriers. Clause 3.9.8.4 Proximity to non-electrical services. Wiring systems must not be installed near services that produce heat, smoke, or fumes unless shielding prevents damage. Wiring below services that may create condensation must be protected. Electrical services must not interfere with the operation of adjacent services. Wiring must be protected from hazards created by the presence of other services. Unenclosed wiring must not be installed where it might be accessible to personal contact or could touch other services such as gas or water piping. When crossing gas or water pipes, wiring must maintain the required minimum separation. Clause 3.9.9 Selection and installation to minimize the spread of fire. This clause covers precautions to help prevent fire spreading through or because of wiring systems. Clause 3.9.9.1 General. Where wiring systems pass through building elements, precautions must be taken to limit the spread of fire. Where equipment contains flammable liquid, measures must be taken to prevent burning liquid from escaping and spreading fire. Where building dimensions increase fire spread risk, precautions must be used so wiring does not contribute to fire propagation. Clause 3.9.9.2 Precautions. Wiring systems must be installed so the building's structural performance in a fire is not reduced. Cables and wiring products with appropriate fire ratings must be used where required. Wiring systems that do not meet the required fire rating may be used only for short lengths when connecting appliances. Segregation between fire-rated compartments must not be compromised. Clause 3.9.9.3 Penetration of fire barriers. Where wiring passes through floors, walls, or other fire-rated elements, the penetration must meet strict requirements. The opening must fit closely around the wiring system, the size of the opening must be limited, and the fire rating of the structure must be reinstated after the wiring is installed. Conduits or trunking systems may pass through fire-rated elements if they meet specified protection and sealing requirements. Sealing systems must be compatible with the wiring materials, must allow thermal movement without losing sealing performance, and must resist the same external influences as the wiring system. Clause 3.9.10 Limitation of circulating and eddy currents. This clause explains how certain wiring arrangements can create unwanted circulating or induced currents, and steps must be taken to limit them. Clause 3.9.10.1 General. Precautions must be taken to reduce circulating currents and eddy currents that may cause overheating. Clause 3.9.10.2 Cables for AC circuits. Single-core cables running through ferrous enclosures such as steel must not be used for AC circuits unless precautions are taken to limit induced heating. Where single-core cables carrying alternating current enter a ferrous enclosure, the conductors must either be arranged so they are not surrounded by ferrous metal or provided with spacing or other methods to prevent excessive heating. Clause 3.9.10.3 Cables with non-ferrous metal sheathing. Single-core cables enclosed in copper, aluminium, or other non-ferrous sheathing may be used only where the installation avoids the creation of excessive heating. Trefoil formation may be used, where the cables are run together in groups of 3 for their full length. Where trefoil is not used, cables must be installed as close as possible to each other. The sheathing must be bonded at both ends and at intervals not exceeding 30 meters to ensure equal conductivity and to control induced currents. Clause 3.9.11 Electromagnetic interference. Some electrical installations may be sensitive to electromagnetic interference created by current in nearby cables. Interference may be reduced by selecting cables with low magnetic emissions, installing cables in enclosures that shield magnetic fields, or arranging cables in configurations that minimize magnetic field strength. Clause 3.10 Enclosure of cables. This clause explains when cables must be enclosed in a wiring enclosure, what types may be used, and how they must be installed. Clause 3.10.1 General. This clause sets the rules for enclosing insulated cables that do not have a sheath. These cables must be enclosed throughout their entire length unless one of the listed exceptions applies. Clause 3.10.1.1 Insulated, unsheathed cables. Insulated unsheathed cables must be enclosed unless they are used in specific situations allowed by the standard. These include when they are used as aerial conductors, when they are inside a wall cavity very close to an accessory or wiring enclosure, when they are inside a switchboard or similar enclosure where they cannot be touched during normal operation, when they are earth or bonding conductors installed under Section 5, or when they are extra low voltage conductors under Section 7.5. Clause 3.10.1.2 Insulated and sheathed cables. Sheathed cables do not always need to be enclosed. However, if the cable's insulation or sheath does not meet the fire propagation requirements of the ASNZS 5000 series, then the cable must be put inside a fire-rated enclosure. Whenever part of a sheath is removed, the exposed conductors must be enclosed to provide protection similar to a fully sheathed cable. Clause 3.10.2 Wiring enclosures. Clause 3.10.2.1 Types. This clause explains what types of wiring enclosures may be used. These include steel conduits and other metal tubing, flexible metal conduit, rigid and flexible insulating conduit, corrugated insulating conduit, and cable trunking systems. Any other enclosure may be used if it provides at least the same level of mechanical protection as the ones already listed. Where unsheathed cables are enclosed, any removable cover must be fixed so it cannot be taken off without tools when it is in an accessible place. Clause 3.10.2.2 Change of wiring enclosures. Whenever a cable moves from one type of enclosure to another, the change must occur either at a switchboard or through a suitable device that protects the insulation and maintains continuity of any conductive enclosure. Clause 3.10.2.3 Entry of water. Wiring enclosures must be installed to prevent water entering equipment or the enclosure. Where exposed to the weather, they must include suitable protection to stop rain entering. The installer must consider the height of each end of the enclosure, because the lower end may be more likely to allow water entry. Clause 3.10.3 Installation of wiring enclosures. Clause 3.10.3.1 General. Wiring enclosures must be installed following safe and sound practice and must provide the degree of protection set out in earlier clauses of Section 3. Clause 3.10.3.2 Support. Enclosures must be supported so they are not damaged and so they do not damage the cables inside. Clause 3.10.3.3 Continuity. Metal enclosures must maintain both mechanical and electrical continuity unless the standard specifically allows them not to be earthed, such as when they contain only insulated and sheathed cables. Clause 3.10.3.4 Bending. Every bend in a wiring system must be made so the cables are not damaged. Rigid conduit must not be bent so tightly that the internal diameter is reduced. Where trunking or ducts are used, any change of direction must allow the cable to meet the bending radius requirements stated earlier. Clause 3.10.3.5 Passage for conductors. When cables pass through metalwork such as tubes, channels, conduit ends, or openings, they must be protected. If the opening is bush, the bush must be securely fixed. If it is not bushed, the edges must be smooth with no sharp projections that could damage the insulation or sheath. Clause 3.10.3.6 Terminations. Wiring enclosures must terminate and be supported so that cables passing into equipment are fully protected. Flexible conduit must be securely anchored to the equipment where it terminates. Clause 3.10.3.7 Installation in direct sunlight. Rigid insulating conduit fittings, and cable trunking systems installed in direct sunlight must either be designed for sunlight exposure or be painted with a suitable light-colored acrylic paint that reduces heat buildup. Clause 3.10.3.8 Provision for expansion. Rigid insulating conduit must be installed with allowance for thermal expansion. As a guide, a 10-degree temperature rise causes about 1 mm of expansion per meter of conduit. Clause 3.10.3.9 Cable trunking. Cable trunking must be installed so that its covers can be opened where practical, and covers must be continuous when passing through walls or floors. The full length of the trunking must remain accessible. Trunking must not rely on removable covers for cable support. Non-hygroscopic trunking must be used when enclosing insulated unsheathed conductors. Any live parts of accessories mounted on trunking must be arranged so that basic protection is provided, consistent with Clause 1.5.4. Clause 3.11 Underground wiring systems. This clause explains how underground wiring must be selected, protected and installed so that it remains safe throughout its life. Clause 3.11.1 Suitability and protection. Any cable installed below ground must be suitable for the soil or environment it is placed in. It must also be protected against accidental damage, especially from digging or machinery. Where there is any chance that the cable might be struck during excavation, suitable warning systems, markings or protective measures must be used to reduce the risk. Clause 3.11.2 Classification of wiring systems. Underground wiring systems are grouped into 3 categories. The category depends on the type of cable and the amount of enclosure or mechanical protection provided. A Category A system is considered inherently suitable for below-ground installation and generally does not need extra mechanical protection. A Category B system is suitable for below-ground installation but requires added mechanical protection. A Category C system is one in which the cable is laid in a channel chased into rock. Underground wiring must use the types of cable allowed for that category and must follow the permitted installation methods for that category. Clause 3.11.3 Arrangements. This clause describes the arrangements that qualify as Category A, Category B, or Category C systems. Category A systems may use heavy-duty insulating conduit, insulating wiring enclosures encased in concrete, or sheathed cables buried directly in the ground where permitted. Category B systems include cables enclosed in medium-duty conduit with added mechanical protection, or sheathed cables buried directly with protection provided. Category C systems are used when the cable is laid within a rock channel and then covered with concrete. Examples of each arrangement are given for illustration, but the key idea is that the cable type and the enclosure must match the intended category. Clause 3.11.4 Installation Requirements. This clause outlines how underground wiring must be installed to remain safe from mechanical damage and environmental effects. Clause 3.11.4.1 General. Underground wiring must follow the specific requirements of the later subclauses, which include bedding, mechanical protection, minimum depth of cover, and correct identification. Clause 3.11.4.2 Unenclosed cables. If cables are not installed inside an enclosure in a Category A or B system, they must be laid on a bed of fine material at least 50 mm deep. They must also be covered by at least 50 mm of the same type of material. This bedding prevents stones or sharp objects from damaging the cable. Clause 3.11.4.3 Category B Mechanical Protection. A Category B system requires additional mechanical protection. This must be placed not more than 75 mm above the cable, and must be at least 150 mm wide. The protection must also extend at least 40 mm beyond each side of the wiring system. This protection may be provided by precast slabs, cast-in-place concrete, continuous concrete cover, fibrous cement slabs, bricks, polymeric cover strips, or other materials that provide an equivalent degree of protection. Clause 3.11.4.4 Minimum depth of cover. Underground wiring must be buried to a depth suitable for the specific installation. The required depth depends on whether the wiring is inside a building, beneath poured concrete, or out in natural ground. The minimum depth is based on the top of the wiring system, or on the top of the mechanical protection layer if used. Clause 3.11.4.5 Identification of underground wiring. Underground wiring must be identified with orange marker tape. The tape must meet the requirements of the relevant standard and should be positioned roughly halfway between the wiring system and the ground surface, or halfway between the wiring system and the top of the mechanical protection. Where the wiring is chased into rock, the tape must be laid directly above the cable before concrete is poured. Where underground wiring is installed by directional drilling, tape may be omitted as long as the location of the wiring is permanently recorded so it can be found by anyone digging in the future. If a pipe or conduit is left in place after drilling, using an orange conduit is recommended for clear identification. Clause 3.11.4.6. This clause is about making sure we always know where underground cables are, so they don't get damaged when someone digs. First, we must put a marker sign showing where the cable goes into the ground or comes out near a building. If this point is already very clear, then a sign is not needed. Next, the path of the cable must be drawn on a plan so future workers can find it. That plan must be kept at the switchboard where the circuit starts. For consumers' mains, the plan must be kept at the main switchboard of the building. If the underground wiring is fully inside a building area, marking is not required. Clause 3.11.5 Spacing from other underground services. Underground wiring must be separated from gas, water, stormwater, sanitary drains and telecommunications services by a safe distance. This distance depends on the type of service but is never less than 100 mm. The wiring must also be marked with suitable warning tape when required. Additional requirements apply for separation from telecommunications, gas and water services, as described in earlier clauses. Table 3.7 gives the minimum separations. The exact numbers vary depending on the service, but the key idea is that low-voltage electrical wiring must be kept enough distance away from other underground services so that damage or faults in one system do not affect the other. Some exceptions apply, such as when services are installed in the same trench but kept in separate enclosures, or when conductive enclosures are bonded to the electrical earthing system. Clause 3.12, Aerial Wiring Systems. The standard reminds us that aerial wiring may not be allowed in some places, especially areas with a high bushfire risk. Local authorities and the electricity distributor may place limits on this type of wiring. Clause 3.12.1, Types of conductor. This clause explains what types of conductors are suitable for aerial wiring. Aerial wiring can use bare hard-drawn conductors, or insulated polymeric cables, or neutral screened cables, or insulated cables that are twisted, bundled, or webbed together. The idea is that only conductor types designed to withstand environmental exposure can be used overhead. Clause 3.12.2, Arrangements. Clause 3.12.2.1, Insulation of aerial conductors. Aerial conductors must be insulated in several situations. They need to be insulated when they are attached to a building or structure. They need insulation when the cable span is close enough for someone to reach from a building or an opening. They need insulation where sailing craft or irrigation pipes may rise up underneath the line. And insulation is required in areas at risk of bushfire when the authority says so. There is an exception for conductors that are fully supported by two independent poles or similar supports, as long as the span is not connected to a building. Clause 3.12.2.2, Minimum Size. Overhead conductors must meet minimum size rules to ensure strength and safety. Copper or aluminium conductors need at least 7 strands, with copper no smaller than 6 square millimeters and aluminium no smaller than 16 square millimeters. Steel conductors need at least 3 strands. The idea is that overhead conductors must be strong enough to resist wind, tension, and long-term sag. Clause 3.12.3, Clearances. Clause 3.12.3.1, General. Aerial conductors must be installed with enough clearance from the ground, from buildings, and from structures. The clearances are set so the conductors stay safely out of reach under normal conditions and when they sag in hot weather. If the conductor will run hotter, or if extra sag is expected, more clearance must be added. When conductors end at a building or structure, the installation must prevent anyone from touching them accidentally. Clause 3.12.3.2, Safety Warnings. Where there is a reasonable chance that people may contact aerial conductors, warning signs or other notices must be installed. This includes areas with sailing craft, locations where long irrigation pipes may be moved around, places where high vehicles load or unload, or anywhere else where unexpected contact might occur. Some authorities may require extra signage near waterways. Near aerodromes, extra warnings may be required to alert aircraft. Clause 3.12.4, Distance between supports. This clause gives the maximum span allowed between supports for different overhead conductor types. The span length depends on the conductor size and construction. Longer spans may be used only when a qualified engineering design confirms the installation is safe. Clause 3.12.5, Aerial conductor supports. Supports must be suitable for the conductor type and must be designed for overhead use. Pin-type insulators must not be used when the conductor strain might pull the wire off the insulator, or when the line changes direction by more than 30 degrees. The idea is to avoid mechanical stress that could make a conductor come loose. Clause 3.12.6, Poles and posts. Poles and posts must be made from materials suitable for the conditions in which they will be used. They also need to be installed to the correct depth for the soil type. If the ground is very solid, such as rock, the depth may be reduced. If the ground is weak, the pole must be installed deeper or supported by other means. Clause 3.12.7, Joints and connections. All joints and connections in aerial conductors must follow the same installation rules as other cable joints in the standard. They must be mechanically sound and provide proper electrical continuity and insulation. They must also be protected against weather where required. Clause 3.13.3 Clearances. This clause explains that cables supported on a catenary wire must keep safe clearances from buildings, structures and equipment. Outdoors, the clearance must match the requirements for a neutral screened aerial cable. Indoors, the cable must stay at least 100 mm away from any moving parts or from equipment that runs at a high temperature. These clearances help prevent damage to the cable and reduce the risk of electric shock or fire. Clause 3.14 Safety Services. This clause explains that any wiring used for a safety service must meet all the normal installation requirements in this section and must also follow the extra rules set out in section 7.2. Safety services must continue operating during faults or emergencies, so their wiring has stricter reliability and protection requirements than general wiring. Clause 3.15 Busways including rising main systems. This clause explains that busway and rising main systems must comply with ASNZS 3439.2 and must be installed exactly as the manufacturer instructs. Where a busway passes through a fire-rated part of a building, the installation must also meet the fire penetration requirements in Clause 3.9.9.3 so that the fire barrier remains effective. Clause 3.13 explains wiring systems that are supported by a catenary wire. When cables are supported in this way, they must be stranded cables that provide double insulation or an equivalent level of protection. If these cables are installed outdoors, they must also be suitable for direct sunlight. A cable is considered properly supported when it is carried by a catenary wire so that mechanical stress on the cable is reduced. The catenary support must give even support, be made from a material that resists corrosion, be securely fixed at both ends, and be able to handle the mechanical forces that may occur, especially from wind or ice. It also needs to be mounted high enough above the ground so it does not create danger for people, animals or property. Cables on a catenary must keep the same clearances as a neutral screened aerial cable outdoors, and when used indoors must stay at least 100 mm away from moving parts or from equipment that operates at high temperature. Clause 3.14 explains that wiring systems used for safety services must follow every requirement in this section, and must also follow the extra rules in section 7.2, because safety systems must remain reliable during faults and emergencies. Clause 3.15 explains busways, including rising main systems. These systems must meet the requirements of ASNZS 3439.2 and be installed exactly according to the manufacturer's instructions. Whenever a busway passes through a fire-rated part of a building, it must also meet the fire penetration requirements described in Clause 3.9.9.3 so that the integrity of the fire barrier is not reduced. That brings us to the end of Section 3. In this lesson we worked through how wiring systems must be chosen, how they handle external influences, how clearances and support systems work, and how underground and aerial wiring must be installed. All of these rules share the same purpose: to keep the installation safe under normal conditions and under the unusual conditions that can happen over time. If you ever feel unsure in practice, come back to the core ideas from this section, choose the right wiring system, protect it from harm, support it well, and make sure the installation stays safe for the people who use it. When you are ready, we will move on to the next section of the ASNZS 3000. Hi everyone, and welcome to this audiobook designed for the EWRB Electrician Regulation Exam. My name is Aria, and I work alongside Whit Roy as an electrical tutor. This audiobook explains the exam topics in simple spoken language, making it easier to understand and review anywhere, anytime. Before we get into the lesson, I want to explain what this audiobook actually is. This audiobook is not a word-for-word reading of ASNZS 3000. You must always refer to the real standard when you're doing electrical work or preparing for an assessment. What we do here is take the important ideas from the standard and rewrite them in simple spoken English. The goal is to make the rules easier to understand, easier to remember, and easier to revise, especially when you're listening on the go. So think of this audiobook as a learning guide, not a replacement for the actual standard. Alright, let's begin. Today we're starting section 4, which looks at electrical equipment and appliances. This part of the standard brings together many practical rules that you will use on real jobs. It explains how different types of equipment must be installed, how they must be protected, and what safety features need to be in place. Some of the clauses are short and simple, and others go into detailed requirements for appliances like motors, water heaters, heating cables, and gas systems. As we move through the section, we'll break the ideas down into clear points so they're easier to understand and remember. Alright, let's begin section 4, Selection and Installation of Appliances and Accessories. This part explains how appliances and accessories must be chosen and installed so they can operate safely and correctly in a New Zealand electrical installation. Clause 4.1, General. This clause says that Section 4 sets the minimum standard for selecting and installing appliances, accessories, and other electrical equipment that are not covered in other parts of Part 2 of ASNZS 3000. To meet the safety requirements of Part 1, we must follow the rules in this section whenever we choose or install this type of equipment. Clause 4.1.1, Application. This clause explains that the provisions in Section 4 apply to the selection and installation of appliances and accessories that are not already covered in other parts of Part 2. The intention is that by following this section, the installation will meet the safety outcomes required by Part 1. Clause 4.1.2, Selection and Installation. This clause explains that electrical equipment must be chosen and installed so it performs properly and safely in the conditions it will face. It must be able to operate correctly under external influences, it must not create harmful effects on the installation, and it must work safely once assembled and connected to the supply. It must also be installed so people are not exposed to electric shock, fire, high temperature, or physical injury when abnormal conditions such as overload or faults occur. To achieve this, the equipment normally needs to comply with the relevant Australian and New Zealand standards. Section 4 then goes on to explain how to address issues such as external influences, adverse effects, protection, methods of connection, and suitability for different environments. Clause 4.1.3, External Influences. This clause says that electrical equipment must have characteristics that suit the environment where it will be installed. It needs to function properly at its intended location even when exposed to environmental or other conditions. This can be achieved by choosing equipment with suitable design features, or by adding installation measures that protect it against the environment. External influences may include mechanical damage, rain, snow, sunlight, splashing, humidity, plants, animals, excessive dampness, corrosive fumes, galvanic effects, dust, steam, oil, temperature extremes, solar radiation, explosive atmospheres, vibration, or seismic activity such as earthquakes or tremors. The main idea is that the equipment must continue to be safe and functional under these real-world conditions. Clause 4.1.4, Adverse Effects and Interference. This clause explains that equipment must be chosen so that during normal operation, including switching, it does not cause harmful effects to other equipment. When selecting equipment, we must consider issues such as poor power factor, excessive voltage fluctuation, distortion of current waveforms, or electromagnetic emission. These effects can interfere with other equipment or reduce performance. The goal is to make sure the installation operates smoothly without one appliance disturbing another, and this is achieved by good equipment selection and proper installation. Clause 4.2, Protection against thermal effects. This part explains how electrical equipment must be selected and installed so that heat from the equipment does not create danger to people, property, or other parts of the installation. Clause 4.2.1, General. This clause says that electrical equipment must be installed so that the heat it produces during normal operation does not create harmful effects on the equipment itself or on anything around it. Adequate ventilation must be provided when needed so the equipment stays within its normal temperature range. The main idea is that heat must not cause deterioration, unsafe operation, or early failure. Clause 4.2.2, Prevention of fire hazard. This clause explains that electrical equipment must be arranged so it does not create a fire risk in the place where it is installed. Clause 4.2.2.1 Installation of electrical equipment. This clause says that equipment must not be placed in a position where the heat it produces, or any fault it may develop, could cause material around it to ignite. The installer must think about the environment and avoid creating a fire hazard. Clause 4.2.2.2 Storage of flammable materials. This clause explains that when an area is likely to be used to store flammable materials, measures must be taken to prevent sparks or high temperatures from igniting them. The installer must make sure equipment is positioned or protected so that stored materials cannot be set alight. Clause 4.2.2.3 Protection from high temperatures. This clause explains that some fixed electrical equipment can reach high surface temperatures that may ignite nearby materials. When this is the case, the equipment must either be mounted on materials that can withstand the heat, screened from combustible materials, or placed far enough away so the heat does not cause a harmful effect. The idea is that surrounding parts of the building must not overheat to a dangerous level. This clause also explains that some equipment produces radiant heat, such as lamps, heaters, and transformers. These must be placed far enough away so that anything behind or around them does not reach a dangerous temperature. The notes remind us that long-term heating can cause some materials to slowly break down or even self-ignite, and that restricting heat dissipation can increase temperatures inside the equipment. Clause 4.2.2.4 Emission of arcs or sparks. This clause explains that if permanently connected equipment may produce arcs or sparks during normal operation, it must be enclosed or screened by arc-resistant material, or placed far enough away from building elements so those arcs do not cause thermal damage. The idea is to contain or control the arc so it cannot set fire to anything around it. Clause 4.2.2.5 Electrical equipment enclosures. This clause says that the materials used to build enclosures must be able to withstand the highest temperature likely to be produced by the equipment. Flammable or easily combustible materials must not be used for enclosures because they may ignite or melt when heated. Clause 4.2.2.6 Prevention of spread of fire. This clause explains that equipment such as switches, socket outlets, and other accessories must be positioned so they maintain a minimum separation from openings and fire-rated building elements. The separation distance helps ensure that fire does not easily pass through. Openings made for electrical equipment and fire-rated barriers must not penetrate more than half the thickness of the barrier. Any space around the equipment and the barrier must be sealed to the correct fire resistance rating so the barrier continues to perform its function. Clause 4.2.2.7 Thermal insulation. This clause applies to New Zealand domestic installations. It explains that appliances and accessories must be installed assuming that thermal insulation will be added in ceilings, walls, or underfloors in the future. The installer must position equipment so that added insulation does not cause the equipment to overheat. Clause 4.2.3 Protection against burns. This clause explains that parts of electrical equipment that can be reached within arm's reach must not exceed the temperature limits shown in Table 4.1. If any part of the installation might reach a temperature above its limit under normal conditions, that part must be guarded so accidental contact cannot occur. The clause includes two exceptions. Equipment that already complies with a standard specifying a limiting temperature does not need further guarding, and items such as lamps are not covered by this requirement. Clause 4.3 Connection of electrical equipment. This clause explains how electrical equipment must be connected to installation wiring. Clause 4.3.1 General. This clause explains that equipment may be connected using several permitted methods listed in later subclauses. Wherever possible, the point of connection must be close to the equipment and must be protected from mechanical damage and interference. Wiring that forms part of an item of equipment is considered equipment wiring and must follow the relevant product standard or as ASNZS 3100. Clause 4.3.2 Direct connection. This clause explains that the installation wiring of the installation may be connected directly to the terminals provided on the equipment. Clause 4.3.2.1 General. This clause states that when equipment is designed with terminals for direct connection, the installation wiring must be connected directly to those terminals. Clause 4.3.2.2 Installation Coupler. This clause explains that an installation coupler, whether enclosed or not, that complies with AS NZS 61535, may be used to connect cables to electrical equipment. The wiring on the equipment side of the coupler is considered equipment wiring. Notes explain that installation couplers are intended for permanent connection and that some types allow the equipment to be disconnected only when not under load. Clause 4.3.3 Socket Outlet. This clause explains that installation wiring may terminate at a socket outlet and the equipment is supplied through a plug and flexible cord or cable. The wiring between the socket outlet and the equipment is considered equipment wiring. Clause 4.3.4 Other connecting devices. This clause explains that wiring may terminate at a junction box, sealing rows, or another suitable device used to connect a specific item or items of equipment. The wiring from the connecting device to the equipment is considered equipment wiring. Clause 4.3.5 Equipment wiring. This clause explains that equipment wiring must be as short as practicable and must have a current carrying capacity not less than the maximum load of the connected equipment. The wiring must be protected against short circuit in accordance with Clause 2.5.4. Where earthing is required, the equipment wiring must include a protective earthing conductor of sufficient size so that, in the event of a fault to earth, the protective device operates without damaging the earthing conductor. Two exceptions apply. Smaller conductors may be used when an assessment confirms they meet the protection requirements. And wiring between a terminating device and a pendant socket outlet is considered installation wiring. Clause 4.4 Socket outlets. Clause 4.4.1 Types. Clause 4.4.1.1 General. Socket outlets shall be suitable for the intended application and location of installation and shall comply with the requirements of the following standards or standards equivalent thereto, as NZS 3112, as NZS 3123, ASE 60309, and as NZS 3131. Clause 4.4.1.2 Different systems. Where an ELV electrical installation and an electrical installation of greater than ELV are in the same premises, all socket outlets supplied at ELV shall have their voltage conspicuously marked, and shall be of a form that will prevent insertion of an ELV plug into a socket outlet connected to a circuit of greater than extra low voltage. Plugs and socket outlets for SELV and PELV systems shall not be provided with an earthing contact or pin and shall comply with Clause 7.5.10. Clause 4.4.2 Location. Clause 4.4.2.1 Accessibility. Each socket outlet shall be installed so that any plug intended to be used with the socket outlet can be conveniently inserted and withdrawn and not cause damage to any flexible cord or cable connected to the plug. Socket outlets shall not be installed where the withdrawal of a plug from the socket outlet is restricted by a permanent fixture or fitting within the installation. Clause 4.4.2.2 Protection of socket outlets. Socket outlets shall be installed so that they will not be subjected to undue mechanical stress or damage in normal service. Where installed in a floor or other horizontal surface, socket outlets shall be designed or arranged to prevent the accumulation of dust or water therein. Where installed within 75 mm of a floor, socket outlets shall be installed so that any plug used with the socket outlet is withdrawn in the horizontal plane. Socket outlets shall be so installed that a plug is not likely to become loose or to malfunction because of gravity, vibration, or the weight of the flexible cord or cable. Where installed in a location that is not readily accessible for the connection of a fixed or stationary appliance or a luminaire, the socket outlet shall be securely fixed to a structure or support to ensure that no mechanical strain is placed on the installation wiring connections when inserting or removing a plug to the socket outlet. The socket outlet need not be fixed in position where the installation meets the following conditions. Cable connections are not subject to undue mechanical stress. The wiring system where likely to be disturbed is supported. The wiring system where installed in a suspended ceiling is supported. Conductors are flexible or stranded type. and insulated unsheathed cables including exposed cores where sheathing is removed are enclosed. The use and location of socket outlets is restricted in a number of particular situations including damp situations in accordance with Section 6 and hazardous areas and other situations in accordance with Section 7. Clause 4.4.3 Earthing contacts. Every socket outlet shall be provided with an earthing contact. Socket outlets for SELV and PELV systems shall not be provided with an earthing contact. Clause 4.4.4 Switching device. Clause 4.4.4.1 General. Each socket outlet shall be individually controlled by a separate switch that complies with either as NZS 3133 or as 60947.3 and operates in all active conductors. Exceptions apply where a single switch is used to control two socket outlets located immediately adjacent to each other, where a socket outlet rated at not more than 10 amperes and installed for a fixed or stationary appliance or a luminaire and is not readily accessible does not need to be controlled by a switch, and where a socket outlet that is switched by the insertion and withdrawal of the plug is deemed to meet this requirement. Clause 4.4.4.2 Rating. Each switch shall have a current rating, at its operating voltage, not less than the current rating of the socket outlet it controls. Where one switch is used to control two socket outlets, the current rating of the switch shall be not less than the total current rating of the socket outlets or the current rating of the overcurrent protective device on the circuit, whichever is the lesser value. Clause 4.4.4.3 Location and marking. Each switch or means of operating the switch for a socket outlet shall be as close as practicable to the socket outlet and marked to indicate the socket outlet or the connected electrical equipment it controls. Where the switch is remote from the socket outlet, it shall be installed in a convenient and readily accessible position and marked in accordance with the requirement that the location of the switch shall be clearly and permanently marked, and both the switch and the socket outlet shall be provided with legible, indelible, and uniform labels indicating their relationship. Marking is not required where the socket outlet is located more than 2.5 meters above the ground, floor, or platform, or is provided for a specific lamp, luminaire, or appliance, or is not accessible for general use. Clause 4.4.4.4 Pendant type socket outlet. A switch incorporated in a pendant socket outlet attached to a flexible cord shall interrupt all live conductors. Exception applies where pendant-type multiphase outlets with switching only in the active conductors are allowed when the outlet is not dependent on the supply cable for support, when additional mechanical protection is provided where necessary, and when the supply cable is selected to take into account any likelihood of vibration and movement expected during operation. Clause 4.4.5 Polarization and phase sequence. Where socket outlets of the same type form part of an electrical installation, the order of connection of the socket outlets shall be the same. All socket outlets that accommodate 3-pin or flat-pin plugs shall be connected so that, when viewed from the front of the socket outlet, the order of connection commencing from the slot on the radial line shall be earth, active, neutral, in a clockwise direction. Clause 4.5 Lighting equipment and accessories. Clause 4.5.1 Lamp holders. Clause 4.5.1.1 Location. All lamp holders shall be located to be adequately protected against damage that might reasonably be expected. In order to protect against inadvertent contact with live parts, low-voltage lamp holders shall be located to minimize the risk of direct contact with live parts of a lamp holder when the lamp is removed, and mechanical damage to the lamp or lamp holder. These requirements may be satisfied by installation not less than 1.8 meters above the ground, floor, or platform, or by provision of a suitable guard for the lamp and its lamp holder, or where the lamp holder is incorporated in a luminaire. A pendant lamp holder shall not be exposed to the effects of significant movement of air such as outdoors or where exposed to the operation of fans. Clause 4.5.1.2 Edison screw lamp holders. Every low-voltage Edison screw lamp holder shall be connected to the supply so that, where a neutral conductor is required, it shall be connected to the outer contact. This requirement need not apply where an Edison screw lamp holder is incorporated in an appliance in a manner permitted by the AS or NZS 60335 series or the AS or NZS 3350 series of the luminaire, and the lamp holder is provided with a shroud or skirt that prevents contact with the outer contact. Clause 4.5.1.3 Festoon lighting. Festoon lighting shall be located and supported so that no lamp will be within 0.15 meters of flammable materials or structural metalwork, or within arm's reach of the ground or any other place on which a person is likely to stand. Festoon lighting may be within arm's reach where installed immediately below a ceiling. Clause 4.5.2 Lamps and luminaires. Clause 4.5.2.1 General. Lamps, luminaires, and their associated ancillary gear shall be so installed as not to cause undue temperature rise, ignition, or deterioration of the materials on which they are mounted or that they illuminate. Luminaires shall be suitable for the highest temperatures to which they are likely to be subjected by external influences, and be installed in accordance with the manufacturer's instructions taking account of the highest rating of lamp to be used. Clause 4.5.2.2 Lamps near flammable materials. Where lamps are located near flammable materials, lamps shall be suitably shielded by a shade, reflector, guard, or enclosure to prevent contact with the material, and lamps such as spotlights that generate heat in the illuminated surface shall be separated by such a distance that the material will not attain excessive temperature. Where information is not otherwise provided with products, the minimum separation distances given in Table 4.2 shall be used. Flammable shades shall not be installed where they are liable to come in contact with any lamp. Clause 4.5.2.3 Recessed luminaires. Clause 4.5.2.3.1 Requirements. Recessed luminaires and their auxiliary equipment shall be installed in a manner designed to prevent excessive temperature rise of the luminaire and auxiliary equipment, and the risk of fire from ignition of combustible materials. These requirements shall be satisfied by one of the following compliance methods: the installation of a luminaire designed and certified by the manufacturer as being suitable for operation in contact with combustible materials or in contact with or enclosed or covered by thermal insulation material, or the installation of a luminaire in combination with a barrier tested and classified in compliance with AS or NZS 5110 as being suitable for the installation conditions, or the installation of a luminaire with separation from thermal insulating materials, combustible building elements, and loose combustible materials not less than the minimum clearance specified by the manufacturer, which may require a barrier or guard constructed of fire-resistant materials, or the default clearances shown in Figure 4.7. Clause 4.5.2.3.2 Warning sign. Where recessed luminaires are installed in an accessible roof space, a permanent and legible warning sign shall be installed in the roof space adjacent to the access panel in a position that is visible to a person entering the space. The sign shall comply with AS 1319 and contain the words shown in Figure 4.8 with a minimum size of lettering of 10 mm. Clause 4.5.2.3.3 Installation precautions. The following precautions should be undertaken for the installation of recessed downlights. The heat generated from lamps should be dissipated in order to prevent over-temperature damage to the luminaire or to adjacent materials. Cooling air circulation through or around the equipment is a requirement for the typical range of downlights. AS or NZS 60598.1 and AS or NZS 60598.2.2 detail the test method and the maximum surface temperatures permitted for recessed luminaires. The maximum temperature of adjacent materials is to be no more than 90 degrees Celsius. In the case of a suitably designed and certified luminaire, the manufacturer's instructions may restrict installation, including warnings such as covering with insulation or the symbol meaning do not cover. Unmarked light fittings shall be treated as do not cover. Under National Building Code requirements, bulk thermal insulation is prevalent in modern building construction within roofs, ceilings, walls, and floors depending on the building and its climate zone. Bulk insulation may also be retrofitted, added, or altered, and precautions will need to be applied by the insulation installer where recessed downlights are present. In Australia AS 3999 and in New Zealand NZS 4246 include instructions for insulation installers in relation to clearances from recessed downlights. The presence of bulk insulation, particularly over the rear of ceiling-mounted downlights, can impair cooling air circulation. Unless the manufacturer specifies otherwise, the space above the luminaire shall remain clear and a warning sign installed. Where clearances are to be applied and bulk insulation is not fixed in position, one of the following means shall be provided to maintain the clearance: a barrier complying with AS or NZS 5110, a guard complying with AS 3999, or a barrier or guard constructed of fire-resistant materials. Combustible materials shall be prevented from being in close proximity or contacting hot surfaces of the luminaires. Where extraneous materials such as leaves, vermin debris, or combustible materials stored in a roof space are present in proximity to the downlight, precautions shall include the use of a suitably designed and certified luminaire or a barrier or compliance method. Unless the auxiliary equipment instructions permit otherwise, any auxiliary equipment operating at a high temperature shall be installed above any insulation as illustrated in Figure 4.7. Clause 4.5.2.3.4. Additional installation requirements, New Zealand only. The following additional requirements apply in New Zealand only. Only recessed luminaires of classes IC-F, IC, SIA 80, or SIA 135 which are compliant with AS or NZS 60598.2.2 including New Zealand only amendment shall be installed in residential buildings. If the recessed luminaire is supplied with a detachable barrier, the complete luminaire including its barrier shall be installed. All classes of recessed luminaires shall be spaced from other building elements as given in the luminaire manufacturer's installation instructions. If no instructions are available, the default clearances shown in Figure 4.9 shall apply and a fixed guard constructed of rigid fire-resistant material may be required. Under the New Zealand Building Code, building insulation is required. Where building insulation is already fitted and recessed luminaires are retrofitted, added, or altered, precautions must be taken by the installer not to compromise the safety of the installation. Clause 4.5.2.4. Suspended ceilings. Luminaires that are supported by a ceiling panel shall not present a mechanical loading that exceeds the capacity of the ceiling panel, and shall not operate at a temperature that would cause deformation, discoloration, or other deterioration of the ceiling panel. Clause 4.6. Smoke and fire detectors. National building codes have requirements for installation of fire and smoke detectors in domestic residences, including location and number required. Where mains-powered smoke or fire detectors are fitted, such detectors may be directly connected to the lighting final subcircuit or to an individual final subcircuit. Use of the lighting final subcircuit provides monitoring that the mains power supply is available, as failure of lighting in an electrical installation would be indicated by the non-operation of lighting luminaires. Fire and smoke detectors are not considered to be safety services for the purposes of this standard. Clause 4.7. Cooking appliances. Clause 4.7.1. Switching device. A circuit for a fixed or stationary cooking appliance having an open cooking surface incorporating electric heating such as a cooktop, deep fat fryer, barbecue griddle or similar shall be provided with a switch operating in all active conductors, mounted near the appliance in a visible and readily accessible position. Switches shall be marked to identify the appliance controlled. Where the open cooking surface is a combined gas and electric appliance incorporating both gas and electric cooking, the switching device shall operate in all active and neutral conductors. Where an electric cooktop is installed in a public park or other open area, the required switch shall be installed adjacent to the cooktop and, to prevent damage by vandalism, may be placed under a lockable cover that is located so that it is able to be operated as required for servicing and maintenance purposes of the cooktop. The switch should be mounted within 2 meters of the cooking appliance but not on the appliance in such a position that the user does not have to reach across the open cooking surface. A single switch is permissible for the control of associated cooking appliances in the same room. It is recommended that switches, particularly those in domestic installations, be marked to identify the appliance controlled. This requirement is not intended to apply to enclosed cooking appliances such as built-in ovens and microwave ovens. Clause 4.7.2 Connection. In New Zealand, a freestanding cooking appliance shall be connected to the electrical installation wiring by a socket outlet or an installation coupler. This requirement need not apply to built-in hobs and ovens. Clause 4.8 Appliances producing hot water or steam. Clause 4.8.1 General. All appliances producing hot water or steam shall be protected against overheating by design or installation in all service conditions. Protection shall be provided by means of an appropriate non-self-resetting device functioning independently of the thermostat. This requirement need not apply to appliances that comply as a whole with an appropriate standard. Where an appliance has no free outlet, it shall also be provided with a device that limits the water pressure. Clause 4.8.2 Water heaters. Clause 4.8.2.1 Access to easing equipment of pressure relief and terminals of protective devices. Every unvented water heater shall be installed so that easing equipment of pressure relief devices and all terminals of the protective devices are readily available for operation, inspection, and adjustment. A vent pipe is one that is intended to operate at the pressure of the water system and the flow of the water being controlled by one or more valves in the outlet system. Clause 4.8.2.2 Protective devices fitted to unvented water heaters. Overtemperature cutouts and similar protective devices fitted to unvented water heaters shall operate directly in the circuit wiring to the heater elements and shall not be arranged for control through relays or contactors. Clause 4.8.2.3 Isolating switch. Every water heater shall be provided with an independent isolating switch or switches in accordance with Clause 2.3.2.2. Such switch or switches shall be additional to any automatic switch incorporated in the heater structure and grouped together and installed on or adjacent to the water heater, or on the switchboard at which the water heater final subcircuit originates. Clause 4.9 Room heaters. Clause 4.9.1 General. Where a permanently connected room heater or a number of permanently connected room heaters are installed in one room, an individual isolating switch and individual functional switch shall be provided for each room heater or for each group of room heaters. Where a number of permanently connected room heaters are installed in one room and are supplied by one final subcircuit, a single isolating switch may be used for the room heaters in that room. Clause 4.9.2 Isolating switches. In accordance with Clause 2.3.2.2, isolating switches shall be installed immediately adjacent to an entrance to or within the room where the room heater is located, or installed on the switchboard at which the room heater final subcircuit originates. Isolating switches may be incorporated in temperature control devices provided that they have a definite off position. Clause 4.9.3 Functional switches. In accordance with Clause 2.3.7, functional switches shall be installed in a readily accessible position in the same room or immediately adjacent to an entrance to the room in which the room heater or room heaters are located. A functional switch may be an appliance switch, or a switch with an off position incorporated within the room heater, or an isolating switch provided in accordance with Clause 4.9.2. Clause 4.10 Electric heating cables for floors and ceilings and trace heating applications. Clause 4.10.1 General. Cables for electric heating systems and floors and ceilings and trace heating applications shall be of a type specifically designed for the purpose. The heating equipment shall be installed in accordance with the manufacturer's instructions. In New Zealand, additional requirements for underfloor and ceiling heating cables are detailed in NZS 6110. Clause 4.10.2 Heating cables. Heating cables shall be so installed that they are not in contact with flammable materials and, where designed to be embedded, are completely and adequately embedded in the substance they are intended to heat and do not suffer any detrimental effect because of flexing or movement of the substance in which they are embedded, or where designed as trace heating cables shall provide adequate heat transfer to the surface or material to which they are fixed. Clause 4.10.3 Isolating switches. Cables or groups of cables that comprise the heating system shall be provided with an isolating switch or switches in accordance with Clause 2.3.2.2. Isolating switches may be incorporated in temperature control devices provided that they have a definite off position. Isolating switches shall be installed immediately adjacent to an entrance to or within the room or area in which the heating system is located, or installed on the switchboard at which the heating system final subcircuit originates. Where the heating system is provided for trace heating applications, the isolating switch need not be located as specified in this clause. Clause 4.10.4. Functional switches. Cables or groups of cables that comprise the heating system shall be provided with a functional switch or switches in accordance with Clause 2.3.7. Functional switches shall be installed in a readily accessible position immediately adjacent to an entrance to or within the room or area in which the heating system is located. A functional switch may be an isolating switch in accordance with Clause 4.10.3. Where the heating system is provided for trace heating applications, the functional switch need not be located as specified in this clause. Clause 4.10.5. Additional protection. All heating cables shall be provided with additional protection by an ACD with a fixed residual current not exceeding 30 mA, and in the case of heating units fitted with a conductive covering, this covering shall be earthed, and in the case of underfloor heating units without a conductive covering, an earthed metallic grit with a spacing not exceeding 30 mm shall be provided above the underfloor heating cable, and heating units shall be provided with adequate mechanical protection to prevent damage. Clause 4.10.6. Signs. Where heating cables are installed, suitable signs drawing attention to their existence shall be provided in each location. Signs warning of the danger of covering embedded heating equipment with furnishings or building materials that might cause excessive temperatures shall be provided where appropriate. This requirement may be satisfied by clearly and permanently marking the functional switch or switches in the heated room or area, or providing suitable labeling at the relevant distribution board. Clause 4.11. Electric duct heaters. The electrical portion of any electric duct heater installation shall comply with the requirements of this standard. Attention is drawn to the fact that such installations are within the scope of AS or NZS 1668.1, and safety requirements are contained in AS or NZS 3102, and compliance therewith may be required by the relevant regulatory authorities. Clause 4.12. Electricity converters. Clause 4.12.1. General. For the purpose of this clause, an electricity converter includes both static and dynamic equipment designed either to stabilize the supply voltage or to change the voltage or frequency of an electricity supply, or to maintain a continuous electricity supply for a limited period of time when the primary source of electricity supply is interrupted. Examples include uninterruptible power systems, semiconductor power converters and inverters, voltage stabilizers, motor generator sets, and rotary converters. Transformers and engine-driven generating sets that comply with AS or NZS 3010 shall not be considered as electricity converters. Requirements for alternate, standby and standalone systems are set out in Clause 7.3. Clause 4.12.2. Selection and installation. Guidance on the selection and installation of electricity converters is contained in AS or NZS 62040 series for uninterruptible power systems, AS 60146 series for semiconductor power converters, AS 3011 for batteries, and AS 1359 series for rotating electrical machines. Clause 4.12.3. Control. Where an electrical installation or part thereof is supplied through an electricity converter, the converted supply shall be controlled by an isolating switch or switches at the output of the converter or at the switchboard to which the output is connected. Each electricity converter shall be controlled by switches or devices suitable for starting and stopping the converter. Where there is more than one switch or device for this purpose, they shall be grouped together and clearly identified. An electricity converter shall be so arranged that it cannot supply energy upstream of the point of connection to the installation either directly or indirectly. Electricity converters may be arranged to supply energy upstream of the point of connection to the installation, subject to any additional conditions required by the electricity distributor. Provision shall be made to ensure that all necessary connections for protection in the installation remain intact when supply is available from the output of the electricity converter. Clause 4.12.4 Isolation. Clause 4.12.4.1 General. Each electricity converter shall be provided with an independent isolating switch in accordance with Clause 2.3.2.2 that shall be installed adjacent to or on the electricity converter so that a person operating the switch has a clear view of any person working on the converter, and comply with Clause 4.13 when the electricity converter incorporates an earth-neutral conductor, and be under manual control only and not be capable of being overridden or bypassed by programmable control systems or the like. Clause 4.12.4.2 Electricity converters incorporating batteries. Where batteries are incorporated in an electricity converter, a switch capable of interrupting the supply from such batteries shall be installed adjacent to the isolating switch and shall be clearly identified to indicate its purpose. A single switch that incorporates both alternating current and direct current switching functions outlined in Clause 4.12.4.1 and this Clause 4.12.4.2 may be used. Clause 4.12.5 Overcurrent protection. Clause 4.12.5.1 Electricity converter protection. Electricity converters shall be provided with overcurrent protection. Overcurrent protective devices shall not be provided where the unexpected interruption of the supply could cause a greater danger than overcurrent. Overcurrent protective devices shall be located as close as practicable to the output terminals of the electricity converter so that the unprotected interconnecting conductors are as short as practicable and in no case exceed 15 meters in length. The unprotected interconnecting conductors shall be completely enclosed by metal or other material that is not flammable. Overcurrent protection may be provided by an overcurrent protective device within the electricity converter itself, or by the characteristics of the electricity converter being unable to support the fault current. Where an electricity converter is intended to operate in parallel with a network or other source, circulating harmonic currents shall be limited so that the current carrying capacity of conductors is not exceeded. The effects of circulating harmonic currents may be limited by the selection of generating sets with compensated windings, the provision of a suitable impedance in the connection to generator star points, the provision of switches that interrupt the circulatory circuit but are interlocked so that protection is not impaired, the provision of filtering equipment, or other suitable means. Clause 4.12.5.2 Circuit protection. Every submain or final subcircuit outgoing from an electricity converter shall be individually protected in accordance with Clause 2.5 and shall also include additional protection where required by Clause 2.6. This requirement need not apply where protection on the incoming side provides protection against an overcurrent condition on the outgoing side. Overcurrent protective devices shall not be provided where the unexpected interruption of the supply could cause a greater danger than overcurrent. The possible waveform of a fault current to earth can affect the operation of RCDs and shall be taken into account for the selection of the type of RCD. Where an electricity converter includes an inverter, the RCD shall be of a type suitable for the waveform of the particular inverter and in accordance with the inverter manufacturer's recommendations. Requirements for types of RCDs are set out in Clause 2.6.2.2. Clause 4.12.6 Earthing. The output of an electricity converter shall be provided with the same type of earthing system used for the associated electrical installation. Protective earthing conductors shall not be switched. Provision shall be made to ensure that all necessary connections for protection, such as the MEN connection, remain intact when supply is available from the output of the system. See Clause 4.12.2 for information regarding standards applicable to various devices. Clause 4.12.7 Neutral continuity. Electricity converters, particularly static converters such as uninterruptible power systems, shall be arranged to ensure that the continuity of the neutral conductor to the load is not interrupted during bypass or maintenance switching. Clause 4.12.8 Electrical equipment connected to output. All electrical equipment connected to the output side of an electricity converter shall be suitable for the voltage, current, and frequency of the output of the unit. The values of current carrying capacity and voltage drop specified in the AS or NZS 300.1 series are valid only for conductors operating at 50 Hz. Refer to Clause 2.6.2.2 regarding the type of a CD to be used where additional protection is required for circuits or equipment supplied by an electricity converter. Clause 4.13, Motors. Clause 4.13.1, Protection against injury from mechanical movement. Clause 4.13.1.1, Switching devices. Every motor shall be provided with a switching device capable of starting and stopping the motor, emergency stopping in accordance with Clause 2.3.5, and isolating the motor for mechanical maintenance in accordance with Clause 2.3.6. Exceptions. Where several motors must function as a group or in a coordinated manner, such as a split-system air conditioner, a single switching device may control more than one motor. A switch for item C need not be provided for motors connected by a plug-in socket outlet, or incorporated in an appliance with no exposed moving parts, or rated not greater than 150 VA notes. Refer to Clause 2.3 for the switching device requirements. As NZS 1668.1 requires locking of air handling and smoke spill isolating switches in the on position. Clause 4.13.1.2, Rating of switches. The isolating switch shall have a rating not less than the full load current of the motor when installed in the motor supply circuit, or the control circuit current when installed in the motor starter circuit. Any switch operating directly in the motor supply circuit shall be capable of interrupting locked rotor or stall current. If not specified, locked rotor or stall current shall be taken as 8 times full load current for AC motors, or 4 times for DC motors. Notes. Suitable switches include those complying with AS 3133 marked with M and the locked rotor current, or switches complying with AS NZS 3947.3 marked with DC23 or AC23. Clause 4.13.1.3, Devices for starting and stopping. Starting and stopping devices shall be located so they are easily operated by the person in charge. A stopping device or isolating switch shall be provided where danger is likely because of moving parts. The stopping device shall remain effective during a fault in a motor control circuit. Remote-controlled equipment shall also have stopping devices at all danger points. Emergency stopping shall comply with Clause 2.3.5. Clause 4.13.1.4, Protection against restarting or reversal. Motors shall be provided with means to prevent danger from unexpected restarting. Notes. This need not apply where warning of automatic restarting is adequate. Alternatives include enclosing moving parts or using warning sirens. Measures shall be taken where danger may occur due to incorrect direction of rotation. Notes. This applies particularly where reverse current braking is used. Clause 4.13.2, Protection against overload. Each electric motor rated above 370 watts shall be provided with protection against overload. Exception. This clause does not apply to motors within electrical equipment complying with an appropriate standard. Clause 4.13.3, Protection against overtemperature. Clause 4.13.3.1, General. Electric motors shall have overtemperature protection where they may be required to run unattended and have a rating greater than 480 VA for shaded pole motors, or 240 VA for other unattended motors, or a rating greater than 2,250 watts. Exception. This clause does not apply where overtemperature protection is not permitted or is not required in accordance with Clause 4.13.3.2. Notes. A continuously running motor or a motor under automatic control in non-domestic premises is deemed unattended. Examples include motors for refrigerators in shops, motors in remote basements, and motors for communal refrigerators in flats. Clause 4.13.3.2, Protection not required. Overtemperature protection is not required where Clause 7.2.9 applies for fire protection motors, or where opening the motor circuit could cause a hazard. It is also not required for unattended submersible pump motors immersed in water rated not greater than 2,250 watts. Clause 4.13.3.3, Overtemperature protective devices. Protective devices shall comply by providing thermal overload protection in accordance with AS 60947.4.1, or built-in thermal protection in accordance with AS 60947.8, or an equivalent protective device. The protective device shall disconnect the required number of supply conductors. Clause 4.14, Transformers. Clause 4.14.1, General. Transformers shall be installed in accordance with clauses 4.14.2 to 4.14.5. Exception. This clause does not apply to an instrument transformer, an extra low voltage transformer, a luminous discharge tube transformer, or a transformer incorporated in a motor starter. Clause 4.14.2, Secondary circuit. Clause 4.14.2.1, General. Wiring and equipment connected to the secondary winding shall comply with the requirements for extra low, low, or high voltage. Clause 4.14.2.2, Control and protection. Secondary conductors shall be treated as submain or final subcircuit conductors and shall be controlled and protected according to clauses 2.3 and 2.5. Exceptions include where only one subcircuit is supplied, or where conductor capacity is not less than the rated current adjusted by the transformer voltage ratio. Clause 4.14.3, Low voltage transformer supply. Clause 4.14.3.1, Isolating transformers. Electrical equipment may be supplied through an isolating transformer in accordance with Clause 7.4. Clause 4.14.3.2, Other transformers. Electrical equipment shall be earthed in accordance with Clause 5.4. Exception. When the output complies with AS NZS 61558, earthing is not required on the secondary. Clause 4.14.3.3, Autotransformers. An autotransformer shall not supply equipment that requires a voltage rating less than the highest input or output voltage. Clause 4.14.3.4, Step-up transformers. No connection shall be made between primary and secondary windings when voltage is raised above normal supply voltage. Exception. A connection may be made using a protective earthing conductor to provide an earth reference supply. Clause 4.15, Capacitors. Clause 4.15.1, General. Capacitors shall be installed in accordance with clauses 4.15.2 and 4.15.3. Exception. This does not apply to capacitors integral to other equipment such as luminaires. Clause 4.15.2, Electrical equipment. Clause 4.15.2.1, General. Equipment and wiring for capacitors shall be suitable for the highest expected voltages, currents and temperatures. Means shall be provided to dissipate heat. Clause 4.15.2.2, Rating of circuit breakers, switches or contactors. Devices controlling capacitors shall be suitable for switching capacitors and appropriate for reactive current. Notes. An example is a utilization category AC6 contactor. Clause 4.15.2.3, Current carrying capacity of supply conductors. Where a capacitor is controlled by a circuit breaker, conductors shall have current rating not less than 135% of the capacitor rating or breaker setting. For motors, conductor ratings follow the motor circuit or 135% of capacitor rating. Clause 4.15.3, Provision for discharge and control. Clause 4.15.3.1, General. Capacitors greater than 0.5 microfarads shall have a discharge path. Terminal voltage shall fall below 50 volts within the required time after disconnection. Warning notices shall state that capacitors must be completely discharged before work. Clause 4.15.3.2, Capacitors connected in parallel with individual appliances. Capacitors shall be arranged so discharge does not occur through the appliance windings. No switch or fuse shall be inserted between capacitor and appliance. Exception. Does not apply where a permanently connected discharge device is used. The capacitor shall be controlled by the appliance control gear. Clause 4.15.3.3, Capacitors not connected in parallel with individual appliances. The capacitor shall comply with the requirements shown in your image. Clause 4.16, Electrical equipment containing liquid dielectrics. Clause 4.16.1, General. Where equipment contains flammable liquid in significant quantity, Precautions shall be taken to prevent burning liquid or byproducts from spreading. Clause 4.16.2. Liquid dielectrics with flashpoint not exceeding 250 degrees Celsius. Precautions include preventing fire spread. Notes. Examples are a drainage pit or installation in a fire-resistant chamber. For less than 50 liters, minimal precautions may be enough. It may be desirable to switch off supply automatically in a fire. Clause 4.17. Batteries. Information on battery selection and installation is contained in AS 3011.1 and AS 3011.2. Clause 4.18. Gas appliances. Clause 4.18.1. General. A gas appliance connected to the electricity supply shall be provided with a means of electrical isolation that is adjacent to the appliance location and is accessible with the appliance in the installed position. The means of isolation shall be a plug to a switched socket outlet, or a plug to a socket outlet that may be located in an inaccessible position but has a separate switch operating in all live conductors located in an accessible position, or a switch operating in all live conductors. Note. If the appliance has an open cooking surface incorporating both gas and electric cooking, it shall also comply with Clause 4.7. Clause 4.18.2. Gas cylinders containing heavier than air gases outdoors. Electrical equipment that is a source of ignition, including socket outlets, switches, luminaires, switchboards, meter boxes and air conditioners, shall not be installed within the hazardous areas shown in Figure 4.10 by dimensions A and B. These dimensions apply for both exchange and in situ fill gas cylinders. For further information refer to AS NZS 60079.1.0.1 and AS NZS 5601, particularly for gases lighter than air. Exception. Approved combined gas and electrical meter enclosures are exempt from these requirements. Note. Electrical equipment selected and installed in accordance with Clause 7.7.2.4 is not considered an ignition source. Clause 4.18.3. Reticulated lighter than air gas system, metering system and regulators. In New Zealand only, electrical equipment, except items that are part of the gas system and installed to the hazardous area requirements, shall not be installed within the hazardous areas shown in Figure 4.11 for both venting and non-venting regulators. For additional information refer to AS NZS 5601. Exception. The dimensions may be reduced where the owner of the metering or pressure-reducing equipment has otherwise advised a different zoning in writing or by way of a sign or sticker attached permanently in proximity to the gas equipment. Note. Electrical equipment selected and installed in accordance with Clause 7.7.2.4 is not considered an ignition source. Clause 4.19. Air conditioning and heat pump systems. Air conditioning and heat pump systems incorporating a compressor shall be provided with a lockable isolating switch installed adjacent to the unit, which isolates all parts of the system including ancillary equipment from the same location. For split system air conditioning units, where the manufacturer requires the air conditioning system to be connected to the electricity supply by means of a plug-in socket at the internal unit, the isolating switch installed at the external unit shall control the socket outlet located at the internal unit. Exception. The isolating switch may be installed at the switchboard supplying the system where the switchboard is dedicated to the equipment, such as an air conditioning plant room. That brings us to the end of Section 4. This section covers a wide range of electrical equipment, and every clause connects back to real work you'll do in the industry. The key message is that each appliance or system has its own safety needs, and the installation must follow the specific requirements to match those risks. When you're on site, keep these rules in mind so the equipment operates safely and meets the standard. In the next section we'll continue building your understanding of how electrical installations work from both a safety and performance point of view. Hi everyone, and welcome to this audiobook designed for the EWRB Electrician Regulation Exam. My name is Aria, and I work alongside Whit Roy as an electrical tutor. This audiobook explains the exam topics in simple spoken language, making it easier to understand and review anywhere, anytime. Before we get into the lesson, I want to explain what this audiobook actually is. This audiobook is not a word-for-word reading of ASNZS 3000. You must always refer to the real standard when you're doing electrical work or preparing for an assessment. What we do here is take the important ideas from the standard and rewrite them in simple spoken English. The goal is to make the rules easier to understand, easier to remember, and easier to revise, especially when you're listening on the go. So think of this audiobook as a learning guide, not a replacement for the actual standard. Alright, let's begin. Today we're moving into section 5, which focuses on earthing arrangements and earthing conductors. This section is all about understanding how earthing is set up in an electrical installation so that faults can clear safely and touch voltages stay within safe limits. Earthing is one of the most important safety foundations in our industry, so as we work through the clauses, we'll see how each part of the system fits together to keep people and property protected. Let's begin section 5, earthing arrangements and earthing conductors. Clause 5.1, General. Clause 5.1.1, Application. This clause explains that the provisions of section 5 form the minimum standard for choosing and installing earthing arrangements. These arrangements must satisfy the requirements of Part 1 of the standard. Clause 5.1.2, Selection and Installation. This clause explains that earthing arrangements must be selected and installed so the electrical installation can operate safely and correctly. They must allow automatic disconnection of supply when there is a fault to earth or excessive earth leakage current. They must allow equipment that needs an earth reference to operate properly. They must reduce voltage differences between exposed conductive parts and extraneous conductive parts through bonding. They must provide a reliable low-impedance fault path so earth fault and leakage currents can flow safely without danger or damage. They must also allow exposed conductive parts and extraneous conductive parts to be connected correctly. Clause 5.1.3, MEN Earthing System. This clause explains that the protective earthing arrangements in this standard apply to electrical installations connected to the multiple earth neutral system used in Australia and New Zealand. Under this system, the neutral conductor is earthed at the source and at regular points along the distribution network, and also at each installation. Inside an installation, the earthing system is separate from the neutral, and the neutral is arranged so exposed conductive parts of equipment can be connected to it. This clause notes that figures 5.1 and 5.2 illustrate the system. It also explains the letters used. T means the distribution system is directly connected to earth at the neutral point of the supply transformer. N means exposed conductive parts are connected to the earth point of the distribution system at the MEN connection. C means the neutral and protective conductor functions are combined in one conductor. S means the protective conductor is separate from the neutral in the installation. Clause 5.1.4, Other earthing systems. Alternatives to the MEN system may be used if they still meet the requirements of Part 1 and do not affect the distribution system supplying the installation. Examples include installations that follow IEC 60364, surface mines that use TN, TT, or IT systems under AS 3007, older installations still connected under previous direct earthing or voltage-operated ELCB arrangements allowed by older editions, and installations not supplied from a distribution system. Clause 5.2, Earthing Functions. Clause 5.2.1, Protective Earthing. This clause explains that when a fault occurs between a live part and an exposed conductive part, or a part of the protective earthing system, a touch voltage may appear. Automatic disconnection of supply is intended to limit this voltage. Disconnection is achieved by providing a protective earthing system that connects exposed conductive parts to the earth neutral point of the distribution system. It is also achieved when, in the event of a fault or excessive earth leakage current, overcurrent or earth leakage devices operate within the required time and touch voltage limits. Clause 5.2.2, Functional Earthing. This clause explains that some equipment needs to be connected to the earthing system so it can function correctly, not for safety reasons. Functional earthing conductors do not need to be selected to carry fault current in the same way as protective earthing conductors. Examples include functional earthing connections fitted to some types of ASNZS to provide an earth for alternative supply to their internal electronic circuit when the incoming neutral connection becomes disconnected. It also includes conductors used for cathodic protection systems or for radio interference suppression devices. Where a clean earth is specified for data or signaling equipment, the manufacturer must be consulted to confirm the correct arrangement. Where used for operational purposes, functional earth connections for data and signaling must be insulated from protective earthing conductors and should only be connected to protective earthing at one point, normally at the main earthing terminal or bar. Care must be taken to avoid unintended connections between systems. This clause notes that the color identification for functional earthing conductors has not been detailed, and green or green and yellow must not be used. Clause 5.2.3 for combined protective and functional purposes. When protective and functional purposes are combined, the protective requirements must take priority. Clause 5.3 Earthing system parts. Clause 5.3.1 General. This clause lists the parts that make up the protective earthing arrangement for an electrical installation connected to the MEN system. It includes protective earthing conductors that connect exposed conductive parts, the main earthing conductor, the main earthing terminal or bar, the MEN connection between the earthing terminal and the supply neutral bar, the earth electrode, and equipotential bonding of extraneous conductive parts. It also notes that figures 5.1 and 5.2 show examples of these parts. The parts of the earthing system must comply with clauses 5.3.2 to 5.3.7. Clause 5.3.2 Earthing conductor material and type. Clause 5.3.2.1 Conductor material. Clause 5.3.2.1.1 Copper conductors. Copper earthing conductors must be high conductivity copper, and may be stranded, circular braided, or solid with a cross-sectional area of at least 10 square millimeters and a thickness of at least 1.5 millimeters. Exceptions allow smaller solid conductors where a cable standard permits it. This clause also does not apply when copper cable components are deemed to be earthing conductors under Clause 5.3.2.2. Clause 5.3.2.1.2 Aluminium conductors. Aluminium may be used as an earthing conductor if it meets the following conditions. Conductors of 10 square millimeters or less must be solid. At least 16 square millimeter conductors must be used for main earthing conductors. Terminations must be satisfactory, and corrosion must be prevented. Aluminium conductors must not be installed underground or in damp areas. An exception allows aluminium earthing conductors underground or in damp areas when designed and suitable for that use. Clause 5.3.2.1.3 Other materials. Other materials may be used if their resistance is no greater than the copper conductor specified in Clause 5.3.3, and their corrosion resistance is not inferior to the required standard. Clause 5.3.2.2 Conductor type. Protective earthing conductors may be conductors that comply with Clause 5.3.2.1 and are installed separately, or conductors installed in a common enclosure with live conductors, or conductors in multi-core cables or busbars. Additional types may include conductive conduit, tube, trunking or similar wiring enclosures, conductive sheaths, armors or screens of cables, conductive framework used to mount equipment, and catenary wires for supporting cables. Sprinkler pipes or pipes carrying gas, water, flammable liquid, or non-electrical service conduits must not be used as earthing conductors. This does not prevent bonding these systems to conductive electrical service enclosures as required by Clause 5.6. Main earthing conductors must comply with Clause 5.3.2.1. Clause 5.3.2.3 Special conditions. This clause explains conditions where the conductor types listed earlier may be used as protective earthing conductors. Conductive conduit or tubing may be used when the electrical equipment is supplied by live conductors within the enclosure, and when screwed conduit is directly connected by threads or lock nuts to the equipment. Conductive sheaths, armors and screens of cables may be used when the electrical equipment is supplied by live conductors within those cables. An exception allows the use of a MIMS cable sheath as a main earthing conductor when all protective earth conductors associated with it belong to the same circuit. Conductive framework may be used when exposed conductive parts are mounted on the framework and in effective contact with it, and when protective earthing conductors are connected to it. Hinged conductive components, such as cubicle doors, may be used when the fixed component is connected to a protective earthing conductor and the hinged and fixed parts are connected by a protective earthing means. Moving components may be used when they are directly connected to a protective earthing conductor and when electrical contact between fixed and moving parts is effective. Catenary wires may be used when they have at least 7 strands, are supported by suitable anchorages, meet the minimum cross-sectional area, have resistance as required by Clause 5.3.3, and are identified as earthing conductors in accordance with Clause 3.8.3.4. Clause 5.3.2.4, Insulation. Earthing conductors must have insulation. Exceptions include aerial conductors, flat-braided conductors, bus bars, sheaths of MIMS cable, conductive framework and wiring enclosures that are earthing conductors, copper earthing conductors buried directly in the ground as allowed in Clause 5.5.5.5, and catenary wires. Clause 5.3.2.5, Identification. Insulated earthing conductors must be identified in accordance with Clause 3.8. Clause 5.3.3, Earthing conductor size, cross-sectional area. Clause 5.3.3.1, Protective earthing conductors. Clause 5.3.3.1.1, General. This clause explains that the cross-sectional area of a protective earthing conductor must provide enough capacity to carry prospective fault current for the required disconnection time, must have appropriate earth fault loop impedance, must have suitable mechanical strength and resistance to external influences, and must allow for any deterioration of conductivity in parts of the earthing system that are not cables or parts of cables. Clause 5.3.3.1.2, Selection. The cross-sectional area of a protective earthing conductor must be determined either from Table 5.1 based on the size of the largest active conductor supplied, or by calculation as described in Clause 5.3.3.1.3. Exceptions include the minimum size needed for earthing exposed conductive parts associated with unprotected consumers' mains, aerial earthing conductors which must comply with Clause 5.3.3.3, and earthing conductors and cables or flexible cords which must comply with Clause 5.3.3.4. Notes state that the installation must allow terminals to accept the protective earthing conductors, and that calculation may be necessary if the phase conductors are selected based on short-circuit current. When several conductors form the active conductor in parallel, the earthing conductor must be selected in relation to the total cross-sectional area of the largest active conductor to be protected. Where the total cross-sectional areas do not match a standard size in Table 5.1, the next larger size must be chosen. The minimum cross-sectional area of any wiring enclosure, cable component, framework or catenary wire used as an earthing medium must not exceed the impedance allowed for a copper earthing conductor of the required size. Clause 5.3.3.1.3, Calculation. The minimum cross-sectional area determined by calculation must not be less than the value found by the formula S equals the square root of I squared times T divided by K squared. S is the cross-sectional area of the protective earthing conductor, I is the fault current that would operate the overcurrent device, T is the disconnection time, and K is a factor depending on the conductor material, insulation, and final temperatures. Notes explain that K values are given in the ASNZS 3008.1 series, and examples appear in that standard. If the equation produces a non-standard size, the nearest higher standard size must be used. Clause 5.3.3.2, Main earthing conductor. Where the main earthing conductor connects the main earthing terminal to an electrode, it must be selected from Table 5.1 based on the largest active conductor of the consumer's mains. The copper main earthing conductor must not be less than 4 square millimeters and not more than 120 square millimeters. An exception allows the size to be determined differently when double insulation is maintained between the point of supply and submains or final subcircuits, so long as the minimum size is related to the largest outgoing submain or final subcircuit. Another condition applies where the consumer's main's cross-sectional area is larger than needed for maximum demand. In that case, the minimum size may be based on the largest cable required to carry maximum demand. When the conductor connects the main earth bar to an earth bar or link inside a substation, its size must be based on prospective fault current and duration. Clause 5.3.3.3 Aerial earthing conductors. The minimum size of an aerial earthing conductor must be selected in accordance with Clause 5.3.3.1 and must not be less than the sizes given in Table 3.12.2.1, with type and length considered. Clause 5.3.3.4 Earthing conductors and cables, flexible cables or flexible cords. The minimum size of an earthing conductor within a cable or cord must be selected according to Clause 5.3.3.1.2 and must also meet the requirements for the type of cable or cord. Single core and flexible cords must have at least 2.5 square millimeters for the earthing conductor, except that short lengths inside a multicore cable may be as small as 1 square millimeter. Multicore cables must have at least 1 square millimeter for the earthing conductor. For multicore flexible cords, the minimum size must not be less than the largest active conductor in the cord, provided that the largest active conductor is more than 0.5 square millimeters and less than 2.5 square millimeters, and the cord is used to supply a handheld or portable appliance. Screen and drain wires must have a cross-sectional area selected according to Clause 5.3.3.1.2, and also at least the minimum required for a protective earthing conductor. An exception applies where the screen or drain wire is separated from live conductors by double insulation or equivalent. Clause 5.3.4 Main earthing terminal, connection or bar. This clause states that every electrical installation must have a main earthing terminal, connection or bar at the main switchboard. All protective earthing conductors, the main earthing conductor, the MEN connection, equipotential bonding conductors, and functional earthing conductors if required, must be connected directly or indirectly to that terminal or bar. A note explains that the main earthing terminal may be a soldered connection. Clause 5.3.5 MEN connection. Clause 5.3.5.1 General. In every electrical installation there must be an MEN connection, also called the MEN link, located at the main switchboard. Its function is to connect the earthing system inside the installation to the supply neutral conductor. This is done by connecting from the main earthing terminal or bar to the earthing terminal on the main neutral link. Exceptions allow the MEN connection to be made at an earth bar or link inside an owner or user-operated supply substation, or at a distributor neutral bar or link inside the installation when required by the distributor, or through an earthing conductor or terminal provided by the distributor. Clause 5.3.5.2 Size. The MEN connection must be a conductor that complies with Clause 5.3.2 and must have a cross-sectional area capable of carrying the maximum current that may be required during short-circuit conditions. The minimum size must be not less than the current carrying capacity of the main neutral conductor, or, for heavy current switchboards rated at 800 amperes or more per phase, must meet the requirements for a protective earthing conductor as determined from Table 5.1 or by calculation. An exception states that the minimum size of the MEN connection does not need to exceed the main earthing conductor where short-circuit protection is provided on the supply side of the consumer's mains, or where the earthing of an enclosure containing consumer's mains without short-circuit protection on the supply side is made by connection directly to the neutral bar or link in accordance with Clause 5.5.3.5.3, or where double insulation of the consumer's mains conductors is maintained up to the terminals of the service protective devices and short-circuit protection is provided by those devices. Clause 5.3.5.3 Identification. Where the MEN connection is insulated, the insulation must be colored green or green and yellow, in accordance with Clause 3.8. Clause 5.3.6 Earth electrodes. Clause 5.3.6.1, General. The connection of the earthing system to the general mass of Earth must be made using an earth electrode. No specific resistance value is required for an installation connected to an MEN system, but the impedance of the combined earthing system must meet the earth fault loop impedance requirements of Clause 5.7. As ASNZS 3017 provides guidance on measurement methods. Clause 5.3.6.2, Types. Earth electrodes must be selected to resist corrosion and to have suitable mechanical strength, and the nature of the soil and environmental conditions must be considered. Earth electrodes must be of a type listed in Table 5.2 and installed in accordance with that table. An exception allows conductive reinforcement in concrete foundations, either embedded directly in the soil or in contact with the ground beneath a floor slab where no insulating barrier exists. Clause 5.3.6.3, Installation. Vertical type earth electrodes must be driven to a minimum depth of 1.2 meters in Australia and 1.8 meters in New Zealand. Strip type electrodes must be buried in a horizontal trench with at least 0.5 meters of cover and with a minimum length of 3 meters in Australia and 7.5 meters in New Zealand. Clause 5.3.6.4, Location. Earth electrodes must be installed where they maintain effective contact with moist soil, either external to the building where exposed to weather or in areas where soil conditions keep moisture levels high. The electrode must be separated from buried conductive enclosures such as services for water, gas, telecommunications or flammable liquids so that electrochemical effects do not cause damage. The main earthing conductor connection to the electrode must be accessible in accordance with Clause 5.5.1.2. The location of the electrode must be identified at the main switchboard. Clause 5.3.7, Functional earthing conductors. Functional earthing conductors provided solely to ensure the correct operation of equipment, or to allow stable operation of electrical installations, do not need to comply with protective earthing requirements. Where functional and protective purposes are combined, the protective requirements take priority. It is recommended that the functional earthing connection is independent from the protective earthing system unless the manufacturer's instructions require otherwise, which would limit the connection to the main earth connection point. A note explains that where a clean earth is specified, the manufacturer must be consulted to determine the correct arrangement. Clause 5.4, Earthing of equipment. Clause 5.4.1, General. Clause 5.4.1.1, Exposed conductive parts. Exposed conductive parts of electrical equipment must be earthed whenever the equipment is installed or could be operated in an earthed situation, or when the equipment is not in an earthed situation but an exposed conductive part is electrically continuous with an extraneous conductive part that is located in an earthed situation. An exception applies where the wiring of the equipment meets certain provisions. Protection by use of double insulation allows equipment complying with ASNZS 3100 to not require earthing. Where cables enter equipment and have double insulation, they must be arranged so accessible conductive parts cannot be contacted, and the cables must be of a type that provides double insulation. Fasteners such as screws or nails must not be able to penetrate the insulation where the cable may move during maintenance or operation. Internal equipment wiring must be arranged so that if one conductor detaches from its termination, neither it nor any other conductor can come into contact with accessible conductive parts. Conductors must be insulated, protected or secured, and the tying or lacing of conductors to prevent movement is considered acceptable. Equipment supplied by electrical separation under Clause 7.4 must not have its exposed conductive parts earthed. Exposed conductive parts supplied by an SELV or APELV system do not require earthing if they comply with Clause 7.5. Clause 5.4.1.2, Conductive building materials. Conductive building materials must be earthed as required by Clause 5.4.6. Clause 5.4.1.3, Connection of electrical equipment to earth. Equipment that needs to be earthed must be arranged for connection to protective earthing conductors in the form of cables, cords, busbars or similar forms of current-carrying material, or to another earthing medium such as conductive parts of cables, wiring enclosures or structural framework in accordance with Clause 5.3.2. Equipotential bonding must be arranged in accordance with Clause 5.6. Clause 5.4.2. Socket outlets. Every socket outlet must have its earthing contact earthed. Exceptions include a socket outlet supplied as a separated circuit where the earthing contact must be bonded to the protective bonding system according to Clause 7.4, and socket outlets supplied from an extra low voltage circuit under Clause 7.5.1.0, which must not have an earthing contact. Clause 5.4.3. Lighting points. A protective earthing conductor connected to a terminal or insulated and enclosed must be provided at every lighting point, including those supplied by ELV lighting systems. Exceptions apply where luminaires are in Zone 0 of swimming and spa pools under Clause 6.3.4.5, or in Zone 0 of fountains and water features under Clause 6.4.4.5. Another exception applies to festoon-type lamp holders of the all-insulated type, to lighting points where the luminaire is attached by screw connection in accordance with Clause 5.3.2.3, to lighting points outdoors on a non-conductive pole not in an earthed situation, and to ELV lighting points. Clause 5.4.4. Luminaires. Exposed conductive parts of luminaires must be earthed. Exceptions apply where earthing is not required under Clause 5.4.1, or where a protective earthing conductor is not required under Clause 5.4.3, or where the luminaire outdoors is on a non-conductive pole and not in an earthed situation, or where the luminaire is supplied at ELV according to Clause 7.5. Clause 5.4.5. Conductive supports for aerial conductors. Conductive poles, posts, struts, brackets, stay wires and other conductive supports for low-voltage aerial conductors must be earthed. Exceptions include supports that are effectively and permanently separated from all conductors by double insulation, including the use of XLPE Type X-90 UV cable with insulated strain clamps and insulated connectors. Another exception covers supports effectively separated from aerial conductors by insulators or insulating mounts, provided spacing between conductors and the support meets the requirements for single-core or multi-core conductors. Conductive supports beyond arm's reach and separated from conductive equipment, structures or metalwork by sufficient clearance or creepage distance also require no earthing. Supports attached to conductive poles fitted with a robust insulator must not need earthing if the support is isolated from the pole. Clause 5.4.6. Structural metalwork including conductive building materials. Clause 5.4.6.1. General. Parts of structural metalwork, including conductive building materials, must be earthed where they could make contact with live parts of electrical equipment or unsheathed cables, or where double insulation of cables in contact with structural metalwork is not permanently maintained. Clause 5.4.6.2. Domestic electrical installations. Structural metalwork forming the frame of a dwelling must be earthed. Clause 5.4.6.3. Connection to protective earthing conductors. Structural metalwork may be earthed by connecting a protective earthing conductor at one point, provided the resistance between the earth bar and the metalwork does not exceed 0.5 ohms. Clause 5.4.7. Submersible pumps. The exposed conductive parts of a submersible pump must be earthed by means of a protective earthing conductor that is terminated at the pump motor. The termination must be made in a way that prevents moisture ingress and mechanical damage. This may be done by terminating the conductor at a terminal inside a housing or at an internal or external constructional component according to Clause 5.5.6.6.2. Clause 5.4.8. Variable frequency devices. Devices that create high-frequency currents in the protective earthing system may create touch voltages harmful to people and livestock. Notes explain that touch voltages may reach 100 volts and may not be detectable using normal 50 Hz test instruments, and attention is drawn to safety requirements for electronic equipment in AS 62103. Clause 5.5. Earthing arrangements. Clause 5.5.1. Main earthing conductor. Clause 5.5.1.1. Arrangement. An earthing conductor, known as the main earthing conductor, must be taken from the main earthing terminal or bar at the main switchboard to an earth electrode that complies with clause 5.3.6. The conductor must be run in as direct a manner as possible and must not be directly connected to any accessory, luminaire or appliance. Exceptions allow the main earthing conductor to be taken to an earth bar or link inside a customer's substation forming part of the installation, or to an earthing conductor or terminal provided by the distributor, or if required by the distributor, to a distributor's neutral bar or link inside the installation. A note explains that a distributor's earthing conductor may include a special earthing conductor, the sheath of a supply cable, or a neutral bar or link at a substation. Clause 5.5.1.2, Connection to earth electrode. The main earthing conductor must be connected to the earth electrode in a way that is visually accessible for inspection and testing. Notes explain that when an underground pit with a cover is needed for accessibility, adequate space for test leads must be provided, and when reinforcing steel is used as the earth electrode, the test point may be provided at the main earthing electrode position. The connection must be made using a method that provides adequate electrical conductivity in accordance with the manufacturer's specification, must provide protection against mechanical damage likely to occur at the location in accordance with clause 5.5.5.2, and must be protected against corrosion in accordance with clause 5.5.5.3. A note refers to clause 5.3.6.4 for the location of earth electrodes. Clause 5.5.1.3, Labeling. The main earthing conductor must have a permanent label at the connection to the earth electrode with a legible warning stating main electrical earthing conductor, do not disconnect. An exception states that this requirement does not apply where the method of connection does not allow disconnection. Clause 5.5.1.4, Resistance. The resistance between the main earthing terminal bar and the earth electrode, including the connection, must not be more than 0.5 ohms. Clause 5.5.2, Protective earthing conductors. Clause 5.5.2.1, Arrangement. All submain and subcircuit protective earthing conductors must be connected to the main earthing conductor or to another point on the earthing system that is connected to the main earthing conductor. The connection may be made at an earthing terminal or bar at the main switchboard provided specifically for earthing conductors and connected directly to the main earthing conductor, or at any point on the main earthing conductor, or at an earthing terminal or bar at a distribution board for protective earthing conductors arranged to comply with clause 5.5.2.2. or at any point on a protective earthing conductor that provides earthing facilities at a distribution board arranged to comply with clause 5.5.2.2. Notes mention examples in Figure 5.3 and refer to clause 5.5.3.1 for outbuildings where a separate MEN installation is required. Clause 5.5.2.2, Restricted connections. Clause 5.5.2.2.1, Circuits. A protective earthing conductor incorporated inside the same cable sheath or wiring enclosure as associated live conductors must only be used for equipment supplied from the same circuit. An exception notes that an unenclosed common protective earthing conductor may still serve multiple circuits. Clause 5.5.2.2.2, Earthing of equipment. A protective earthing conductor taken from a distribution board in accordance with clause 5.5.2.1 must not be used to earth equipment supplied from another switchboard. Clause 5.5.2.2.3, Earthing facilities for distribution boards. A protective earthing conductor originating at a distribution board in accordance with clause 5.5.2.1 must not be used to provide earthing facilities for another distribution board. Exceptions allow this where earthing facilities originate from the same distribution board as the associated active conductors, or a common protective earthing conductor connected to the main earthing conductor under clause 5.5.2.1 can supply earthing facilities to several distribution boards, provided the continuity of the protective conductor is not dependent on a terminal at a distribution board and the connection between the common protective conductor and any branch protective conductor is direct. Clause 5.5.3, Particular methods of earthing. Clause 5.5.3.1 Outbuildings. All parts of an outbuilding installation that require earthing under Clause 5.4 must be earthed by one of two methods. The first method is connection to the electrical installation earthing system, where the outbuilding earthing system is connected to a protective earthing conductor that is connected in accordance with Clause 5.5.2.1. The second method is a separate MEN installation, where the outbuilding earthing system is connected to the submain neutral conductor supplying the outbuilding, and in this case the neutral supplying the outbuilding is a PEN conductor. The outbuilding is treated as a separate installation and must meet additional requirements. There must not be more than one MEN connection in any outbuilding. The distribution board in the outbuilding is regarded as a main switchboard for making the MEN connection. The earthing conductor between the distribution board and the earth electrode is regarded as the main earthing conductor for the outbuilding. The submain supplying the outbuilding must be run directly from the main switchboard or routed through distribution boards in other outbuildings to only one distribution board inside the outbuilding. Where the PEN conductor supplying the outbuilding runs through the main switchboard and other distribution boards, the terminals on those boards must not be used for continuity of the PEN conductor. The PEN conductor supplying the distribution board must not be connected to any earthing or equipotential bonding conductor or to conductive pipes or structural metal. A note explains that particular care is required where conductive pipes and similar services run between buildings, as these could otherwise create a parallel earth and neutral path. Clause 5.5.3.2 Wiring systems. Conductive wiring enclosures must be earthed at the switchboard or accessory where the wiring originates. Conductive sheaths, armors or screens of cables or cords must also be earthed at the point where the cable or cord originates. Clause 5.5.3.3 Earthing of electrical equipment supplied by flexible cord or flexible cable. Exposed conductive parts of equipment supplied by flexible cord or cable must be earthed by a protective earthing conductor incorporated with the associated live conductors. Exceptions apply where a conductive screen or braid is separated from live conductors by double insulation and is sheathed or covered with non-conductive material, or where cable sheaths, armors or screens do not require earthing under Clause 5.4.1. Clause 5.5.3.4 Switchboards. Electrical equipment mounted on the conductive framework of a switchboard must be earthed under Clause 5.3.2.3. Clause 5.5.3.5 Unprotected consumers' mains. Exposed conductive parts associated with consumers' mains not provided with short-circuit protection on the supply side must be earthed by a conductor with a current carrying capacity not less than that of the main neutral conductor. This conductor must connect to the main neutral conductor or bar, or to the main earthing terminal or bar, in which case the cross-sectional area of the MEN connection must not be less than that of the main neutral conductor. Notes explain that double insulation maintained up to the supply terminals of the protective devices may remove this requirement, and a system designed to provide double insulation for aerial conductors would include XLPE type X-90 UV cable with insulated strain clamps and insulated connectors to ASNZS 4396. Exposed conductive parts associated with consumers' mains include switchboard cases, surrounds and enclosures, wiring enclosures, boxes and accessories, and supports for aerial conductors. Clause 5.5.4 Continuity. Clause 5.5.4.1 General. Earthing conductors must be protected against mechanical and chemical deterioration and electrodynamic forces. Star washers and similar devices that cut through paint or coatings may be used to ensure earth continuity across bolted or clamped joints between metal panels or framework with coated surfaces. Clause 5.5.4.2 Conductive wiring enclosures. Conductive wiring enclosures used as an earthing medium must be electrically continuous and must meet the impedance requirements of Clause 5.7. Clause 5.5.4.3 Conductive sheaths, armors and screens of cables. Conductive sheaths, armors and screens of cables and associated fittings must be mechanically and electrically continuous, and their impedance must meet the requirements of Clause 5.3.3. Clause 5.5.4.4 Connecting devices. Where equipment is connected through a plug, socket outlet or similar device, exposed conductive parts must be connected to earth automatically before live connections are made, and must be disconnected automatically only after live connections are broken. Clause 5.5.5 Installation. Clause 5.5.5.1 General. Earthing conductors and other earthing means must be installed to provide adequate protection against mechanical damage, interference and chemical deterioration. A note states that in areas of high lightning activity, ASNZS 1768 should be considered. Clause 5.5.5.2 Protection against mechanical damage. Earthing conductors must be protected against displacement or cutting by clamps, clips, saddles or similar devices that do not pass between strands of the conductor or damage it, by metallic barriers or robust materials, or by installing in a wiring enclosure per Clause 3.10.2. Clause 5.5.5.3 Protection against corrosion. Earthing conductors and fittings must be protected against corrosion caused by moisture or dissimilar metals. Installations in underground or damp locations must be sealed to prevent moisture entry and must use corrosion-resistant material. Installations exposed to weather must be constructed or protected to prevent moisture affecting the conductor. Clause 5.5.5.4 Aerial earthing conductors. Aerial earthing conductors must be supported in accordance with Clause 3.12.5 and identified in accordance with Clause 3.8.3.4. Clause 5.5.5.5 Buried earthing conductors. Bare or insulated conductors buried directly in the ground or installed in underground enclosures must meet the mechanical protection requirements for sheathed conductors under Clause 3.11. Bare earthing conductors must be copper not less than 25 square millimeters. Earthing conductors passing through a wall or partition must not be considered buried. Clause 5.5.6 Connections. Clause 5.5.6.1 Conductors. Connections in earthing conductors must comply with Clause 3.7. Clause 5.5.6.2 Constructional components. The exposed conductive parts of electrical equipment may be earthed by connecting a protective earthing conductor to a constructional bolt, stud, screw or similar terminal arrangement that forms part of the equipment. The terminal must be mechanically and electrically continuous with the exposed conductive part. The protective earthing conductor must be removable without reducing the effectiveness of the bolt, stud or screw, and without affecting the relative rigidity of the equipment. A stud that also secures a terminal cover may be used if it meets these conditions. Any covers or parts that must be removed to access terminals or adjust the equipment must not disturb or reduce the effectiveness of the earthing connection. A bolt, stud or screw used for earthing must not be used to fix the equipment in place or adjust its position. Clause 5.6 Equipotential bonding. Clause 5.6.1 General. Equipotential bonding is intended to reduce risks created by voltage differences between exposed conductive parts of equipment and extraneous conductive parts. Such voltage differences may arise from a fault external to the installation, or on incoming extraneous conductors such as water or gas pipes, or in the supply neutral. Distribution system load current can also cause voltage in the soil, such as around swimming pools. Telecommunications system voltages, lightning discharges or switching surges inside the installation or on incoming conductors may also create voltage differences. Clause 5.6.2 Arrangement. Clause 5.6.2.1 General. Equipotential bonding arrangements must comply with clauses 5.6.2.2 to 5.6.2.6 to avoid voltage differences between the electrical installation earthing system and any conductive piping, including taps, that may be in contact with the mass of earth. Additional equipotential bonding may be required for patient areas in hospitals, medical and dental practices and dialyzing locations as per ASNZS 3003. Explosive atmospheres under Clause 7.7, telecommunications installations under ASNZS 3050, film, video and television sites under ASNZS 4249, photovoltaic arrays under ASNZS 5033, general access floors under AS 4154, generating systems under Clause 7.3, and separated circuits under Clause 7.4. Clause 5.6.2.2, conductive water piping. Conductive water piping that is installed and accessible inside the building and is continuously conductive from inside the building to a point of contact with the ground must be bonded to the electrical installation earthing system. The bonding conductor must be connected as close as practicable to the point where the piping enters the building. The main earthing conductor may continue past the earth electrode connecting device to form the equipotential bonding connection, but a separate connection to the earth electrode does not meet this clause. Any conductive path through an item of equipment, such as a water heater, is included. Clause 5.6.2.3, Other conductive piping systems. Conductive piping systems associated with fire sprinklers, gas, water or flammable liquid that are unavoidably in contact with exposed conductive parts of wiring enclosures, cable components or other electrical equipment must be connected by an equipotential bonding conductor. Bonding is not required if the piping system is effectively earthed through equipment such as water heaters connected to electric hot water systems. Clause 5.6.2.4, Conductive cable sheaths and conductive wiring enclosures. The conductive sheath, armor or wiring enclosure of conductors operating above extra low voltage must be bonded to any conductive piping containing flammable agents, such as gas or oil, where they come into contact. The bonding must prevent appreciable voltage differences at contact points. Where bonding cannot be achieved because the conductive wiring enclosure must be separated from non-earthed conductive piping, the conductive sheath, armor or wiring enclosure must maintain a separation of 25 mm in air or 6 mm of durable insulating material. Clause 5.6.2.5, Showers and bathrooms. Any conductive reinforcing in a concrete floor or wall of a room containing a shower or bath must be bonded to the earthing system of the electrical installation. The equipotential bonding conductor must comply with Clause 5.6.3 and be connected between the reinforcing and any part of the earthing system. This requirement avoids voltage differences between reinforcing material and electrical appliances or incoming extraneous conductors. Reinforcing mesh laid in the floor and connected to the bonding conductor may be used. Conductive tie wires used in reinforced concrete are considered an adequate electrical bond. If the reinforcement is electrically continuous, one connection point to the bonding conductor is sufficient. Clause 5.6.2.6, Swimming and spa pools. Clause 5.6.2.6.1, Electrical equipment. The exposed conductive parts of any electrical equipment in a classified pool zone must be equipotentially bonded. Any exposed conductive parts of equipment that are not separated from live parts by double insulation and that contact the pool water must also be bonded, including equipment used for circulation or filtering. Clause 5.6.2.6.2, Conductive fixtures and fittings. Any conductive fittings within or attached to the pool, such as pool ladders and diving boards, must be equipotentially bonded. Fixed conductive parts within arm's reach of the pool edge must also be bonded, except fittings smaller than 100 mm in any dimension. Clause 5.6.2.6.3, Conductive pool structures. Where the pool structure is conductive, such as reinforcing metal in the pool shell or deck, all extraneous conductive parts must be bonded to the equipotential bonding connection point. If any items described in earlier clauses require equipotential bonding, the bonding must extend to the conductive pool structure. Clause 5.6.2.6.4, Equipotential bonding conductor connection point. A bonding connection point must be provided within the swimming or spa pool location for connecting all conductive parts requiring bonding. It must be positioned to allow access for connections, marked on the switchboard that supplies the pool circuits, be suitably designed, and protected against mechanical damage and corrosion. Clause 5.6.2.7, Telephone and telecommunication earthing systems. The telephone and telecommunication earthing system may be connected to the electrical installation earthing system to reduce voltage risks between the two systems. If directly connected, It must be connected to an enclosed terminal provided for the purpose, or directly to the earth electrode by an independent connecting device. An enclosed terminal must be connected by a protective earthing conductor to the main earthing conductor or the earthing system described in Clause 5.5.2. The terminal must not be installed in a switchboard and must be in a convenient, accessible position. Clause 5.6.3, Bonding conductors. Clause 5.6.3.1, General. Bonding conductors must meet the same requirements as protective earthing conductors unless Clause 5.6.3.2 applies. Clause 5.6.3.2, Size. The size of equipotential bonding conductors must suit the bonding application. They must not be larger than needed for mechanical strength, but must be large enough to reduce earth fault loop impedance where necessary. A bonding conductor connected to conductive piping, sheaths or wiring enclosures must have a minimum cross-sectional area of 4 square millimeters. Shower, bathroom, swimming and spa pool bonding conductors must also be at least 4 square millimeters, except where the bonding conductor serves as an earthing conductor under Clause 5.3.3.4. Telephone and telecommunication bonding conductors must be at least 6 square millimeters. Clause 5.7, Earth fault loop impedance. Clause 5.7.1, General. Automatic disconnection of supply is used for fault protection and is based on disconnecting supply from the affected part of the installation within a time that keeps touch voltages at safe levels during an insulation fault. The required disconnection time depends on the characteristics of the circuit protective device and the impedance of the earthing system. Where the touch potential exceeds 50 volts AC or 120 volts ripple-free DC, the circuit protective device must disconnect supply within the required time. The impedance of the earthing system must be low enough so that the prospective fault current can operate the protective device within the specified time and touch voltage limits. Clause 5.7.2, Disconnection times. For a 230 volt supply, the maximum disconnection time must not exceed 0.4 seconds for final subcircuits supplying socket outlets with rated currents not exceeding 63 amps, handheld Class 1 equipment, or portable equipment intended for manual movement during use. For other circuits, a longer time may be used where it can be shown that people will not be exposed to unsafe touch voltages. The fault current must still be large enough to cause automatic disconnection within the required time. Clause 5.7.3, Earth fault loop. In a MEN system, the earth fault loop path includes the active conductor to the point of the fault, including supply mains, service line and consumers mains and any final subcircuits. It includes the protective earthing conductor, including the main earthing terminal or connection bar and the MEN connection. It also includes the neutral return path, consisting of the neutral conductor between the main neutral terminal or bar and the neutral point at the transformer, including supply mains, service line and consumers mains. It also includes the path through the neutral point of the transformer and the transformer winding. Clause 5.7.4, Impedance. The earthing system impedance and the operation of protective devices must be such that if a negligible impedance fault occurs anywhere between an active conductor and an exposed conductive part or protective earthing conductor, automatic disconnection of supply will occur within the required time. This requirement is met when the product of the earth fault loop impedance and the operating current of the protective device is less than or equal to the nominal supply voltage to earth. Notes explain that additional earthing may be needed in patient areas, that the return path includes both protective earthing and neutral conductors, that Appendix B provides a method for determining maximum fault loop impedance, and that guidance for measuring fault loop impedance is given in Appendix B. Clause 5.7.5, Supplementary equipotential bonding. If the earth fault loop impedance cannot be reduced enough for the protective device to disconnect supply within the required time, supplementary equipotential bonding of extraneous conductive parts and their connection to the earthing system may be used. Other measures, such as using an RCD with a lower operating current that meets the disconnection time requirement, may also be used. Clause 5.8, Other earthing arrangements. Where fault protection is provided by electrical separation, Protective earthing conductors and equipotential bonding conductors must be arranged in accordance with Clause 7.4. Earthing arrangements for certain systems should be independent. These include lightning protection, static electricity protection, radio frequency interference screened installations, information technology installations, explosion protection systems, and cathodic protection systems. If these systems are connected to the electrical installation earthing system, they must not reduce the integrity of the earthing system. A note explains that requirements for protective earthing and bonding for these systems may appear in other standards. That brings us to the end of Section 5. In this section we've looked at how earthing conductors are arranged, how equipment and structural parts are bonded, and how the earthing system helps protective devices clear faults within safe times. Understanding these ideas gives you a stronger picture of how electrical installations stay safe under fault conditions. When you're ready, we'll move on to the next section. Hi everyone, and welcome to this audiobook designed for the EWRB Electrician Regulation Exam. My name is Aria, and I work alongside Whit Roy as an electrical tutor. This audiobook explains the exam topics in simple spoken language, making it easier to understand and review anywhere, anytime. Before we get into the lesson, I want to explain what this audiobook actually is. This audiobook is not a word-for-word reading of ASNZS 3000. You must always refer to the real standard when you're doing electrical work or preparing for an assessment. What we do here is take the important ideas from the standard and rewrite them in simple spoken English. The goal is to make the rules easier to understand, easier to remember, and easier to revise, especially when you're listening on the go. So think of this audiobook as a learning guide, not a replacement for the actual standard. Alright, let's begin. Today we are moving into Section 6, Damp Situations, which is all about electrical work in places where water, moisture, or heat can create extra danger. In this section we look at baths and showers, swimming pools, spa pools, fountains, water features, saunas, refrigeration rooms, and areas that are regularly washed down or sanitized. All of these locations share one thing in common. The presence of water or high humidity reduces body resistance and makes electric shock far more likely. As we go through the clauses, we will see how the standard sets out zones around these areas, and how each zone has different requirements for protection, wiring systems, and the type of equipment that can be used. The goal of this section is to help you understand how to keep electrical installations safe when water and electricity are close together. Clause 6.1 General. Clause 6.1.1 Application. This clause explains that Section 6 sets the minimum standard for selecting and installing electrical equipment in places where water or high humidity is present. These are called damp situations. The idea is that any installation in these locations must meet this minimum level to satisfy Part 1 of ASNZS 3000. Clause 6.1.2 Selection and Installation. This clause explains that, on top of the rules in Sections 2 to 5, any electrical equipment used in damp situations must be chosen and installed so it performs certain functions safely. The first function is described in Item A. Item A says the equipment must provide enhanced protection against electric shock in places where water or high humidity increases the shock risk. The note explains that the increased shock risk comes from reduced body resistance and the greater chance of the body touching earth potential. The second function is in Item B. Item B says the equipment must provide adequate protection against damage that might reasonably be expected when water or high humidity is present. The note mentions that Appendix G describes the IP system for classifying degrees of protection for electrical equipment. The clause then states that the requirements for particular damp situations either add to, replace, or modify the general rules from other sections of the standard. If this section does not give a specific requirement for a situation, then the general rules from other sections still apply. This clause also lists the specific damp situations that the rules apply to. These include baths, showers, and other fixed water containers, swimming pools, paddling pools and spa pools or tubs, fountains and water features, saunas, refrigeration rooms, and sanitization and general hosing down operations. Clause 6.2, baths, showers and other fixed water containers. Clause 6.2.1, scope. This clause explains that the specific requirements in Clause 6.2 apply to electrical installations in places that contain a bath, a shower, or other fixed water containers, along with the surrounding zones. These are locations where the risk of electric shock is higher because the body resistance is reduced and there is a greater chance of contact with earth potential. The clause also explains that other fixed water containers include anything designed to hold water under normal conditions, but do not include accidental containers or areas that are not meant to hold water. The requirements in this clause are based on classifying zones around the water container. Barriers such as screens, doors, curtains, and fixed partitions that protect against spraying water may be used to limit the extent of the classified zone. Ceilings, with or without windows, as well as doors and floors that limit the extent of the room containing the bath, shower, or water container, also limit the associated zones. Because of the nature of these locations, some methods of protection against electric shock are not allowed. The notes explain that special requirements may be needed for baths used for medical treatment, that equipment installed behind a fixed panel that gives at least an IP4X degree of protection, and can only be accessed by removing the panel might not be considered in a classified zone, and that equipment recessed into a ceiling where all live parts are above the lower surface of the ceiling is considered outside any zone immediately below the ceiling. Another note explains that this clause may also apply in other situations, such as a full commercial safety washdown facility, or a self-contained eye wash basin with a fixed or flexible hose. Clause 6.2.2, classification of zones. Clause 6.2.2.1, baths and showers. This clause explains that 4 zones, called Zones 0, 1, 2, and 3, are used for classifying areas around baths and showers. Item explains Zone 0 as the interior of a bath or shower base, and notes that a shower base may be defined by either a raised hob or a depression in the floor. Item B explains that Zone 1 for a bath is limited by Zone 0, and by the vertical projection of the internal rim of the bath above Zone 0, and when the bath contains a shower, by a vertical plane 1.2 meters from the shower fixed plumbing connection, and in New Zealand also by a horizontal plane 2.25 meters above the floor, or by the height of the fixed plumbing connection if that height is greater than the horizontal plane. The note explains that a barrier at the shower connection height may be used to reduce the 1.2 meter dimension. Item C explains that Zone 1 for a shower is limited by Zone 0, by a vertical plane 1.2 meters from the shower fixed plumbing connection, and in New Zealand by a horizontal plane 2.25 meters above the floor, or by the height of the fixed plumbing connection if that is higher than the horizontal plane. The note again explains that a barrier may reduce the 1.2 meter dimension. Item D explains that Zone 2 is limited by the vertical plane around Zone 1 and another vertical plane 0.6 meters external to Zone 1, and by the floor and a horizontal plane 2.25 meters above the floor. Item E explains that Zone 3 is limited by the vertical plane around Zone 2 and another vertical plane 2.4 meters external to Zone 2, and by the floor and a horizontal plane 2.25 meters above the floor. Clause 6.2.2.2, other fixed water containers. This clause explains that for fixed containers other than baths or showers, only Zones 0 and 2 are used. Item E explains that Zone 0 is the interior of the container. Item B explains that Zone 2 for a container up to 45 liters with fixed water outlets is limited by a vertical plane 0.15 meters from the internal rim, and by a horizontal plane 0.4 meters above the container. Item C explains that Zone 2 for containers over 45 liters or with a flexible hose outlet is limited by a vertical plane 0.5 meters from the internal rim and by a horizontal plane 1.0 meters above the container. The notes explain that there is no Zone 1 or Zone 3 for these containers, and that a flexible hose water outlet example is a vegetable sprayer. Clause 6.2.3, protection against electric shock, prohibited measures. This clause explains that some methods of protection against electric shock must not be used. These include protection by means of obstacles in accordance with Clause 1.5.4.5, and protection by placing out of reach in accordance with Clause 1.5.4.6. Clause 6.2.4, Selection and installation of electrical equipment. Clause 6.2.4.1, Degree of protection required. The clause explains that electrical equipment installed in a classified zone must have at least the minimum specified degree of protection. Item A states that in Zone 0 the equipment must be IPX7. Item B states that in Zones 1 and 2 the equipment must be IPX5 in communal baths and showers, and IPX4 in other locations. Item C states that in Zone 3 the equipment must be IPX5 in communal baths and showers, and that there is no specific degree of protection required elsewhere. The note explains that guidance on selecting and installing equipment is provided in Table 6.1, but figures are skipped in this audiobook. Clause 6.2.4.2, Socket outlets. This clause states that socket outlets must not be installed within 0.3 meters of the floor in a bathroom, laundry, or similar area where the floor may become wet. It explains that Zone 0 and Zone 1 do not permit socket outlets. In Zone 2 a socket outlet must either be part of a shaver supply unit that meets ASNZS 3194, or be protected by an RCD with a fixed rating not exceeding 30 mA and enclosed in a cupboard that maintains enclosure protection during normal use. In Zone 3 a socket outlet must either be protected by an RCD rated not more than 30 mA, or be supplied individually as a separated circuit under Clause 7.4, or be supplied as an SELV or PELV system under Clause 7.5. Clause 6.2.4.3, Switches and other accessories. This clause explains that switches and accessories must not be installed within 0.3 meters of the floor of a bathroom, laundry, or similar area where the floor may become wet. For classified zones, the clause states that switches and accessories must not be installed in Zone 0. In Zones 1 and 2 they may be installed if they have the required degree of protection. Clause 6.2.4.4, Luminaires. This clause explains the requirements for luminaires installed in classified zones. In Zone 0 luminaires must be provided with the required degree of protection, designed and constructed specifically for use in the bath, shower, or water container, and supplied at a low nominal voltage not exceeding 12 volts AC or 30 volts ripple-free DC. For Zones 1, 2, and 3 luminaires must have at least the required degree of protection. An exception allows certain luminaires in Zone 2 even if they do not meet the normal protection requirement. These include Class 2 luminaires that need removal of a cover to access lamps, and luminaires supplied from outside Zone 2 by an SELV or PELV system. Clause 6.2.4.5, Other electrical equipment. This clause explains conditions for installing appliances and electrical equipment in classified zones. In Zone 0 the equipment must be designed specifically for use in a bath, shower, or water container, must have the required degree of protection, and must be supplied from a source outside Zone 0, at a nominal voltage not exceeding 12 volts AC or 30 volts ripple-free DC, and must be supplied as an SELV or PELV system. In Zones 1, 2, and 3 appliances and equipment must have at least the required degree of protection. Heating cable systems installed beneath the floor and intended for heating the location are permitted if they comply with Clause 4.10. Clause 6.2.4.6, Switchboards. This clause states that a switchboard must not be installed within any classified zone. Clause 6.3, Swimming pools, paddling pools and spa pools or tubs. Clause 6.3.1, Scope. This clause explains that the special requirements of Clause 6.3 apply to electrical installations in places that contain swimming pools, paddling pools, wading pools, and spa pools or tubs, along with their surrounding zones. These are locations where the risk of electric shock is increased because of reduced body resistance and a higher likelihood of the body contacting earth potential. The requirements are based on classifying zones around the water container. Ceilings, walls with or without windows, doors, barriers, and fixed partitions at or above 1.8 meters from the floor limit the extent of the room or area containing the swimming pool, paddling pool, spa pool, or tub. Fixed partitions that protect against spraying or splashing water also limit the zones. Because of the nature of these locations, some methods of protection against electric shock are not allowed. The clause explains that these requirements also apply to electrical installations in areas of natural waters such as lakes and gravel pits and coastal or similar areas, especially when used for swimming, paddling, and similar purposes. The note states that special requirements may be necessary for medical or large commercial use. Clause 6.3.2 Classification of zones. Clause 6.3.2.1 Swimming pools and paddling pools. This clause explains that 3 zones, called Zones 0, 1, and 2, apply to swimming pools and paddling pools. Item A explains that Zone 0 is the interior of the water container. Item B explains that Zone 1 is limited by Zone 0, by a vertical plane 2.0 meters from the internal rim of the water container, by the floor or occupied surface, and by the horizontal plane 2.50 meters above that surface. When the pool contains a diving board, springboard, starting block, or slide, Zone 1 also includes a vertical plane 1.50 meters around that equipment, and a horizontal plane 2.50 meters above the highest surface expected to be used. Item C explains that Zone 2 is limited by the vertical plane around Zone 1 and another parallel vertical plane 1.50 meters external to Zone 1, and by the occupied floor surface and a horizontal plane 2.50 meters above that surface. The clause notes that examples of these zones are shown in figures. Clause 6.3.2.2 Spa pools or tubs. Clause 6.3.2.2.1 General. This clause explains that spa pools or tubs with a water capacity not exceeding 500 liters must comply with Clause 6.2. A spa pool attached to a swimming or paddling pool is treated as an extension of that pool. The note explains that equipment behind a fixed panel that provides at least IP4X protection and requires tools to access may not be considered to be in a classified zone. Clause 6.3.2.2.2 Water capacity exceeding 5,000 liters. This clause states that the 3 zones 0, 1, and 2 are used for spa pools or tubs with a capacity greater than 5,000 liters. It also states that examples of the zones are shown in figures. Clause 6.3.2.2.3 Water capacity not exceeding 5,000 liters. This clause explains that 2 zones only, Zones 0 and 1, apply to spa pools or tubs with a capacity up to and including 5,000 liters. Item A states that Zone 0 is the interior of the water container. Item B states that Zone 1 is limited by a vertical plane 1.25 meters from the internal rim, and by the occupied floor or surface, and by a horizontal plane 2.50 meters above that surface. The clause notes that examples of these zones are shown in figures. Clause 6.3.3 Protection against electric shock. Clause 6.3.3.1 Prohibited measures. This clause explains that the following protection measures must not be used: protection by means of obstacles in accordance with Clause 1.5.4.5, and protection by placing out of reach in accordance with Clause 1.5.4.6. Clause 6.3.3.2 Supplementary equipotential bonding. This clause states that where electrical equipment in a classified zone must be earthed, all extraneous conductive parts in Zones 0, 1, and 2 must be bonded together by equipotential bonding conductors and connected to the protective earthing conductor of the electrical equipment in accordance with Clause 5.6.2.6. Clause 6.3.3.3 Voltage gradients. This clause explains that when electrical equipment is in contact with pool water, insulation failure may make a hazardous voltage appear in the water. A very low voltage is enough to present a hazard to people immersed. Protective measures may include locating the electrical equipment far from the pool with or plumbing made from non-conductive material, or installing metal grids or barriers in plumbing connections between the equipment and the pool and bonding them to the equipotential system, or using an RCD not exceeding 30 mA to protect circuits supplying Class 1 equipment. Clause 6.3.4 Selection and installation of electrical equipment. Clause 6.3.4.1 Degree of protection required. This clause explains the minimum degree of protection required. In Zone 0, IPX8. In Zone 1, IPX5. In Zone 2, IPX4. A note explains that guidance on selecting and installing equipment is provided in Table 6.2, though figures and tables are skipped here. Clause 6.3.4.2, Wiring Systems. This clause explains that wiring systems must prevent entry of moisture into any connection and must prevent water siphoning through any enclosure or cable. It also states that aerial conductors must not be installed over Zones 0, 1, or 2, and that other aerial conductors must meet Clause 3.12. Clause 6.3.4.3, Socket outlets. This clause explains that socket outlets must not be installed within 0.3 meters of any floor or horizontal surface where the floor or surface is likely to become wet. For classified zones, socket outlets must not be permitted in Zone 0. In Zone 1, socket outlets required for pool equipment connection are not permitted unless they meet certain conditions. They must have the required degree of protection, and must be located at least 0.45 meters above ground level and at least 1.25 meters from the internal rim, or beneath a fixed continuous horizontal barrier, at least 1.25 meters wide measured from the internal rim. They must either be supplied by a separated circuit under Clause 7.4, or as an SELV or PELV system under Clause 7.5, or be protected by an RCD not exceeding 30 mA, or be controlled by a switch that requires manual operation and is not automatic when inserting or withdrawing a plug. In Zone 2, socket outlets must have the required degree of protection and must be either supplied individually as a separated circuit under Clause 7.4, or supplied as an SELV or APELV system under Clause 7.5, or protected by an RCD not exceeding 30 mA. Clause 6.3.4.4, Switches and other accessories. This clause states that switches and accessories must not be installed in Zone 0, and in Zones 1 and 2 they must have the required degree of protection. Clause 6.3.4.5, Luminaires, appliances and other electrical equipment. This clause explains the installation conditions for luminaires and other equipment. In Zone 0 the equipment must be designed specifically for use in a swimming or spa pool, must have the required degree of protection, and must be supplied from an individual source outside Zone 0. The note explains that an individual source may be an isolation transformer or an isolation transformer with a secondary winding, provided the output meets Clause 7.5.3. Supply may be at not more than 12 volts AC or 30 volts ripple-free DC, or by an SELV or PELV system. Equipment in Zone 0 must not have a protective earthing conductor in accordance with Clause 5.4.3. In Zone 1 luminaires and equipment must have the required degree of protection and must be supplied as an SELV or PELV system, or be of Class 2 construction and fixed in position, or be Class 1 fixed equipment supplied from a circuit protected by an RCD not exceeding 30 mA. In Zone 2 equipment must have the required degree of protection and may be supplied as an SELV or APELV system, or as a separated circuit under Clause 7.4, or be of Class 2 construction, or be Class 1 construction supplied from a circuit protected by an RCD not exceeding 30 mA. Item D explains that in Zones 1 and 2, heating cable systems embedded in the floor and protected in accordance with Clause 4.10 are allowed. The note explains that using a purpose-made pump installation complying with ASNZS 60335.2.41 for each zone is deemed to comply with the clause. Clause 6.3.4.6, Switchboards. This clause states that a switchboard must not be installed within any classified zone. Clause 6.4, Fountains and water features. Clause 6.4.1, Scope. This clause explains that the requirements of Clause 6.4 apply to electrical installations associated with water containers of fountains and water features and their surrounding zones. These are locations where the risk of electric shock is increased because body resistance is reduced and the chance of contact with earth potential is higher. The requirements are based on classifying the zones around the water container. They are intended to protect electrical materials and equipment from the corrosive effects of chemicals used in fountains and water features, and to counter the increased risks when the electrical equipment is used in areas where the body may be partially immersed. The clause explains that these requirements do not need to apply where the depth of water does not exceed 0.3 meters, or where suitable means are provided to restrict people from entering the water. Ceilings, walls with or without windows, doors, and floors that limit the extent of a room or area containing a fountain or water feature, along with fixed partitions that protect against spraying or splashing water, also limit the associated zones. Because of the nature of these locations, certain methods of protection against electric shock are not permitted. Clause 6.4.2, Classification of Zones. This clause explains that two zones, called Zones 0 and 1, apply to fountains and water features. Item explains that Zone 0 is the interior of the water containers, including any recesses in their walls or floors or the interior of water jets or waterfalls. Item B explains that Zone 1 is limited by a vertical plane 2.0 meters from the internal rim, and by the floor or surface expected to be occupied by people with a horizontal plane 2.50 meters above that surface. When sculptures or decorative water containers form part of the fountain or water feature, Zone 1 extends to a vertical plane 1.50 meters around those sculptures, and a horizontal plane 2.50 meters above them. The clause notes that examples of these zones are given in figures. Clause 6.4.3, Protection against electric shock. Clause 6.4.3.1, Use of SELV. This clause states that where SELV is used, basic protection must be provided in accordance with Clause 7.5.5, regardless of the nominal voltage. Clause 6.4.3.2, Application of protective measures against electric shock. Clause 6.4.3.2.1, Supply. This clause states that electrical equipment must be earthed and protected by an RCD not exceeding 30 mA, or supplied at extra low or low voltage through an isolating transformer complying with ASNZS 61558 and not earthed, or supplied by other suitable measures that take into account the equipment construction, installation methods, and the physical location. Clause 6.4.3.2.2, Prohibited Measures. This clause states that protection by means of obstacles in accordance with Clause 1.5.4.5 and protection by placing out of reach in accordance with Clause 1.5.4.6 must not be used. Clause 6.4.4, Selection and installation of electrical equipment. Clause 6.4.4.1, Degree of protection required. This clause explains that equipment installed in the classified zone must have at least IPX8 in Zone 0 and at least IPX5 in Zone 1. Clause 6.4.4.2, Wiring systems. This clause explains that wiring systems for a fountain or water feature must use elastomer or thermoplastic insulated and sheathed copper cables or flexible cords suitable for immersion in the water. Where the wiring is subject to mechanical damage, it must be installed in a wiring enclosure. The system must prevent moisture entering any connection and must prevent water siphoning through any enclosure or cable. Clause 6.4.4.3, Socket outlets. This clause states that socket outlets are not permitted in Zone 0 or Zone 1. Clause 6.4.4.4, Switches and other accessories. This clause explains that switches and accessories, other than socket outlets, must not be installed in Zone 0. In Zone 1 they must be provided with the required degree of protection. Clause 6.4.4.5, Luminaires, appliances and other electrical equipment. This clause explains the installation requirements for luminaires and other equipment. In Zone 0 the equipment must be designed specifically for use in a fountain or water feature, must have the required degree of protection, and must be supplied from an individual source outside Zone 0. The note explains that an individual source may be an isolation transformer or an isolation transformer with a second winding, provided the output complies with Clause 7.5.3. The equipment must be supplied at a nominal voltage not exceeding 12 volts AC or 30 volts ripple-free DC, or must be supplied as an SELV or PELV system. Equipment in Zone 0 must not be provided with a protective earthing conductor in accordance with Clause 5.4.3. In Zone 1, luminaires and equipment must have the required degree of protection and must be supplied as an SELV or PELV system, or must be of Class 2 construction and fixed in position, or must be Class 1 construction fixed in position and supplied from a circuit protected by an RCD not exceeding 30 mA. The note explains that a purpose-made pump installation that complies with ASNZS 60335.2.41 for the relevant zone is deemed to comply with the clause. Clause 6.4.4.6, Switchboards. This clause states that a switchboard must not be installed within any classified zone. Clause 6.5, Saunas. Clause 6.5.1, Scope. This clause explains that the requirements of Clause 6.5 apply to electrical installations in rooms or enclosures containing heating equipment used only for sauna heating. The requirements are based on classifying zones around the sauna heater. Because of the nature of these locations, some methods of protection against electric shock are not permitted. Clause 6.5.2, Classification of Zones. This clause explains that 3 zones, called Zones 1, 2, and 3, apply to locations containing a sauna heater. Item explains that Zone 1 is the area containing the sauna heater, limited by a vertical plane 0.5 meters from the external edge of the heater, and by the floor or occupied surface, and by the cold side of the thermal insulation of the ceiling. Item B explains that Zone 2 is limited by the vertical plane around Zone 1 and the cold side of the thermal insulation of the sauna room or enclosure, and by the floor or occupied surface and a horizontal plane 1.0 meters above the floor. Item C explains that Zone 3 is limited by the vertical plane around Zone 1 and the cold side of the thermal insulation of the walls, and by the horizontal plane 1.0 meters above the floor and the cold side of the thermal insulation of the ceiling. The note explains that Zone 3 is directly above Zone 2. Another note states that examples are shown in figures. Clause 6.5.3, Protection against electric shock. Clause 6.5.3.1, Use of SELV. Where SELV is used, basic protection must be provided in accordance with Clause 7.5.5. Clause 6.5.3.2, Prohibited measures. This clause explains that protection by means of obstacles in accordance with Clause 1.5.4.5 and protection by placing out of reach in accordance with Clause 1.5.4.6 must not be used. Clause 6.5.3.3, Additional protection by RCD. This clause states that all equipment within the sauna room, except the sauna heater, must have additional protection by an RCD with a fixed residual current not exceeding 30 mA. Clause 6.5.4, Selection and installation of electrical equipment. Clause 6.5.4.1, Degree of protection required. This clause states that electrical equipment installed in a sauna room must have at least IPX4B or IP24. Clause 6.5.4.2, Requirements in classified zones. Item explains that in Zone 1 only electrical equipment belonging to the sauna heater may be installed. Item B states that Zone 2 has no special requirements concerning heat resistance. Item C states that in Zone 3 electrical equipment must be suitable for a minimum temperature of 125 degrees Celsius, and the conductors must withstand at least 170 degrees Celsius. Clause 6.5.4.3, Wiring systems. This clause explains that wiring systems should be installed outside the zones on the cold side of the thermal insulation. If the wiring is in Zones 1 or 3 on the warm side, it must be heat resistant in accordance with Clause 6.5.4.2. Metallic sheaths and conduits must not be accessible in normal use. A note states that suitable wiring systems include insulated unsheathed cables in non-metallic enclosures or sheathed cables. Clause 6.5.4.4, Socket outlets, switches and other accessories. This clause states that socket outlets and accessories must not be installed within a sauna room or enclosure. The exception is that switches and accessories forming part of the sauna heater may be located within the sauna room or enclosure. Clause 6.5.4.5, other equipment. This clause states that sauna heating appliances must be installed according to the manufacturer's instructions. Clause 6.5.4.6, Switchboards. This clause states that a switchboard must not be installed within any classified zone. Clause 6.6, Refrigeration rooms. Clause 6.6.1, Scope. This clause explains that the requirements of Clause 6.6 apply to locations such as freezers or cold rooms. Because of the nature of these locations, some methods of protection against electric shock are not permitted. Clause 6.6.2, Classification of zone. This clause explains that a single zone applies to refrigeration rooms. The whole area within the refrigeration room is classified. Clause 6.6.3, Protection against electric shock. Clause 6.6.3.1, Use of SELV. Where SELV is used, basic protection must be provided in accordance with Clause 7.5.5, whatever the nominal voltage. Clause 6.6.3.2, Prohibited measures. This clause explains that protection by means of obstacles in accordance with Clause 1.5.4.5, and protection by placing out of reach in accordance with Clause 1.5.4.6, must not be used. Clause 6.6.4, Selection and installation of electrical equipment. Clause 6.6.4.1, Degree of protection required. Electrical equipment permitted in a refrigeration room must have at least IPX4B or IP24. The note mentions that Clause 6.7 also applies to areas that are sanitized or hosed down. Clause 6.6.4.2, Wiring systems. Clause 6.6.4.2.1, General. This clause explains that wiring systems used for supply, control, and protection of equipment in a refrigeration room must not be affected by the room temperature, and must not have pockets or channels where moisture can collect or enter equipment. Wiring systems not related to refrigeration room equipment must not be installed in or pass through such rooms. Clause 6.6.4.2.2, Types permitted. This clause explains that certain wiring types are permitted. These include unenclosed sheathed cables including served MIMS cables, insulated unsheathed or sheathed cables within an enclosure that drains properly, and other wiring systems that are not inferior to those systems. A note explains that PVC insulated or sheathed cables may not be suitable where temperatures drop below approximately 0 degrees Celsius because of bending or vibration issues. Clause 6.6.4.2.3, Sealing. This clause explains that certain parts must be sealed with a compound that does not set hard. These include each wiring enclosure at any point where it passes from refrigerated to non-refrigerated space, and the entry points of cables into motors, luminaires, switches, or other equipment. Clause 6.6.4.3, Socket outlets, switches and other accessories. This clause explains that socket outlets, switches, and accessories must be designed so moisture cannot accumulate inside them. The requirement may be met by using socket outlets, switches, and accessories that have the required degree of protection and are permanently sealed. Clause 6.6.4.4, Luminaires and lamp holders. Clause 6.6.4.4.1, Luminaires. Luminaires must be sealed to prevent liquid or vapor entering, or designed so moisture cannot enter the lamp holder or other parts, and designed so that moisture retention is prevented in or on the fitting. Clause 6.6.4.4.2, Lamp holders. This clause explains that lamp holders must meet construction and location requirements. Construction must be of the all-insulated type or another type that prevents external metal parts from becoming live. Location requirements state that lamp holders must not be within 2.50 meters of the floor or ground when on a flexible pendant. Clause 6.6.4.5, Fixed appliances and motors. This clause explains that fixed appliances must be designed and constructed for the specific location. Electrical enclosures must provide a suitable degree of protection for the conditions where the equipment is installed. Clause 6.6.4.6, Heating elements and door seals. This clause states that heating elements must have additional protection by an ACD not exceeding 30 mA. Clause 6.6.4.7 Switchboards. This clause explains that a switchboard must not be installed in a refrigeration room. Clause 6.7 Sanitization and general hosing down operations. Clause 6.7.1 Scope. This clause explains that the requirements of Clause 6.7 apply where sanitization or general hosing down is carried out. Because of the nature of these locations, some protection methods are not permitted. The note explains that these requirements may apply in locations such as livestock processing, feed and fertilizer preparation, plant production, agricultural or horticultural processes such as dairies, drying, cleaning, pressing out, fermenting, butchering, meat processing, and car wash bays. Clause 6.7.2 Classification of zone. This clause explains that the classified zone is defined by the limits of any area likely to be affected by hosing. Item explains that where sanitizing or hosing down is throughout the area, the classified zone includes the whole space between the floor, walls, and ceiling. Item B explains that where hosing is limited to floor and walls, the classified zone includes any location from the floor or base or recess to a horizontal plane 2.0 meters above the floor, any wall within the area, and any location on the ceiling within 1.0 meters of a wall. Item C explains that if hosing is limited to the floor only, the zone includes any location from the floor or base or recess to a horizontal plane 1.0 meters above the floor. Clause 6.7.3 Protection against electric shock. Clause 6.7.3.1 Use of SELV. Where SELV is used, basic protection must be provided in accordance with Clause 7.5.5. Clause 6.7.3.2 Prohibited measures. This clause explains that protection by means of obstacles in accordance with Clause 1.5.4.5 and protection by placing out of reach in accordance with Clause 1.5.4.6 must not be used. Clause 6.7.4 Selection and installation of electrical equipment. Clause 6.7.4.1 General. This clause explains that electrical equipment within the classified zone must be suitable for the temperature and pressure of the fluids used during hosing or sanitization. Equipment must also be suitable when exposed to chemicals used in the sanitization process, in accordance with Clause 3.3. Clause 6.7.4.2 Degree of protection required. This clause explains that electrical equipment in the classified zone must have at least IPX5 where low or medium pressure hosing is used, and at least IPX6 where high pressure hosing is used. Clause 6.7.4.3 Electrical equipment. This clause explains that electrical equipment, including wiring systems, must not be affected by the hosing method, materials used, temperature, or pressure. It must be protected against moisture accumulation, and must not have channels or pockets where moisture can enter equipment. Clause 6.7.4.4 Switchboards. Switchboards in classified zones subject to sanitization or hosing down must have at least IPX6. That brings us to the end of Section 6. By now you should have a clear picture of how the standard manages electrical safety in damp, wet, and high-risk environments. You have heard how zones are defined around baths, showers, pools, fountains, saunas, refrigeration rooms, and areas that are washed down, and how each zone has specific rules for protection and equipment. These requirements can feel detailed, but they exist for good reason. Water and electricity are a dangerous combination, and getting the installation right makes a major difference to safety. When you work in any situation covered by this section, always take time to understand the zone you are working in, choose the correct equipment, and make sure the protection matches the environment. Alright, Section 6 is complete. When you're ready, we'll move on to the next part of the standard. Hi everyone, and welcome to this audiobook designed for the EWRB Electrician Regulation Exam. My name is Aria, and I work alongside Whit Roy as an electrical tutor. This audiobook explains the exam topics in simple spoken language, making it easier to understand and review anywhere, anytime. Before we get into the lesson, I want to explain what this audiobook actually is. This audiobook is not a word-for-word reading of ASNZS 3000. You must always refer to the real standard when you're doing electrical work or preparing for an assessment. What we do here is take the important ideas from the standard and rewrite them in simple spoken English. The goal is to make the rules easier to understand, easier to remember, and easier to revise, especially when you're listening on the go. So think of this audiobook as a learning guide, not a replacement for the actual standard. Alright, let's begin. Today we're going into Section 7, Special Electrical Installations, which looks at special electrical installations. These are the kinds of installations that need extra care because the conditions are different from normal work, or the risks are higher than usual. As we move through this section, we'll look at the rules that apply to safety services, to generation systems, to isolated supplies, to extra low voltage work, to high voltage systems, and to hazardous areas. Everything in this section has one purpose, and that's to make sure the installation stays safe when the environment or the equipment adds extra risk. Let's go through each clause step by step and explain what the standard is asking for. Clause 7.1 General. Clause 7.1.1 Application. This clause explains that the rules in Section 7 set the minimum standard for choosing and installing electrical equipment in special electrical installations. These minimum rules must still meet the safety outcomes required in Part 1 of this standard. Clause 7.1.2 Selection and Installation. This clause explains that each type of special installation has requirements that either change or replace the usual rules found in other sections of the standard. When Section 7 does not give a specific rule, the relevant rules from the other sections must be followed. The clause also states that Section 7 applies to electrical systems used for safety services, electricity generation systems, and installations using electrical separation. It applies to extra low voltage installations, high voltage installations, and installations in areas where an explosive hazard could occur. It also applies to electrical installations on construction and demolition sites, electromedical treatment areas, and relocatable installations and the sites they supply. It includes marinas and recreational boats, shows and carnivals, and cold cathode illumination systems. It applies to telecommunication network power supplies, cranes and hoists, lifts, generating sets, and outdoor sites exposed to heavy conditions. It also includes electric fences, and film, video, and television sites. Clause 7.2 Safety Services. Clause 7.2.1 Scope. Clause 7.2.1.1 General. This clause explains that the special requirements in Clause 7.2 apply to electrical work for building services that must keep running for safety reasons. These include systems for fire detection, warning systems, extinguishing systems, smoke control systems, evacuation systems, and systems that protect people during emergencies. The purpose is to make sure the electricity supply is not accidentally disconnected from equipment that must work during an emergency. The notes explain that ASNZS 3009 provides guidance for emergency power in hospitals, and that the term safety services covers equipment described as emergency systems in the older standard, and equipment called emergency or essential service under the building code. Clause 7.2.1.2 Fire and smoke control equipment. This clause explains what is included as fire and smoke control equipment for the purposes of this section. It includes fire hydrant booster pumps, pumps for automatic sprinkler systems, water spray or deluge systems and similar extinguishing systems, and pumps for fire hose reels when these reels are the only firefighting equipment in the area. It also includes fire detection and alarm systems, and air handling systems designed to exhaust and control the spread of fire and smoke. The clause states that the requirements do not need to apply to electrical equipment where its failure does not affect safety services, and examples include pumps used only for jacking or water pressure maintenance when this does not affect the hydrant pump that provides water supply, and pumps for fire hose reels when the reels are not the only extinguishing system, such as where sprinklers are installed. It also includes smoke alarms installed in single private residences, and the note draws attention to the standards applying to fire pumps, automatic sprinkler systems, fire detection and alarm and intercom systems, and air handling systems. The clause also notes that although the listed standards are referred to, compliance with this standard may still require meeting other regulatory requirements. Clause 7.2.1.3 Evacuation equipment. This clause explains that evacuation equipment includes sound systems and intercom systems used for emergencies, and central system emergency evacuation lighting that complies with the AS or ASNZS 2293 series. The note points to requirements for sound systems and intercoms in the AS1670 series, and for emergency evacuation lighting in the AS or ASNZS 2293 series. It also notes that although those standards are listed, there may be extra requirements from regulatory authorities. Clause 7.2.1.4 Lifts. For this clause, lifts are considered safety services when they are electrically controlled lifts used to carry people, but not lifts where people can safely exit at any point in the travel, such as escalators. The clause lists two exceptions. The first is that a lift that allows passengers to get out safely when electricity fails does not need to be arranged as a safety service. The second is that a lift in a single private residence that meets as NZS 1735.18 need not follow Clause 7.2. The note explains that although the AS 1735 series is mentioned, compliance with it may require additional regulatory requirements. Clause 7.2.2 Supply systems. Clause 7.2.2.1 Separation of supplies. This clause explains that the electrical parts supplying a safety service must be controlled by a main switch or switches that are separate from those used for the rest of the electrical installation, as described in Clause 7.2.3 and Clause 7.2.4. Circuits supplying safety services must also be separate from circuits supplying the rest of the installation. An electrical source used for safety services may also be used for other purposes as long as the availability of safety services is not reduced. The note explains that when safety services are needed, it might be necessary to disconnect power to other equipment. Clause 7.2.2.2 Discrimination of circuit protective devices. This clause explains that protective devices must be chosen so a fault on one safety service does not cause loss of supply to another safety service, and a fault on the general installation does not cause loss of supply to safety services. Fault current limiters used for safety services must not be used to protect any part of the general installation. The note explains that this discrimination applies only up to the level of arcing fault current stated. Clause 7.2.2.3 Alternative supply systems. This clause explains that when an alternative supply is provided, a changeover switch must be installed at the main switchboard so the alternative supply can feed the safety services. The generating set or other supply must be able to operate all safety services at the same time, including the initial current needed for startup or motor starting. An alternative supply of adequate size may also start working automatically if the normal supply fails. The clause then lists three exceptions. The first is that a changeover switch for fire or smoke control equipment or evacuation equipment may be located on a dedicated switchboard or control panel. The second is that a changeover switch for smoke control or evacuation equipment may be on or beside the equipment being controlled. The third is that a changeover switch for a lift may be in the lift motor room. The notes explain that alternative supply systems for hydrant and sprinkler pumps are restricted by the relevant standards, and that as NZS 3010 provides guidance on generator connections. Clause 7.2.3 Main switches. Clause 7.2.3.1 General. This clause explains that any part of an installation supplying a safety service must be controlled by a main switch that is separate from the switches used to control the rest of the installation and other safety services. The clause then lists two exceptions. The first relates to lighting equipment and a socket outlet used for a fire pump circuit in line with Clause 7.2.4.3. The second allows submains feeding an outbuilding or separate part of an installation to be controlled by switches in line with Clause 7.2.3.3 and Clause 7.2.6. Clause 7.2.3.2 Number of main switches. This clause explains that there is no limit on the number of main switches provided for safety services. Clause 7.2.3.3 Outbuildings and fire-separated portions of a building. This clause explains that a switch used for controlling safety services installed in an outbuilding and located on that outbuilding's switchboard is treated as a main switch and must follow Clause 7.2.3.1. Parts of a structure with walls providing at least 120 minutes fire resistance may be treated as separate buildings for this clause. Any switch for safety services in such a separate building must be separate from switches used to control the rest of the installation and other safety services. The clause lists an exception for lighting equipment and a socket outlet used for a fire pump circuit in line with Clause 7.2.4.3. Clause 7.2.3.4 Special lifts. This clause states that each lift or group of lifts that must operate for firefighting or for other emergency purposes must be controlled and protected independently of all other lifts. Clause 7.2.4 Arrangement. Clause 7.2.4.1 Supply. This clause explains that main switches for safety services must be connected on the supply side of all general installation main switches, must not be controlled by them, and must control only equipment regarded as safety services. The note refers to a figure for guidance. The clause lists exceptions. The first is a high-voltage switch that supplies a low-voltage switchboard not regarded as a general installation main switch. The second is a low-voltage switch that can only be used by authorized people and is clearly marked. The note explains that locking a switch may be a way to ensure only authorized people can use it. The third exception relates to automatic fire detection, alarm, intercom, and sound systems for emergencies that are supplied from the supply side of a distribution board not more than one board away from the main switchboard, and are marked in line with Clause 7.2.6, and are provided with a secondary power source in line with the AS1670 series or NZS 4512. The fourth exception is safety services in an outbuilding in line with Clause 7.2.3.3. The fifth is a switching arrangement that keeps a secure supply. The sixth is an alternative supply provided in line with Clause 7.2.2.3. Clause 7.2.4.2 Interposing switches. This clause explains that no switch may be placed between a main switch for safety services and the switchboard supplying safety services. The clause lists two exceptions. The first is where an alternative supply is provided in line with Clause 7.2.2.3. The second is where the switches are remote from the building being supplied, such as upstream switches feeding an outbuilding. Clause 7.2.4.3 Pump rooms. This clause explains that in rooms used mainly for hydrant or sprinkler pumps, lighting equipment and socket outlets may be connected as a final subcircuit to the circuit supplying the pump equipment if certain conditions are met. The final subcircuit must be protected against overcurrent in line with Clause 2.5, must be protected by an RCD with a rating not more than 30 mA, and the wiring system between the pump equipment circuit and the protective device must meet the current carrying and installation requirements of Clause 2.5.3.1. and must meet the type and segregation requirements of Clause 7.2.7.2 and Clause 7.2.8. The note explains that the wiring system between the protective device and the lighting equipment does not need to meet the type requirements of Clause 7.2.7.2. Clause 7.2.5 Mechanical protection. This clause explains that switches and control equipment that are part of a safety service installation must be properly protected if they may be exposed to damage because of where they are located or how they are used. Clause 7.2.6 Identification. Clause 7.2.6.1 General. This clause explains that all switches in the supply circuit for safety services must be clearly identified so people can tell which safety service they control. Clause 7.2.6.2 Main switches. This clause explains that main switches controlling safety services must be identified to show which safety service they operate, must be marked with the words "in the event of fire, do not switch off," and must be identified by contrasting colors or another suitable method in line with Clause 2.3.3.4. Clause 7.2.6.3 Electrical installations in outbuildings. This clause explains that a safety service main switch installed in an outbuilding must be clearly identified in line with Clause 7.2.6.1 and Clause 7.2.6.2. The note explains that a switch for safety services on the switchboard of an outbuilding is treated as a main switch in line with Clause 7.2.3.3 subclause A. Clause 7.2.6.4, Special lifts. This clause explains that main switches controlling lifts arranged under Clause 7.2.3.4 must be identified in line with Clause 7.2.6.1 and 7.2.6.2, and must also be identified separately from the main switches for other lifts. Clause 7.2.6.5, Identification of alternative supply system. This clause explains that when an alternative supply system may be affected by the operation of a switch, extra marking is required in line with Clause 2.3.3.4 and Clause 7.3.8.1.2 subclause A. Clause 7.2.7, Wiring systems. Clause 7.2.7.1, General. This clause explains that wiring systems supplying safety services must be able to keep supplying the equipment when exposed to fire. Clause 7.2.7.2, Type of wiring. This clause explains that wiring systems supplying safety services, including consumers' mains, must comply with ASNZS 3013 with AWS classification or the classification given in the standard applying to the installation. The note refers to Appendix H for more detail on the WS system. The clause also explains that when a standard does not specify a WS classification, the wiring system must be one that can keep supplying the equipment when exposed to fire or when exposed to mechanical damage, or when protected from these hazards by suitable enclosure or by installation in a place where the wiring is not likely to be damaged. The clause includes an exception stating that the fire and mechanical protection requirements do not need to apply when wiring systems are in an enclosure or location that gives the required protection, such as underground cable ducts, concrete or masonry walls or floors, or other fire-rated enclosures with suitable mechanical protection. Clause 7.2.7.3, Wiring for safety services. This clause explains when wiring for safety services must be separate from other wiring. It lists several situations in which wiring may be combined with other circuits. These include fire detection and alarm circuits compliant with AS1670 or NZS 4512 beyond the control and indicating panel, circuits that provide the primary power source for fire detection and alarm systems that have battery backup in line with AS1670 or NZS 4512 up to the control and indicating panel. Circuits for fire detection for fire and smoke control equipment compliant with its NZS 1668.1, circuits for lighting and socket outlets in pump rooms installed in line with Clause 7.2.4.3, circuits for emergency warning systems that have battery backup and comply with AS 1670 or NZS 4512 up to the main panel. Circuits for emergency warning systems that comply with AS 1670 or NZS 4512 beyond the main equipment panel. Circuits supplying lifts beyond the terminals of a circuit breaker in the lift machine room for control and protection of the lift installation. Circuits for electric-driven fire pumps that are part of a pump set including a standby fuel-driven pump. And circuits supplying battery chargers for battery-operated single-point lighting systems used for emergency evacuation. Clause 7.2.8, Segregation. Clause 7.2.8.1, Switchgear. This clause explains that when emergency equipment is required by national building codes, switchboards supplying that equipment must be constructed so the emergency equipment switchgear is kept separate from other switchgear by metal partitions to reduce the spread of faults. Clause 7.2.8.2, Cables in the same enclosure. This clause explains that conductors of safety services must not share the same enclosure with conductors of other systems. It explains that for this clause, a duct or trunking divided into separate channels by fixed continuous barriers may be treated as separate enclosures. It also states that wiring systems compliant with Clause 7.2.7.2 may be considered to give effective segregation. It also explains that wiring systems within switchboards must be separated from other wiring by at least 50 mm or by suitable barriers. Clause 7.2.8.3, Conductors and multi-core cables. This clause explains that conductors for different safety services must not be included with each other or with other conductors of any other system within a multi-core cable. Clause 7.2.9, Fire pump motors. Clause 7.2.9.1, Isolating switches. This clause explains that when fire pump motors are controlled automatically, a manually operated isolating switch must be installed on the supply side of the pump motor controller. The isolating switch must meet the requirements of Clause 2.3.3.2, must be installed either next to or on the pump motor controller, and must have a device that allows the switch to be locked in the closed position. Clause 7.2.9.2, Overcurrent protection. This clause explains that the overcurrent protective devices for fire pump motors must have an inverse time characteristic and must be rated or set so they can carry 125% of the full load motor current continuously, and can open the circuit in not less than 20 seconds at 600% of that current. It also explains that no other overcurrent protective device may be placed between the pump motor controller and the motor. When more than one motor is on the same circuit, the protective device must carry 125% of the total full load current of all motors running together, and must open the circuit in not less than 20 seconds at 600% of the full load current of the largest motor connected. Clause 7.2.9.3, Overtemperature protection. This clause explains that overtemperature protection must not be used on fire pump motors when such protection might reduce the ability of the equipment to operate during an emergency. Clause 7.2.9.4, Control circuits. This clause explains that control circuits for fire pump motors must be directly connected between the active and neutral conductors of the pump circuit. The note explains that this requirement prevents the use of transformers. Subclause B explains that the active conductor of the control circuit must be directly connected to the coil of the operating device inside the starter. Subclause C explains that overload protective devices must not be installed on the control circuit other than the devices already required for the pump motor circuit in line with Clause 7.2.9.2. The note explains that this arrangement requires a switch in the neutral conductor of the control circuit for a fire pump. Clause 7.3, Electricity generation systems. Clause 7.3.1, General. This clause explains that the requirements in this part add to, or modify, the rules in sections 2 to 7 for electricity generation systems that supply electrical installations either all the time or only sometimes. It lists the types of generation systems that may be used. The first is an engine-driven generator set, which typically uses a combustion engine. It can provide standby or alternative supply when the main power fails, act as the main supply to an installation, or be used in a standalone system. The second is a standalone power system that connects a renewable energy source such as solar, wind, or mini hydro to an installation, and can provide an AC supply from an inverter, or a DC supply. The note explains that such a system may also include an engine-driven generator. The third type is a grid-connected inverter system that provides AC power from an interactive inverter using renewable sources such as solar, wind, or mini hydro. The notes explain that grid-connected means the installation can run in parallel with the distribution system, and that these systems may include an engine-driven generator. Another note explains that the connection of a grid-connected inverter system needs formal agreement with the electricity distributor. The clause also explains that when renewable energy output is higher than the installation load, and approval is given by the distributor, the excess energy may be exported to the distribution system. When renewable energy output is too low for the installation load, the shortfall must be imported from the network. The interactive inverter also controls the importing and exporting of energy. The clause also includes a battery system that provides supply from a renewable source to charge a battery bank and provide a DC supply to an installation. Clause 7.3.2, Selection and installation of system. This clause explains that the equipment chosen, installed and controlled as part of an electricity generation system must follow the relevant standards. These include as NZS 3010 for engine-driven generating sets, AS4509 for standalone power systems, AS3011 for battery systems, ASNZS5033 for photovoltaic systems, and AS4777 for grid-connected inverter systems. Clause 7.3.3 Control. This clause explains that an electricity generation system must be controlled by an isolating switch or switches at the source of supply or at the switchboard where the system connects into the installation. The system must also be controlled by switches or devices suitable for starting and stopping it, and when more than one device is used they must be grouped together and clearly identified. The system must be arranged so that it cannot supply energy upstream of the connection point either directly or indirectly. The clause includes an exception that an electricity distributor may enter into an agreement for cogeneration or exporting energy into the upstream network under certain conditions. The note explains that the connection rules for grid-connected systems, cogeneration and other similar systems operating in parallel with the distributor's network are outside the scope of this standard. Clause 7.3.4 Isolation. Clause 7.3.4.1 General. This clause explains that each electricity generation system must have an isolating switch in line with Clause 2.3.3.2. The switch must be installed next to, or on, the system so the operator can clearly see any person working on it, or must include a means that requires a deliberate action to operate. It may be combined with overcurrent protection required by Clause 7.3.5.1. It must comply with Clause 4.13 when the system includes an electric motor, and must be under manual control only. It must not be able to be overridden or bypassed by programmable controls. The clause includes an exception stating that isolation arrangements in AS4509 or the AS4777 series are accepted as meeting these requirements. Clause 7.3.4.2 Electricity generation systems incorporating batteries. This clause explains that when batteries are included in the system, a switch capable of interrupting the supply from the batteries must be installed next to the isolating switch and clearly labeled. The clause includes an exception allowing a single switch that incorporates both AC and DC switching functions described earlier. Clause 7.3.5 Overcurrent protection. Clause 7.3.5.1 Electricity generation systems. This clause explains that electricity generation systems must have overcurrent protection. The clause includes an exception stating that overcurrent protection must not be provided where the sudden loss of supply could cause greater danger than leaving the system running. Overcurrent protective devices must be located as close as practicable to the open terminals of the system so the unprotected cable length within the installation is as short as possible and never more than 15 meters. Clause 7.3.5.2 Circuit protection. Clause 7.3.5.2.1 General. This clause explains that the prospective short circuit and earth fault current must be assessed for each electricity generation system or combination of systems capable of supplying the installation. The short circuit rating of protective devices must not exceed the rating of any part of the intended path of electricity generation. The note explains that if the system has an electronic overcurrent protection device such as an inverter that automatically limits output during faults, it may prevent the external overcurrent device from disconnecting the installation under fault conditions. The clause states that every circuit leaving the generation system must be protected in line with Clause 2.5 and include additional earth leakage protection if required by Clause 2.6. A circuit is considered protected against prospective short circuit and earth fault currents when it is supplied by a system incapable of delivering a current exceeding the rating of the circuit. The note explains that supply sources like small generators or inverters may limit fault current. The clause includes an exception stating that overcurrent protection must not be provided where sudden loss of supply could cause greater danger than leaving the system energized. Clause 7.3.5.2.2 ASNZS. This clause explains that the fault current waveform can affect how ASNZS operate and must be considered when choosing them. When the system includes an inverter, the RCD must be suitable for the inverter's waveform in line with the manufacturer's instructions. The note explains that ASCII types are covered in Clause 2.6.2.2. Clause 7.3.6, Earthing. This clause explains that the earthing system of the installation must follow Section 5 as an MEN system. An exception states that when the system output does not exceed 25 kV, the output may be arranged as a separated supply in line with Clause 7.4. Any exposed conductive parts of the system must be earthed to the main earthing conductor at the main switchboard. When several independent generation systems with engine-driven generators operate in parallel, the neutral connection of each generator winding must be switched so that only one neutral is connected to earth at one time. The note explains that this rule prevents circulating currents between generators. Clause 7.3.7, Connected electrical equipment. This clause explains that any accessory, conductor, insulation or other component connected to the output of an electricity generation system must be suitable for the voltage, current and frequency of the output unit. The note explains that current carrying capacity and voltage drop for conductors must follow ASNZS 3008.1 for 50 Hz systems. Clause 7.3.8, Connection to electrical installation. Clause 7.3.8.1, Alternative supplies. This clause explains that the following rules apply when connecting an alternative or standby supply to an installation. Clause 7.3.8.1.1, General. Subclause explains that the neutral to earth connection, called the MEN connection, must be made within the installation at the switchboard where the electricity generation system connects. The note explains that this may require disconnecting any neutral to earth connection within the generating system itself, such as an engine-driven generator set. Subclause B explains that the incoming neutral to an MEN switchboard must not be switched. The note explains that this applies to any switchboard that has an MEN connection and may be a main switchboard or a switchboard in an outbuilding treated as a main switchboard for earthing. Subclause C explains that the neutral and earth conductors must not operate in parallel. An exception explains that when connected to a distribution switchboard and operating on the alternative supply, the submain neutral and protective earthing conductors may operate in parallel through a remote MEN connection if the conductors are not overloaded by current sharing, the conductors are suitable for the maximum fault current, the copper earthing conductors meet the requirements of Clause 5.3.3, and the current carrying capacity of the neutral conductors is not less than their associated active conductor. Clause 7.3.8.1.2, Switching. This clause explains that the changeover device for an alternative supply must be chosen so that it maintains the function of the installation and prevents damage to the installation being supplied. The note explains that examples include maintaining the continuity of the neutral conductor, the operation of ASCIIs, and the continued operation of uninterruptible power supplies. The clause explains that the changeover device must open all active conductors of the normal supply when the alternative supply is connected. It explains that where a switch automatically brings the alternative supply into service, the purpose of that switch must be marked. It also explains that switching arrangements in line with ASNZS 3010 are considered to meet these requirements. The note explains that typical switching arrangements are shown in Figures 7.2, 7.3, and 7.4. Clause 7.3.8.2, Grid-connected inverter systems. Clause 7.3.8.2.1, General. This clause explains that connecting a grid-connected system requires a formal agreement with the electricity distributor. Clause 7.3.8.2.2, Switching. This clause explains that a main switch must be provided to isolate the inverter output from the switchboard it is connected to. All switches must be clearly identified for their function in line with Clause 2.3.2. Clause 7.3.8.2.3, Connection. This clause explains that the method of connection for a grid-connected inverter system must follow the AS4777 series as well as the distributor's requirements. The system must not impose a voltage on the installation at the network point of supply outside the limits in Clause 1.6.2.c. The note explains that a typical interactive inverter AC connection and main switch is shown in Figure 7.5. Clause 7.3.8.3, Standalone Power Systems. Clause 7.3.8.3.1, General. This clause explains that the consumer's mains of the installation must be connected to the output of the electricity generating system. Clause 7.3.8.3.2, Switching. This clause explains that control of the installation must be arranged in line with Clause 2.3. Clause 7.3.8.3.3, Connection. This clause explains that the connection method of a standalone system must follow the ASNZS 4509 series. The note explains that a typical standalone connection is shown in Figure 7.6, using a switchboard that includes a local MEM connection. Clause 7.4, Electrical Separation, Isolated Supply. Clause 7.4.1, Scope. This clause explains that several methods of protection against indirect electric shock are recognized in Clause 1.5.5. One method is protection by electrical separation of the supply. Electrical separation is an alternative method to prevent shock current through exposed conductive parts that may be energized by a fault in the insulation of a circuit. Protection by electrical separation must follow clauses 7.4.2 to 7.4.4. and either Clause 7.4.5 for a single item of equipment or Clause 7.4.6 for more than one item. The note explains that Figure 7.7 shows examples of separated supply. Clause 7.4.2, Source of supply. This clause explains that the supply for a separated circuit must be from an isolating transformer that complies with ASNZS 61558. or from a generator output that is isolated so the output is separated from the frame of the generator. The note explains that using an RCD or equipping a generator with an equipotential bonding conductor does not provide the correct separated output. The clause also allows an isolated inverter that complies with the safety requirements of ASNZS 4763 International. Clause 7.4.3, Arrangement of circuits. This clause explains that a separated circuit must not exceed 500 volts. All parts of a separated circuit must be reliably and effectively separated from all other circuits. Notes explain that this can be achieved by using Class II insulation or similar methods, and that this rule applies to relays, contactors and similar equipment. Each separated circuit must use a separate cable or wiring system, although multi-core cables, or a common non-conductive wiring enclosure may be used where the segregation requirements of Clause 3.9.8 are met. Exposed conductive parts supplied by the separated circuit must not be connected to any protective earthing conductor or exposed conductive parts of the source of supply. Cables and flexible cords for equipment must be protected from damage or arranged to ensure any damage can be seen. Clause 7.4.4, Switching devices. This clause explains that switching devices must operate in all live conductors of a separated circuit. The note explains that switching the active conductors of an isolating transformer in line with Clause 2.3.2 is acceptable for isolating and reconnecting supply. Clause 7.4.5, Single item of electrical equipment. This clause explains that when a separated circuit supplies a single item, no exposed conductive parts of that item may be connected to exposed conductive parts of any other circuit. Exposed conductive parts must not be connected to earth. Clause 7.4.6, Multiple items of electrical equipment. This clause explains several requirements when a separated circuit supplies more than one item. Exposed conductive parts must be connected together by an insulated equipotential bonding conductor and must not be connected to earth, to protective earthing conductors, or to exposed conductive parts of another circuit. Any socket outlet installed on the separated circuit must have its designated earthing contact connected to the equipotential bonding conductor. The designated protective earthing conductor of any supply cable or flexible cord to the equipment must be connected to the equipotential bonding conductor. Exposed conductive parts of the source of supply that are earthed must not be accessible at the same time as exposed conductive parts of the separated circuit. A protective device must disconnect the separated circuit automatically if faults expose conductive parts to different potentials. If the device is a circuit breaker, it must open all unearthed conductors at the same time. Clause 7.4.7, Testing. Clause 7.4.7.1, General. This clause explains that separated circuits must be tested in addition to the testing in Section 8. The separation must be verified by measuring the insulation resistance between the separated circuit and the transformer primary, any other wiring, and earth. Insulation resistance must be at least 1 megohm when tested at 500 volts DC. The note explains that shorter circuits may have much higher insulation values. Clause 7.4.7.2, Single items of electrical equipment. This clause explains that for a single item supplied by a separated circuit, separation must be verified as required earlier and by measuring resistance between exposed conductive parts and the earth contact of a socket outlet. Clause 7.4.7.3, Multiple items of electrical equipment. This clause explains that for more than one item on a separated circuit, separation must be verified as required earlier and by measuring resistance between the separated circuit and its equipotential bonding conductor, between the bonding conductor and earth, and between the bonding conductor and any equipotential bonding conductor of another separated circuit. Clause 7.4.7.4, Bonding conductor continuity. This clause explains that the resistance of the equipotential bonding conductor, for socket outlet earth contacts or exposed conductive parts connected to the separated circuit, must not be more than 0.5 ohms. Clause 7.5, Extra low voltage electrical installations. Clause 7.5.1, Scope. This clause explains that it applies to parts of an electrical installation operating at extra low voltage and sets the requirements for meeting Clause 1.5.7 of the standard for both basic protection and fault protection when extra low voltage is used. Clause 7.5.2, Compliance with other sections. This clause explains that extra low voltage installations must be of either SELV or PELV systems. The particular requirements in this clause replace or modify other parts of the standard when needed. If no special requirement is given in this clause, the installation must follow the other sections. When an installation operates at extra low voltage but does not meet the rules for SELV or PELV, it is considered to be an installation operating at low voltage and must meet the requirements for low voltage systems. Clause 7.5.3, Sources of supply by SELV and PELV. This clause explains that the supply for a SELV or PELV system must be from one of several sources. These include a safety isolating transformer that complies with ASNZS 61558, or a source of current independent of higher voltage systems such as an engine-driven generator or a battery, or a source of current separate from higher voltage systems such as a motor generator set with separate windings that provide electrical separation. The clause also allows certain electronic devices that limit the output voltage to extra low values under both normal and fault conditions. The note explains that such devices include insulation testing equipment. Clause 7.5.4, Separation requirements for SELV and PELV circuits. This clause explains that live parts of SELV and PELV circuits must be electrically separated from each other and from higher voltage circuits. Arrangements must provide a level of separation equal to that between the input and output of a safety isolating transformer that complies with ASNZS 61558. SELV and PELV conductors must be segregated from other circuit conductors. An exception explains that SELV and PELV circuits installed in line with Clause 3.9.8.3 may be within the same wiring system as low-voltage circuits. Live parts must be arranged so that short-circuiting or bridging between live parts or between live parts and conductive materials cannot occur under normal expected conditions. Clause 7.5.5, Arrangement of SELV circuits. This clause explains that live parts of SELV circuits must not be connected to earth or to protective earthing conductors or to live parts of other circuits. SELV circuits must not be connected to other circuits or to earthing conductors or exposed conductive parts of other systems or to extraneous conductive parts. An exception allows connection to extraneous conductive parts when equipment is designed to be connected in that way and the parts cannot reach a voltage greater than that of the SELV circuit. A note explains that if SELV circuits may come into contact with other exposed parts, the protective measure must be applied to those exposed parts and not to the SELV conductors. The clause also explains that when nominal voltage is above 25 volts AC or 60 volts ripple-free DC, basic protection against electric shock must be provided either by enclosures giving at least IP2X protection or insulation that withstands a 500-volt AC test for 1 minute. Notes explain that basic protection is not required when the voltage is below these limits, and that the insulation must withstand the test for the specified time. Clause 7.5.6 Arrangement of PELV circuits. This clause explains the requirements for PELV circuits where one conductor is earth. Basic protection must be provided by enclosures or barriers giving at least IP2X protection, or insulation that withstands a 500-volt AC test for 1 minute. An exception explains that basic protection may not be required when equipment is within the zone of equipotential bonding and the voltage does not exceed 25 volts AC or 60 volts ripple-free DC for equipment normally used in dry contact areas, or 6 volts AC or 15 volts ripple-free DC in other cases. Notes explain that earthing may be achieved by suitable connection, that ASNZS 60479 describes the surface area for large contact, and that the insulation must withstand the test voltage for the required time. Clause 7.5.7 Voltage drop in conductors. This clause explains that voltage drop at any point in an extra low voltage circuit must not exceed 10% of the nominal voltage when all live conductors carry the circuit's current. A note explains that more information is given in ASNZS 3008.1. An exception explains that this rule does not apply when equipment is designed for operation with a voltage drop greater than 10%. A second note explains that some equipment, such as motors, solenoids and items that draw high transient currents, may be affected by voltage drop and are excluded from this consideration. Clause 7.5.8 Control of an electrical installation. Clause 7.5.8.1 Main switches. This clause explains that the supply to an extra low voltage installation must be controlled by a main switch or switches operating in all unearthed conductors. An exception explains that this requirement does not apply when the extra low voltage installation is supplied from part of a higher voltage installation where the extra low voltage depends on the higher voltage supply and the high voltage main switch disconnects both systems. Clause 7.5.8.2 Other switches. This clause explains that switches must operate in all unearthed conductors when the supply is earthed at the point of supply, such as PELV switches may operate in one fewer conductor than the number of conductors in the circuit for SELV. Clause 7.5.9 Overcurrent protection. Clause 7.5.9.1 General. This clause explains that every extra low voltage circuit must have protection at its origin against overload and short circuit currents as required in clauses 2.2 and 2.5. Protection may be provided in fewer conductors than the number of conductors in the circuit. When the supply is earthed, protective devices must be in all unearthed conductors. An exception explains that circuits in line with clause 7.5.9.2 do not need overcurrent protection. Clause 7.5.9.2 Emission of overcurrent protection. This clause explains that overcurrent protection does not need to be provided when interrupting the supply could cause greater danger than not interrupting, or when the rated output of the supply does not exceed the rating of the circuit, or when the circuit is supplied from a transformer that is short-circuit proof under ASNZS 61558 and the transformer output does not exceed 1 ampere or the short-circuit current is not more than the rating of the conductors and that value is marked on the transformer. It may also be emitted when the circuit is supplied from a battery with high internal resistance such as Leclanche type or dry primary cells. Clause 7.5.10 Connecting devices. This clause explains that plugs and socket outlets for SELV and PELV systems must meet certain requirements. Plugs must not be able to enter socket outlets of other voltage systems. Sockets must not accept plugs of other voltage systems. Sockets must not have a contact for an earthing conductor. Clause 7.5.11 Wiring systems. Clause 7.5.11.1 General. This clause explains that conductors and cable insulation used for extra low voltage installations must be suitable for their intended purpose and do not need further protection unless the conditions of use demand it. The note explains that segregation requirements and wiring system protection under Clause 3.9.8.3 may still apply. Clause 7.5.11.2 Aerial conductors. This clause explains that aerial conductors used in extra low voltage installations must follow Clause 3.12. Exceptions explain that clearances above ground or elevated areas do not apply when Clause 3.3.1 is met, and bare conductors may be used if they comply with the rules for insulated conductors. Clause 7.5.11.3 Underground conductors. This clause explains that there are no burial depth requirements for safety of extra low voltage cables. A note explains that possible mechanical damage must still be considered. Clause 7.5.12 Testing. Clause 7.5.12.1 General. This clause explains that extra low voltage circuits must be tested to confirm separation. Testing follows Clause 7.5.12.2 for SELV and Clause 7.5.12.3 for PELV. Insulation resistance measured under these clauses must not be less than 0.5 megohms when tested at 250 volts DC. Clause 7.5.12.2 Protection by SELV. This clause explains that separation of live parts from other circuits and earth must be confirmed by measuring insulation resistance. Clause 7.5.12.3 Protection by PELV. This clause explains that separation of live parts from other circuits must be confirmed by measuring insulation resistance. Clause 7.6 High voltage electrical installations. This clause applies to any part of an electrical installation that operates at high voltage. For protection and earthing purposes, the rules here also cover the equipment up to and including any low-voltage cables and switchgear connected to high-voltage transformers. This clause does not apply to electric discharge lighting systems, to X-ray equipment, to high-frequency equipment, or to any high-voltage wiring that is completely enclosed within self-contained equipment and supplied at low voltage where precautions stop contact with high-voltage parts. Clause 7.6.2.2 in New Zealand. In New Zealand, any electrical installation that operates at high voltage must be installed in line with the requirements of the New Zealand electrical regulations. Clause 7.6.3 Issues relevant to high voltage installations. When planning or designing high voltage electrical installations, a range of issues must be considered because the risks are more significant than for installations below 1 kV. These issues include ensuring the insulation can withstand the highest voltage and impulse levels, providing adequate clearances to live parts, and considering any special conditions that may reduce safe clearances. The way connected devices behave under high voltage must also be taken into account. The methods used to install equipment, cables and accessories are important, as are general installation requirements such as circuit arrangement, documentation, transport routing, lighting, operational safety and labeling. Special building requirements may apply, and careful thought must be given to safe access and protection against both shock and fire. The earthing system must operate correctly under all expected conditions, and there must be provision for testing. Clause 7.7 Hazardous areas, explosive gas or combustible dusts. Clause 7.7.1 Scope. This clause applies to the selection of electrical equipment and the way it is installed in areas where flammable or combustible materials are produced, prepared, processed, handled or stored. These situations may create an explosive atmosphere, and electrical equipment must be suitable for these conditions. Clause 7.7.2 Classification of hazardous areas. Responsibility for determining whether an area is hazardous rests with the people in control of the installation. Hazardous areas are defined using the requirements of as NZS 60079.10.1 for gas or vapor, and as NZS 60079.10.2 for combustible dust. Clause 7.7.2.2 Recognized hazardous areas. Two main types of hazardous areas are recognized. The first is hazardous areas formed by gas or vapor where a flammable atmosphere is present or may be present. These areas are divided into zones based on how often and how long the flammable atmosphere is expected, and include vapors arising from liquids. The second type is hazardous areas formed by dust. These areas involve clouds of combustible dust that may be present or may form, and special precautions are needed for installation and use of equipment. Dust hazards are also divided into zones, and the possibility of an explosive dust cloud forming above a settled layer must be considered. Combustible dust can include fibers and flyings. Clause 7.7.3 Reduction or elimination of the hazard. Through careful design, the level of hazard can often be reduced. This can include the way plant is laid out, the ventilation provided, and the selection of suitable equipment. Clause 7.7.4 Electrical equipment. Electrical equipment used in hazardous areas must meet the requirements of as NZS 60079.14 for its selection and use. Clause 7.7.4.2 Installation. Electrical equipment must be installed following the requirements of as NZS 60079.14. Additional requirements for competence of persons and inspection and maintenance are given in the associated standards. Clause 7.8 Specific electrical installation standards. Clause 7.8.1 Scope. This clause identifies standards that apply to particular electrical installations. Some give extra requirements to this standard, some provide requirements that, when met, are taken as complying with this standard, and others give guidance for special electrical installations. Clause 7.8.2 Additional requirements of this standard. Clause 7.8.2.1 Construction and demolition sites. Electrical installations on construction and demolition sites must comply with as NZS 3012. Clause 7.8.2.2 Electromedical treatment areas. Electrical installations in electromedical treatment areas must comply with as NZS 3003. Clause 7.8.2.3 Transportable structures and vehicles including their site supplies. Electrical installations in transportable structures and vehicles, including site supplies, must comply with as NZS 3012. Clause 7.8.2.4 Marinas and recreational boats. Electrical installations in marinas and recreational boats must comply with as NZS 3004. This standard has two parts, one for marinas and one for recreational boats. Clause 7.8.2.5 Shows and carnivals. Electrical installations in shows and carnivals must comply with as NZS 3002. Clause 7.8.2.6 Cold cathode illumination systems. Cold cathode illumination systems must comply with as NZS 3137. Clause 7.8.2.7 Telecommunications networks power supplies. Extra low voltage direct current power supplies within public telecommunications networks must comply with as NZS 3015. Clause 7.8.2.8 Cranes and hoists. Electrical installations for cranes and hoists must comply with the relevant parts of the AS 1418 series or other requirements set by regulatory authorities. Clause 7.8.2.9 Lifts. Electrical installations of lifts must comply with the relevant parts of this standard. Additional requirements may apply depending on the type of lift installation. Clause 7.8.3 Deemed to comply standards. Electrical installations in single domestic dwellings that comply with as NZS 3018 are taken as meeting the requirements of this standard. Clause 7.8.4 Specific electrical installation guidance. Clause 7.8.4.1 Generating sets. Guidance on minimum safety requirements for generating sets operating at voltages normally not exceeding 50 volts AC or 120 volts DC is given in as NZS 3010. Clause 7.8.4.2, Outdoor sites under heavy conditions. Electrical installations at outdoor sites exposed to heavy conditions must meet the relevant requirements of this standard as far as they apply. Clause 7.8.4.3, Electric fences. Guidance on the installation requirements of electric fences is given in as NZS 3014 and as NZS 3016. Where an electric fence is connected directly or indirectly to electricity supply mains, the connection must be through an improved fence controller. Clause 7.8.4.4, Film, video and television sites. Guidance on safe procedures for electrical equipment and temporary electrical installations at film, video and television sites is given in as NZS 4249. Further requirements may be set by regulatory authorities. That brings us to the end of Section 7. In this section we've covered a wide range of special installations, each with its own set of requirements to keep people and property safe. Whether it's emergency systems, generation systems, isolated supplies, extra low voltage work, high voltage installations or hazardous areas, the key idea is always the same: understand the risk, choose the right equipment and install it so it performs safely under all expected conditions. As you work with these types of installations, keep these principles in mind and always refer back to the detailed requirements when you need them. Now we can move on to the next part of the standard. Hi everyone, and welcome to this audiobook designed for the EWRB Electrician Regulation Exam. My name is Aria, and I work alongside Whit Roy as an electrical tutor. This audiobook explains the exam topics in simple spoken language, making it easier to understand and review anywhere, anytime. Before we get into the lesson, I want to explain what this audiobook actually is. This audiobook is not a word-for-word reading of as NZS 3000. You must always refer to the real standard when you're doing electrical work or preparing for an assessment. What we do here is take the important ideas from the standard and rewrite them in simple spoken English. The goal is to make the rules easier to understand, easier to remember, and easier to revise, especially when you're listening on the go. So think of this audiobook as a learning guide, not a replacement for the actual standard. Alright, let's begin. Today we move into Section 8, Verification, which is all about verification. In this section we look at the checks and tests that must be carried out to make sure an electrical installation is safe before it is put into service. I'll take you through each clause in clear, simple language so you understand what needs to be inspected, what needs to be tested, and why these steps matter for safety and compliance. Let's begin Section 8, Verification. Clause 8.1, General. Clause 8.1.1, Application. The provisions of Section 8 represent the minimum standard of inspection and testing that must be achieved to satisfy the fundamental safety principles of Part 1 of the standard in relation to verification of an installation. Clause 8.1.2, Requirements. Prior to placing an electrical installation, or any part of it, into service following construction, alteration, addition or repair, it shall be verified, as far as practicable, that the installation is safe to energize and will operate correctly in accordance with the requirements of this standard. To confirm that the requirements of this standard have been met, after completion and before being placed in service, the installation shall be inspected as far as is practicable and tested in accordance with Clause 8.3. Precautions shall be taken to ensure the safety of persons and to avoid damage to property and electrical installation equipment during inspection and testing. Where the electrical installation is an alteration, addition, or repair to an existing electrical installation, it shall be verified that the alteration, addition, or repair complies with this standard and does not impair the safety of the existing electrical installation. Certain types of test, such as those involving thermal properties and operation, may be carried out after the electrical installation has been placed in service. Periodic inspection and testing of electrical installations shall be performed in accordance with the requirements of the regulatory authority or the owner or occupier of the premises. Recommended periodic testing arrangements are set out in ASNZS 3019. Additional visual inspections and testing may be required for specific installations, including separated supplies, SELV and PELV installations, medical electrical installations, transportable structures and vehicles, and marinas. Guidance for these electrical installations can be obtained from the provisions of Section 7 and the installation standards referenced in Clause 7.8. Clause 8.2, Visual Inspection. Clause 8.2.1, General. A visual inspection shall be made when work on an electrical installation has been completed in order to verify that the work complies with the requirements of this standard. The visual inspection shall be carried out before, or in association with, testing and should, where practicable, be made before the relevant part of the electrical installation is placed in service. Where the visual inspection of a part of the electrical installation is not practicable at the completion of the work, for example where it is not accessible because of enclosure in the building structure, consideration should be given to inspecting that part during the course of the installation. Clause 8.2.2, Checklist. The following items provide a guide to the matters to be checked during the visual inspection to assess that the relevant requirements of this standard are satisfied. Under Item A, General, basic protection against direct contact with live parts such as insulation and enclosure. Fault protection against indirect contact with exposed conductive parts, for example by the use of automatic disconnection of supply, double insulation, or isolating transformers. Protection against hazardous parts such as enclosure, guarding or screening of flammable materials, hot surfaces and parts that may cause physical injury. Protection against the spread of fire such as penetration of fire barriers. And the general condition of the electrical equipment such as any signs of damage that could impair safe operation and disconnection of unused electrical equipment. Under Item B, Consumers Mains, current carrying capacity, voltage drop including conductor size, underground installation conditions including enclosure depth, burial and mechanical protection, aerial installation conditions, connection of wiring, and protection against external influences. Under Item C, Switchboards, location including access and egress, protective devices including selection and setting of adjustable protective devices for overcurrent protection and discrimination, isolating devices such as main switches, connecting devices such as neutral bars, earth bars and active links, connection and fixing of wiring and switchgear, identification and labeling of electrical equipment, and protection against external influences. Under Item D, Wiring Systems, conductor size including current carrying capacity and voltage drop, identification of cable cores, adequate support and fixing, connections and enclosures, particular installation conditions such as underground aerial and safety services, segregation from other services and electrical installations, and protection against external influences including enclosure. Under Item E, Electrical Equipment, isolation and switching devices for protection against injury from mechanical movement devices and motors, isolation and switching devices for protection against thermal effects such as motors, room heaters and water heaters, switching devices for particular electrical equipment such as socket outlets and water heaters, particular installation conditions such as locations affected by water explosive atmospheres, extra low voltage and high voltage, compliance with the required standard, connection support and fixing, and protection against external influences. Under Item F, Earthing, ME in connection, earth electrode, earthing conductors including size and identification, and equipotential bonding conductors including size and identification. Clause 8.3, Testing. Clause 8.3.1, General. After completion of, or in association with, the visual inspection, tests in accordance with Clause 8.3.3 shall be carried out on the electrical installation to verify that it complies with the requirements of the standard and that it is suitable for use after connection to the supply. If necessary, additional tests may be carried out. Notes explain that the test methods described are reference methods and other methods may be used if they give equally valid results, and that ASNZS 3017 sets out some common test methods required to test that a low-voltage electrical installation complies with this standard, and that additional tests for isolated supplies and for ELV systems are detailed elsewhere in this standard. Clause 8.3.2, Application of ASNZS 3017. ASNZS 3017 sets out some of the common test methods required to test that a low-voltage electrical installation complies with this standard. Clause 8.3.3, Mandatory tests. The following tests shall be carried out on low-voltage electrical installations. Under Item A, continuity of the earthing system including earth resistance of the main earthing conductor, protective earthing conductors and bonding conductors in accordance with Clause 8.3.5. Under Item B, insulation resistance in accordance with Clause 8.3.6. Under Item C, polarity in accordance with Clause 8.3.7. Under Item D, correct circuit connections in accordance with Clause 8.3.8. Under Item E, verification of impedance required for automatic disconnection of supply in accordance with Clause 8.3.9. Under Item F, operation of RCDS in accordance with Clause 8.3.10. If the installation fails a test, that test and any preceding tests that may have been influenced by the fault shall be repeated after the fault has been rectified. Notes explain that items E and F may require supply to be available, and high-voltage installations may require additional tests. Clause 8.3.4, Sequence of tests. The verification test must be carried out in a set order so each safety step is confirmed before moving on. First, we begin with a visual inspection. This is where we check the installation for any damage, defects, or poor workmanship. Once the installation passes that check, we move to the main earthing conductor. Here we confirm that the main earth path is continuous and reliable. After that, we check the equipotential bonding. This makes sure that all bonding conductors are properly connected to earth. When the earthing and bonding are confirmed, we carry out the insulation resistance test to ensure the wiring insulation is sound and has a safe resistance value. The next step is to verify correct polarity. This confirms that the active, neutral, and earth conductors are all connected to the correct terminals. Following polarity, we check the circuit connections. This ensures there are no short circuits and no conductors accidentally linked between circuits. With those checks done, the installation is ready for the earth fault loop impedance test. This test confirms that if a fault occurs, the protective device will disconnect quickly enough to keep the installation safe. After that, we test the operation of the RCDS to make sure each one trips correctly when a residual current occurs. For three-phase installations, the final step is to check the phase rotation, confirming that all socket outlets and supply points have the same phase sequence. This sequence provides a clear, safe, and reliable way to verify an installation before it is put into service. Clause 8.3.5, Continuity of the earthing system. Clause 8.3.5.1, General. Tests to prove the continuity of the earthing system, including earth resistance of the main earthing conductor, protective earthing conductors and bonding conductors, are necessary to ensure that the earthing system has been installed so that protective devices will operate if there is a fault between live parts other than the neutral and the mass of earth. An effective earthing system will ensure that exposed conductive parts of electrical equipment do not reach dangerous voltages when such faults occur. Clause 8.3.5.2, Results. The resistance of protective earthing conductors shall be low enough to permit the passage of current necessary to operate the overcurrent protective device, and consistent with the length cross-sectional area and type of conductor material. For example, for a 100-meter length of 2.5 square millimeter copper conductor, a resistance of 0.8 ohms could be expected. The resistance of the main earthing conductor or any equipotential bonding conductor shall be not more than 0.5 ohms. Notes explain that allowable resistance depends on the protective device type and rating and the impedance of the live conductors, and that maximum resistance values for earthing conductors are given in a table. Clause 8.3.6, Insulation resistance. Clause 8.3.6.1, General. An insulation resistance test is necessary to ensure that the insulation resistance between all live conductors in earth, or as the case may be, all live parts in earth, is adequate to ensure the integrity of the insulation. This is to prevent electric shock hazards from inadvertent contact, fire hazards from short circuits, and equipment damage. An insulation resistance test between conductors is also necessary for consumers' mains and submains to minimize the potential for insulation breakdown, injury or property damage because of failure of such conductors. The integrity of the insulation is stressed by applying a direct current at 500 volts. Exceptions state that where equipment such as electromagnetic compatibility filters or equipment containing surge protective devices connected to earth, or electronic equipment, is likely to be damaged, such equipment shall be disconnected or switched off before carrying out the insulation resistance test, or the test voltage for that particular circuit may be reduced to 250 volts direct current, in which case the insulation resistance should not be less than 1 megohm. A second exception states that where equipment such as an RCD with an FE connection is likely to influence the verification test, the FE connection shall be disconnected before testing, or the insulation resistance of the FE connection shall be not less than 0.05 megohm, or as prescribed by the manufacturer. The insulation resistance tester shall be able to maintain its terminal voltage within plus 20% and minus 10% of the nominal open circuit terminal voltage when measuring a resistance of 1 megohm on the 500 volt range or 10 megohms on the 1000 volt range. Clause 8.3.6.2 Results. The insulation resistance between the conductors of consumers' mains and submains and between live and earthed parts of an electrical installation, or parts thereof including consumers' mains and submains, shall be not less than 1 megohm. Sheet heating elements of appliances, a CDS with a functional earth connection and some other electrical equipment may cause test results lower than 1 megohm and should be disconnected from the circuit prior to testing. Acceptable insulation resistance values for such items are 0.01 megohm for sheet heating elements of appliances, or the value permitted in the standard applicable to the electrical equipment. A note explains that where consumers' mains or submains are not of significant length, the insulation resistance of the circuit should be significantly greater than 1 megohm. For example, with short lengths of polymeric cables, a value in excess of 5 megohms would be expected. Clause 8.3.7 Polarity. Clause 8.3.7.1 General. Polarity testing is necessary to ensure that no shock hazard arises from the incorrect connection of active, neutral and earthing conductors. This testing is to prevent the transposition of active and neutral conductors of the consumer's mains or submains supplying an outbuilding having an MEN connection, resulting in the electrical installation earthing system becoming energized, and to prevent combinations of incorrect active, neutral and earthing conductor connections resulting in the exposed conductive parts of the electrical installation becoming energized. Clause 8.3.7.2 Results. Proof shall be obtained that all active, neutral and protective earthing conductors in the electrical installation are correctly connected to their corresponding terminals. This includes ensuring there is no transposition of conductors that could result in equipment becoming unsafe, particularly where appliances are connected by socket outlets, ensuring switches or protective devices do not operate independently in the neutral, earthing or a combined protective earthing and neutral conductor, ensuring all Edison screw lamp holders not incorporated in an appliance or provided with a shroud or skirt have the neutral connected to the outer contact, and ensuring all fixed socket outlets for multi-phase supplies are connected so the phase sequence is the same throughout the installation. Clause 8.3.8 Correct circuit connections. Clause 8.3.8.1 General. Tests for correct circuit connections are necessary to ensure that protective earthing conductors do not normally carry current and that no short circuit exists, because a short circuit current flowing between live conductors and through part of the earthing system can cause considerable fire damage or personal injury, particularly in high current locations. Clause 8.3.8.2 Results. Proof shall be obtained that the active, neutral and protective earthing conductors of each circuit are correctly connected so that there is no short circuit between the conductors, no transposition of conductors that could result in the earthing system and any exposed conductive parts of the installation becoming energized, and no interconnection of conductors between different circuits. A note explains that any MEN or ESR connection is not considered as a short circuit. Clause 8.3.9 Verification of impedance. Earth fault loop impedance. Clause 8.3.9.1, socket outlet circuits not protected by an RCD. Where an installation includes circuits containing socket outlets not protected by an RCD, the impedance required for automatic disconnection of supply shall be verified on each such circuit. This includes verification of the total resistance of the active and protective earthing conductors and, where supply is available, verification of the earth fault loop impedance in accordance with Clause 8.3.9.3. Where supply is available and the installation is connected to a distribution system, the earth fault loop impedance test is performed in order to verify the complete earth fault loop, including the integrity of the MEN connection and the upstream neutral conductors. These tests shall be carried out to verify that the protective device will operate to disconnect an earth fault current within the time and touch voltage requirements of Clause 5.7. A note states that further information on maximum earth fault loop impedance is contained in Table 8.1. Clause 8.3.9.2 results. The values obtained shall satisfy the requirements of Clause 5.7.4. This requirement is deemed to be satisfied if the total resistance of the active and protective earthing conductors of an individual circuit that forms part of the earth fault loop does not exceed the value shown in Table 8.2 when tested in accordance with Clause 8.3.9.3. Or, where supply is available, the earth fault loop impedance measured at a socket outlet does not exceed the value shown in Table 8.1 when tested in accordance with Clause 8.3.9.3. Notes explain that the values of ZS in Table 8.1 are calculated as shown in paragraph B4.5, that the values in Table 8.2 are calculated using specified conductor resistances, and that if an RCD operates during the test the result is considered satisfactory although it may not verify the MEN connection and upstream neutral conductors. Clause 8.3.9.3 Method of measurement. Clause 8.3.9.3 Subclause A, supply not available. Where supply is not available, the resistance of the conductors of each individual circuit may be measured by an ohmmeter by connecting the active conductor and protective earthing conductor together at the origin of the circuit, and at the most distant point connecting one lead of the ohmmeter to the active conductor, and the other lead to the associated protective earthing conductor. The measured value of resistance shall not exceed the value in Table 8.2 for the appropriate conductor size and type of protective device. Clause 8.3.9.3 Subclause B, supply available. Where supply is available, the required impedance should be measured using an instrument with the facility for measuring and indicating low values of impedance. A note states that earth continuity and resistance tests should be carried out on protective earthing conductors in accordance with Clause 8.3.3 before measuring earth fault loop impedance. The MEN connection is to be left intact. Measurements should be carried out with the instrument connected between the most distant point on the active conductor and the point on the associated protective earthing conductor at the socket outlet. A note states that this test verifies the integrity of the MEN connection and the upstream neutral conductors, measures the value of ZS for the complete circuit, and should be performed in a manner that ensures the safety of the operator. Appropriate values of ZS are given in Table 8.1. Clause 8.3.10, Operation of RCDS. Supply must be available to perform this test. Clause 8.3.10.2, New Zealand. Tests shall be performed on each final subcircuit protected by an RCD to verify that the RCD operates to disconnect the designated circuit. In New Zealand, the function of each RCD shall be verified by the operation of the integral test device provided that the manufacturer's compliance documentation or equipment markings confirm that the RCD is intended to operate under residual alternating current and residual pulsating direct current conditions, or by the use of test equipment that causes the device to operate under residual alternating current and residual pulsating direct current conditions. Notes explain that if the RCD being tested is marked with a symbol confirming that it is a Type A RCD, the residual pulsating direct current testing may be omitted, that the connection of test equipment to fixed wiring shall be restricted to supply connections by a 3-pin plug connected into a socket with a purpose-made tester connection cord, and that a suitable test could be performed using a test plug with a resistor between the active and earth pins. Clause 8.3.10.3 Results. The RCD shall disconnect the supply. Clause 8.4 Date of initial energization of an installation. The date of initial energization or certification of an installation shall be available on site either by marking or in an accessible record. In order to enable verification, it is necessary to know the details of the original verification. This will facilitate the operation of a re-verification regime when required. That brings us to the end of Section 8, and the end of this audiobook. You've now worked through all the verification steps, from inspection to testing, and the final details needed before an installation is energized. These requirements help ensure every installation is safe and ready for use. Thank you for listening, and I hope this guide has made the standard easier to follow and easier to learn.